Hey everyone, in this course we're going to be learning about all the fundamental data structures and algorithms that you need to know, especially with a focus on coding interviews. This course is meant for beginners or anyone who just needs a refresher. We're going to be talking about the design, implementation, trade-offs, and analysis of all the common data structures and algorithms. Being able to solve these problems efficiently, analyze them, discuss their trade-offs, and then communicate the idea to others is what can make a difference in hundreds of thousands of dollars in compensation. I hope the problem-solving skills you learn in this course can serve you for your entire career. For more details on what we're going to cover, please scroll down, and when you're ready, let's get started. So the first data structure that we're going to cover is arrays. But before we even get into that, let's first understand what even is a data structure. Well, as the name implies, it's a way of structuring data, but in our case, we're talking about computers. So we're going to be structuring this data inside of RAM. Let me show you what I mean. So suppose that this is our RAM in this case. And RAM is basically where all of our variables are going to be stored. So as we write code and as we use array data structures, let's say that this over here is our array. Even though maybe we don't quite know what it is yet, we know that this is going to be stored in RAM. Let's say we have a 1, a 3, and a 5 in our array. So this is the information that we're trying to store. Now, how are we going to store it in RAM? Well, first of all, RAM is measured in bytes. It's common for many computers to have, let's say, 8 gigabytes of RAM. What do we mean by gigabyte? Well, giga in this case means about 10 to the power of 9. So let's say that's about a billion. But the more important question is, what exactly is a byte? Well, a byte is nothing more than 8 bits. So the next question is, what exactly is a bit? A bit can be thought of as a position that can store a digit. But the restriction on the digit is that it can either be a 0 or a 1. You might already be familiar with this. Zeros and ones are the language of computers. And as you can already see, individual bits can form multiple bits, which can form bytes, which can form RAM, and RAM can be used to store advanced data structures. But now let's get back to what arrays are. Now in this case, we have an array of integers, as you can tell. Now don't worry, I know I still haven't told you what an array actually is. So in this case, we have an integer 1. How can we store this integer 1 in our RAM? Well, we have to store it in terms of bytes. Now it's pretty common for integers to be represented not by a single byte, but actually as 4 bytes. So what that would mean is instead of using 8 bits, we would actually have, let's say, 32 bits. I'm not going to draw all of them out, but you can assume that we have in total over here, we have 32 bits. So how are we going to represent this 1? Well, we're going to talk about this a little more in depth later in the course, but for now, I'll just tell you that it's going to be 31 zeros, and then all the way at the end, we're going to have a single 1. So what's important here is that we have a way to take this 1, represent it in terms of bytes, and then we're allowed to put that into RAM. Now, while RAM can be thought of as a contiguous block of data, it also has 2 components to it. Of course, we're going to be storing values in our RAM, but every value is going to be stored at a distinct location, which we call an address. Now, I've put a $sign in front of every address just to kind of distinguish that between the values that we're going to be storing. But what you can see here is that the first address is 0. Now, as we store an array in RAM, we don't always get to choose what location it's going to be at. But one thing about arrays is that they're always going to be contiguous. What that means is here we're going to be storing the 1. Here we're going to be storing the 3, and here we're going to be storing the 5. So nothing is going to be in between the 3 that we have stored over here and the 5 that we have stored over here. Nothing is going to be in between that. But if that's the case, why am I incrementing the address by 4 every time? Shouldn't this be stored at 0? This should be stored at address 1. this should be stored at address 2. Well, remember, each value takes 4 bytes to store. So this doesn't represent 1 byte, it represents 4 bytes. So we're storing 32-bit integers. That means they take 4 bytes to store. Now this might seem very straightforward, and it is for the most part, and that's because arrays are considered the most simple data structure. We just store them pretty much the same way that we're representing them here. In memory, they look the exact same as they do the way we use them. A contiguous set of values. Now in this case we're storing integers, but we could be storing other values as well. Let me show you what it would look like if instead we were storing characters like ABC. Characters are stored pretty much exactly the same, contiguously as we would expect. But you notice the address is a bit different. In this case we're incrementing by 1 as we add a new character. That's because each character actually only takes 1 byte to store in memory, not 4 bytes. At least that's the typical case if we're storing ASCII characters, which isn't super important to know. What I'm getting at though is we can store values contiguously regardless of how big or small they are, as long as we increment our address by the size of the value. So this was definitely a lot of theory to understand, but don't worry, this course is mostly going to focus on practical knowledge. But at least we learned a bit about what memory is and how arrays can be stored in memory. Now it's time to understand how arrays can be used and what exactly are its properties and trade-offs up next. Now let's discuss the properties of arrays, but first to review, we know that an array is a contiguous block of data. We know it's stored the same way in RAM. It's stored as a contiguous block of data. Now with any data structure, the two most common operations are reading to the data or writing to the data. We're going to first handle the simple case, which is reading the data. Let's suppose we want to read the first element of our array. Well, as a programmer, we have an array. Let's say we allocated it by calling it myArray. So this is a variable that we have. To read the first element, the intuitive thing is to go in memory at the first address and then read the value. Now that's exactly what's happening under the hood, but we as programmers don't need to know the exact address of every single value. As we use the array, we use indexes to access values. The first value is always at index 0, not at index 1. That can be confusing if you're a beginner, but it's always starting at 0. The next one is at 1, and the next one is at 2, etc., etc. So when we read the first value, which is at index 0, it's automatically going to go to this location in our memory and read the value that's stored in memory. Since we can automatically map any index in our array to a location in memory, that means we can instantly read any value as long as we have the index for it. To represent that that's an efficient operation, we call it big O of 1. We're going to talk more about big O notation later in the course, but for now, what this means is that in the worst case, to read a value, assuming we have the index, so suppose we want to read the value at index 2, it's an instant operation. It happens in constant time. No matter how big our array gets, if we want to read any value in the array, we can read it instantly. That's what big O of 1 means. At least that's the oversimplified explanation so far. The fact that we can go to any arbitrary address in our RAM and then read the value at that address is a property of RAM. It's actually in the name itself. Random access memory is what RAM stands for. It basically means we can randomly access any portion of the memory in constant time. Suppose if we wanted to access this value, we don't have to start from the beginning of our RAM and then keep looking for it. We can automatically access it. And that's pretty important, as you can tell, because if we have a lot of RAM, we don't want to have to go through the entire RAM every single time. If we want to access the third value in the array, we don't want to have to go through the first and second values because it's not necessary for us. Now, after we read our first value, next we want to read the second value and the third value and keep doing that until we get to the end of the array. That's pretty easy. We know that the first index we start at is, let's say, 0. I'm going to call it I. In code, we would typically say my array at index I to read the value. And then of course we would increment the I to be 1, and then we would increment it to be 2, and we would keep doing that until it equaled the length of the array, and then we would stop. So essentially we would loop through the entire input array. In most languages, you can do so with a for loop or a while loop. Now, while this might seem really simple, the ideas that we're talking about now are going to be the building blocks for very advanced algorithms we talk about later in the course. So we talked about reading from an array. Now it's time to talk about writing to an array, which is going to bring us to an important properties of arrays, which is that they're of fixed size. In this case, we declared an array of 3 values. It's fixed size. Suppose we want to add a 4th value to it, let's say a 7. Well, taking a look at our model of memory, so the simple thing to do would just be add a 7 in memory, but we have to make sure it's contiguous, so we would do so only at address 12. So then we have an array of size 4, and it's still contiguous. This seems like it might work, but the way RAM works, we don't always get to decide exactly where we allocate our RAM. We don't always get to decide exactly where we store our values. And we don't know for sure that this spot in RAM is even available for us. It could be that we already have maybe another array stored over here, or maybe the operating system is using this part of our memory for some other purpose. So we're not necessarily allowed to put the 7 over here. Okay, then you might think, well, let's just let the operating system decide. Just put a 7 anywhere in memory. But if we do that, we don't follow the property of arrays. It's no longer contiguous. Now we have 2 arrays. That's not what we wanted. We wanted a single array, because if we do it like this, and then let's say I'm looping through this array, I'm at index 2, now I increment and I'm at index 3, what we're going to try to do by accessing this is we're going to go to this spot, but we don't know that the 7 is stored over here. It might be stored somewhere else. So this is going to break. Basically, we've come across the biggest limitation of arrays, at least for static arrays, which is what we've talked about so far. Static arrays basically mean that they're fixed size arrays. So before we continue to discuss the limitations of static arrays, I do want to mention, if you're used to a programming language like Python or JavaScript, you might have never come across this limitation because those languages don't really offer static arrays. You never have to worry about running out of space when you're using an array. And that's because those languages usually offer dynamic arrays as the default, which we're going to discuss later on. So suppose we allocated an array of size 3. Initially it's empty, but there has to be something stored here. And usually by default, languages will initialize it to be all 0, or sometimes they won't initialize it at all. And sometimes there can just be some random values here, like just some random arbitrary values that we didn't even put there. So initially we have some space. Let's say we start adding values to it. We add a 5, that puts a 5 in memory. We add a 6, that puts a 6 in memory. We add a 7, that puts 7 in memory. Now we're allowed to remove values, but when we say remove, we can't actually delete this in memory. We can't deallocate that with a static array. When we say remove a value, we're basically saying we're going to overwrite it by putting, let's say, 0 in that case. And we would say that this value is no longer relevant. We have a 0 here. We only care about these 2. This is still in memory, but we don't care about it. And we can, remove all the values in a similar way. But what we can't do is add a new value. By the way, as we add a new value to the end of the array at the next empty spot that we're keeping track of, it's also going to be an instant operation because we know this is index 0, this is index 1. We want to write to this position. Therefore, we know instantly that we're writing to this position in RAM. So writing to any position is also a big O of 1 operation. It's constant time. We can think of it as an instant operation. Similarly, removing a value is also as efficient as big O of 1. It's a constant time operation because what we're really doing is just going to that position in memory and Xing it out. we could be replacing it with a 0 or a -1 or something like that. We're not actually deleting it, but we're overwriting it. So these are the efficient operations with a static array. So we have a couple values in our array, and remember, these are ordered values. The 5 comes before the 6. We know that because of the way the indexes work. So let's say we wanted to arbitrarily insert a value into the middle of the array at any position in the middle of the array. By that, I mean any position in between these values, at the end of these values, or at the beginning. We know inserting at the end is always efficient because we're inserting into an empty spot. If at least there's one available. We're assuming that there is space available. That's efficient. That's O of 1. But inserting at any arbitrary position, like the middle or at the beginning, is not going to be efficient because let's say I want to insert the value 4 at this position. Now, it's easy enough to overwrite the value with a 4, but then we have a 4 and a 6. What we actually want is to have 4, 5, 6. We could put the 4 over here because that's efficient. It's O of 1 and there is space there, but that doesn't achieve 4, 5, 6. We have the elements out of order. With arrays, including static arrays, the order of the values does matter. So for us to insert the 4 over here, we first have to shift the 5 to the next position. But if we shift it over here, we're going to get rid of the 6. That's not what we want to do. So before we shift the 5, we have to shift the 6 and then we shift the 5. In other words, we're going to take the 6, it's at index 1, but we're going to set it to be index 1 plus 1, meaning it's going to be at index 2. So the 6 is going to go there. The same thing with the 5. It's going to go at index 0 plus 1, which we know is 1, so it's going to go here. Only after we've performed this shifting are we allowed to put the 4 over here. There's space for it now, and we preserved the order of the values. The downside of this is we couldn't do it in a single operation. We had to move every value in the array. In this case, we only had 2 values in the array. But imagine if we had a really long array and it was all filled with some values, and we wanted to insert a value at the beginning, then we'd have to take all of these, shift them, and then we could insert the new value. This is not very efficient. That's what I'm getting at. We call this a big O of n operation. N in this case refers to a variable, and in this problem, n refers to the number of elements in the array. We can call that the length of the array. Length meaning the actual values we have, not the size of the array, but the number of values. And I've been using big O, but what it actually means is the worst case. Because this, what we just did right now, was the worst case. What we had to do is we had to shift every value in the array, which means n values, over to the right by 1, and then we were allowed to insert the new value. But if we were inserting in the middle between 5 and 6, let's say what we actually wanted to do was have a 5 and then a 4 and then a 6, then we wouldn't have had to shift the 5 at all. We would only have had to shift the 6. The 5 would have stayed over here on the left, and we would have inserted the 4 over here. So in that case, we would have only needed to shift one value, not every value in the array. But we don't want to go through every possible scenario, so we generalize it. We say in the worst case, if you're inserting a value in the middle of the array at any arbitrary position, in the worst case, we might have to shift every value. We might have to shift n values. So in the worst case, the time complexity is going to be big O of n. And the exact same thing is true if we're removing a value at any arbitrary index. When I say removing, I'm not just saying, replacing it with a 0 or something. I'm saying I want to pretend like this doesn't exist anymore. I want the first value to be 6. In that case, we would do something similar, but we would take the 6 and then shift it to the left by 1. So we would say 1 minus 1 is going to be 0. So we're going to put it at the 0th index. 7 is at index 2. We're going to take 2 minus 1, which is 1, and we're going to move this to that index. In the end, we're left with a 6, 7. Technically, the 7 from over here would still be there, or we could have replaced it with a 0, or we could, do something to pretend like it doesn't exist. But the memory that we actually allocated here definitely does exist, and it would be reflected in RAM. So to summarize the operations for a static array, reading or overriding the ith element of an array. Ith basically means any arbitrary element. You could pick any index and read or write from it. You can do that in big O of 1 time. You can do that in constant time. To insert a value at the end of the array or to remove the value at the end of the array is also a big O of 1 time operation. That's assuming that we have an empty space left at the end, or we at least have one element at the end for us to remove. Now, inserting into the middle of an array in the worst case is going to be big O of n. For an empty array to insert in the middle, it would be very efficient. It would be big O of 1. But we know we're talking about the worst case. That's what big O refers to. To insert in the middle would be big O of n. We might have to shift every value in the array. The same thing for removing in the middle. We might have to shift every value in the array. There's a common data structure in programming called a stack, which typically supports 3 operations. You can push an element to the end of the stack, you can pop an element from the end of the stack, or you can look at the last element in the stack. Meaning in this case, we just read the last element without removing it like we would in pop. These operations should run efficiently, so pushing should be a constant time operation, popping should be a constant time operation, and peeking at the last element should be a constant time operation. So do we need to design a data structure from scratch to be able to implement this? No, the dynamic arrays that we talked about earlier actually satisfy all of these requirements. So a stack can be implemented using a dynamic array. So typically when we're programming, we actually just use the default dynamic array that's given to us in the language that we're using. So remember, our stack is nothing but an array, and we're allowed to push elements. So we can push a 1 onto the stack, we can push a 2 onto the stack, and sometimes people like to think of stacks as being vertical. So when we say we're pushing onto the top of the stack, we're throwing a value in here and it gets thrown to wherever the top of the stack is. Since right now it's empty, it'll go to the bottom. Now in reality, we would have some kind of pointer, or we would maintain the number of elements that are added so far. So we would know exactly where to push the next element. Let's push a 2. It's going to go where the next empty spot is, which is now going to be shifted here. Same thing with the vertical representation. We push to the top of the stack, which is considered the end of the stack if you're talking about a regular array. And we can keep doing this. Let's push a 3. We can also now push a 4. Even though technically we don't have space, we know our stack is implemented with a dynamic array, so we don't even have to worry about running out of space. We know it's going to end up allocating some more space for us anyway, so we don't even worry about that. Stacks are just one common use case of dynamic arrays, but we can also support popping elements. So when we pop, we can only remove elements from the end of the array, but we know that's efficient. So we're, in this case, popping from the top of the stack or the end of the array. Internally, we wouldn't necessarily delete this portion of memory. We would just say that this is now the new end of our array, or this is the new top of our stack, and we can keep popping elements. Notice something about the way the elements are being inserted and removed. Remember, we first pushed a 1, and then we pushed a 2, and then we pushed a 3, and then we popped a 3, and then we popped a 2, and now we can pop one more element from our stack, which is the 1. So notice how the order that the elements were inserted in is the reverse of the order that the elements are removed in. In other words, the last element that was added to the stack is going to be the first element that's removed from the stack. The second to last element that was inserted is going to be the second to last that was removed if we pop all of the elements. So stacks are considered a LIFO data structure. That means that the last in is going to be the first out. There are many use cases for a data structure like this. The most obvious one is the one that we kind of implicitly just showed, meaning we had some sequence of values. In this case, it was numbers, but it could have been a string of characters like ABC, but the order that we added them in was the reverse of the order that we removed them in. So we could use a stack to reverse a sequence if we wanted to, even though there are other ways of doing the same thing. There are definitely a lot of other use cases for stacks that can get a lot more complex. And as you solve problems related to stacks, you'll definitely notice this. We will continue to talk about stacks throughout the course, but if you want to practice using this data structure, you can find some stack practice problems in the practice section. Now let's learn about linked lists, which have a lot of overlap with arrays, but also a lot of differences. The first thing to know about linked lists is that they are made up of list nodes, or sometimes just called nodes for short. A list node is an object that encapsulates two things at a minimum. These are the value of the list node. It could be an integer, a character, it could be another object, it could be anything. Maybe in this case, we have a 4 as the value. And also we have next, which is a pointer. This is going to tell us what is the next list node in the linked list. So this is essentially a way of connecting multiple list nodes together, which forms a linked list. If we just had a single list node, it wouldn't be very useful. In this case, let's say our next pointer points at null, which is another way of saying that it points at nothing. That means that in this case, we just have a single list node. That's not very interesting, so now let's understand how these nodes can be connected together. Let's first build a linked list. So first I'm going to create one list node. The value I'm going to give it in this case is going to be a string. Let's call it red. And the next pointer is initially going to be empty, or we could say it's by default set to null, so it's not pointing at anything. That means this list node is not connected to anybody yet. And we know when we create this object, it's going to go somewhere in memory. We don't necessarily get to control where it is, but we know it's going to be somewhere. We know that we're going to have a red node somewhere in memory, and it's not going to be pointing at any other node yet. Next, we'll create a couple more nodes, let's say a blue node and a green node. So now that we have 3 list nodes, it's time to actually connect them together. Now, in most languages, the next pointer is actually a reference to another list node. That's how it's implemented. So in terms of code, this is what we could do. We could set list node 1, assuming that's the name of our variable, our object that we created, dot next, the next pointer, to be list node 2. So what that would do is take this pointer and basically tell it that the next node in the list is going to be this node. Now, what's actually happening under the hood at the lowest level is we have some address for our second list node, our blue list node. Let's call it XX. And maybe this one is stored at address YY. The way we know how to get to the second node is at the lowest level, maybe your language or operating system is doing this. The pointer tells it that the address is here, so that's how we know how to get to the second node. But usually, depending on the language that you're using, you don't have to worry so much about the address because the reference to that object is enough. So when we talk about pointers, we're usually talking about references to objects. But I'm mentioning this because as you can see here, the nodes are out of order. in the way that we're going to connect them. We've connected our red node to our blue node, but the order in actual memory is the opposite. What this means is that linked lists are not stored in memory the same way that we use them as programmers. They could be in some random order in memory, but they're connected via pointers. So the red node is going to point at the blue node, and eventually we're going to have the blue node point at the green node. We could have some big mess like this in memory, but as programmers, we're going to have something nice and clean like this. So this is a difference from a linked lists compared to arrays. Arrays are stored the same way in memory, but linked lists, as we can see, are not necessarily stored the same in memory. Next, for us to connect list node 2 to list node 3, we would do the same thing we have down here, except for list node 2.next, we would have a 2 here, is going to be set to list node 3. So something like this. And then we would have a nice linked list finally formed like this. So now that we have an idea of how linked lists are stored in memory, we're not going to worry so much on the details of what's exactly going on under the hood. Now, what if we wanted to start at the beginning of our linked list and then loop through every single node until we got to the end? And we would know we got to the end, by the way, because our last pointer is not pointing at anything. Now, depending on the language that you're using, the code for that would look something like this, where first we have a variable called cur. We initialize it to be at the first node in the linked list. And we keep looping as long as our pointer current is not pointing at null. What that means is we have a valid linked list node. So let's walk through this code really quickly. Suppose this is our current pointer. It's pointing at the red node. That's how it's initialized. Then we go to the while loop statement. Right now it's not pointing at null. So then we're going to enter the while loop. Current is going to be set to next. So we're going to follow our next pointer over here, which is now going to be pointing at the next node. Very simple. Then we're going to go back to our conditional. Current is still not equal to null, so now let's set it to current.next. So we're going to follow the next pointer, which is now pointing at the green node. So this is where our current pointer is now going to be. We're going to again check the condition. It's still not equal to null. So now we're going to follow the next pointer again, which in this case, it is pointing at null. It's not pointing at any other node. So now our current pointer is going to be set to null, and then we're going to execute the conditional. And in this case, it's going to be false. So we're going to no longer execute the while loop, and we're done with that piece of code. Now, my question for you is, what would have happened instead if this next pointer of the third node was actually pointing at the first node? Well, we would have started here, then went to the blue node, then went to the green node, and then we would have came back to the red node, and then back to the blue node, back to the green node, and just kept doing that over and over again. It wouldn't be very fun to run because the program would crash. It's an infinite loop. But going back to the first case where we didn't have an infinite loop, what was the time complexity of going through the entire linked list? Well, it was the same as doing so with an array. It was big O of n, where n is the size of our linked list. So far, we've learned that linked lists are pretty similar to arrays. Let's talk about a few more similarities real quick. As programmers, it would probably be helpful if, as part of our implementation of the linked list, we're always keeping track of the head of the linked list and the tail of the linked list, or the end of it. So let's assume that we always have pointers that can give us access to the first element and the last element. If we have a linked list of size 1, suppose these didn't even exist, that means our tail pointer would be pointing at the same element as our head pointer. That's how we would know we only have a linked list of size 1. But in this case, we have a couple more nodes. Suppose we now wanted to add a new element to the end of the linked list. And let's say we create a new node and its value is purple. Well, if we want to insert it at the end conveniently, we have a tail pointer at the end of our current linked list, and all we need to do to add this to our linked list is just connect the pointer. So we would simply take the tail.next pointer and set it to list node 4, which is our purple node. So that would look something like taking this pointer and then instead connecting it to this one. But the problem here is that our tail is still pointing at the third node. We want to update our tail pointer now to actually be pointing at this one. And in terms of code, that's also pretty easy. We can set tail equal to list node 4. We could also have set tail equal to tail.next, because remember, tail is still pointing at the third node, and we know tail.next now is set to list node 4. So by setting tail equal to tail.next, we're automatically setting it to this node. Can you tell me the time complexity of this operation? Well, it was a constant time operation. Since we already had a tail pointer at the last node, we didn't have to iterate through every single element in the linked list. We started all the way at the end, and then we created a new node and then connected the pointers. It was just one operation that we needed to do, which is the exact same thing with an array. Now let's say instead we wanted to remove a node. Removing any node in a linked list, whether we're talking about the end of it or the beginning of it, is also always a constant time operation. But there's a really big caveat. That's assuming we have a pointer to the previous node that we're trying to remove. So if we're trying to remove this node, we should hopefully have a pointer to the previous node. So if we're removing this node, what we would do is set our head.next pointer. Instead of it pointing at the second node, we would set it to the next node that it's pointing to. So this is a little complicated because we're chaining the fields. Head.next, remember, refers to this node. This node is equal to head.next. And then if we say .next one more time, we're following this pointer to the third node. So what we know is this evaluates to the third node. So when we say head.next, which is this pointer, is pointing at the third node, we're basically getting rid of this guy and taking this and setting it to the third node. Now, if we want to, we can free the memory that this node was taking up, but in most languages we have garbage collection, so we don't really need to take care of that. The language and operating system will take care of that for us. We can assume that it no longer exists if there aren't any pointers pointing at it anymore. But this is sort of a benefit compared to arrays. We can remove any element from whether we're talking about the beginning or the end in constant time because we don't have to shift everything over like we did with an array. But in the general case, if we wanted to, let's say, delete an arbitrary element in the linked list, we would first have to start at the beginning of the linked list and then follow the pointers until we found the element and then remove it. So practically speaking, to remove an element, it can still take big O of n time if we have to search for the element. Now, so far we've talked about singly linked lists, but there's a slight variation called doubly linked lists, which can also be useful. The main difference, as the name implies, is that we have two pointers. We have double pointers. We have one pointer for the next node, the same for singly linked lists, but we also have a previous pointer, which is going to point at the previous node in the linked list. So with three nodes, 1, 2, and 3, the next pointers are going to be connected to the next node in the linked list. The previous pointers are going to be connected to the previous node in the linked list. Now the first node does not have any previous pointers, so it's going to be set to null, we can assume, the same way how the last node has a next pointer set to null. That's how we know we get to the end of the list, and this is how we know we've gotten to the beginning of the list. Now, just like with singly linked lists, Let's assume that we have a head and a tail pointer to the first and last node of our linked list. Now let's say we wanted to add a new node to the end of the linked list. It would be very similar to doing it with a singly linked list, meaning we would take the next pointer of our current tail node and assign it to the list node 4. We would also want to set the previous pointer of this node to be at list node 3. We would also want to set the previous pointer of list node 4 to point at list node 3, because we want to make sure that this is doubly linked. We want to preserve the properties of our doubly linked list. And then we would take our tail and shift it to the new node that we just inserted. This is how the code for that operation would look like. We would first say tail.next is equal to the new node that we're inserting. We're connecting the pointers, we're adding that node to our list. We're also connecting the previous pointer of that new node. The previous pointer should be set to the current tail. Remember, our tail pointer was originally pointing at node 3, so that's what our previous pointer is going to be set to. But finally, in the end, we take our tail pointer and set it to the next node, which is going to be list node 4 from the assignment we did right here. The one thing to note is the order that we do these operations in is very important. We have to do this operation before we update the tail pointer. So now let's look at removing a node. Let's remove the last node from our list, and it's a little bit easier with a doubly linked list because we're allowed to look backwards. Assuming we only have a pointer to the tail, that's actually all we need. We don't need a pointer to the previous node because from our tail, we can follow the previous pointer and it's going to take us to the previous node. This is really convenient. With a singly linked list, we would have had to start at the beginning and then kept going forward until we got to the node that we wanted to be at. We would start at the tail, follow the previous pointer, we would be at list node 2. We would take the next pointer of it, which is now pointing at list node 3, and we would instead point it at null. And it's really that simple. Now we have a linked list of size 2. Technically, this node still exists and its previous pointer is pointing here. But if we take our tail pointer and set it now to be here, as far as we're concerned, this node doesn't exist anymore. Technically it does, but we have no references to it, so we're never going to see it ever again. And depending on the language you're using, garbage collection might delete this automatically for us. And the code for that operation would look something like this, where we create a variable called node2 and we assign it to tail.previous, which is going to be here. We didn't originally have a pointer to this node, so we created one by taking tail and getting the previous pointer. Now we're taking the next pointer of this node and setting it to be null. It used to point at node 3, now it's not pointing at anything. That means that this is the new end of our linked list. So we should take the tail pointer and set it to node 2 as well. At this point, we have a doubly linked list of 2 nodes left. By the way, we did a few operations, but we didn't have to loop through the entire linked list. Regardless of the size of the linked list, this delete last operation is always going to be the same. It's going to be a constant time operation. So with doubly linked lists, we can insert a value at the end and we can remove a value at the end. So we can do both of those in constant time. Doesn't that satisfy the requirements of a stack data structure? Yes, it does. That means that stacks can be implemented also with linked lists, just like they can be with arrays. But it's a lot less common to implement stacks using linked lists because with our original dynamic array, we could pop and push to the end of the array efficiently, but we could also access any arbitrary element of the array. This is a downside of linked lists, whether we're talking about singly linked list or doubly linked list, because we can't just arbitrarily access the second element or the third element or the seventh element. We have to follow our pointers to do that. That means to access a random element of the linked list, it would be an O of n time operation. So if that's the case, it's probably better to use a dynamic array if we're talking about stacks, because we get extra functionality that we lose when we use linked lists. So let's wrap up by reviewing the time complexity of linked lists and compare that to arrays. So remember, accessing the ith element of an array, accessing any element at any arbitrary index, is a constant time operation with arrays. Inserting or removing at the end is also efficient. We can push and pop efficiently, but inserting into the middle or removing from the middle is going to be a linear time operation, because we might have to shift all of the elements over in either direction. Now, with a linked list that looks something like this, accessing any element in the linked list is not necessarily going to be efficient. I mean, of course, if we already have a pointer to this node, for example, it will be a constant time operation, but that's not always going to be the case. If we had a really big linked list and we wanted to access any element in the linked list, in the worst case, we would have to start at the beginning of the list and then keep incrementing, keep iterating through the list until we got to that element. So linked lists are different. We can't just randomly access any element. The worst case time complexity is big O of n. But if there's a downside to linked lists, we can also expect that there's going to be an upside to them as well, because that's the whole point of data structures. Some are better at certain things. Now, inserting and removing at the end is the same as arrays. It's a constant time operation. We talked about that earlier. Inserting and removing from the middle, though, is a constant time operation. Remember, if we have a linked list that looks something like this, if we want to remove the middle element, we don't have to now shift everything over. We don't have to take all of these and then shift them over by one. All we have to do to remove an element like this one is take the pointer. It's currently pointing at that, but now we want it to point at the next one. That's all we have to do to remove from the middle. Inserting works very similar to that. So yes, it's efficient to do that with linked lists, but the caveat, and it's a really big one, for us to remove any random element, first we have to arrive at that element. We need a pointer to the element before we can remove it. So in most cases, we're going to have to start at the beginning, keep iterating until we find the element that we want to remove, and then remove it. So while doing the insertion or removal is efficient, usually we have to iterate through the linked list before we can do that. So in most cases, it's going to be a linear time operation. So we can see that linked lists do have a slight benefit compared to arrays, but I'll be honest and say that arrays are much more common and much more useful for problem solving. Being able to access the ith element, any arbitrary element, very efficiently is really, really important, much more than something like this, especially when most of the time we do this, we're not actually going to be able to do it in constant time. We're going to have to iterate through the linked list. These are a couple very fundamental data structures, and I can't wait to show you even more. Next, let's talk about queues. Queues are another important data structure similar to stacks. The difference is queues follow FIFO, which means first in, first out. They support two operations, typically enqueue and dequeue, but different from a stack. When we enqueue elements, it's the same as pushing. So in this case, it's actually similar to a stack. When we push elements to the end of the queue. That's called enqueuing. Now, dequeuing is removing a value, but instead of removing from the end, we're actually going to remove from the beginning. That's why it's first in, first out. The first element that we add is going to be the first element that we remove. Elements are going to be removed in the same order that they were added to the queue. And we want to do these operations efficiently. We want to be able to add to the end of the queue in constant time and remove from the beginning of the queue in constant time. We know we couldn't do that with arrays because if you remove from the beginning of the array, then you have to take every other element and then shift it over. That turned out to be a big O of n time operation. But with linked lists, we can achieve this. Let me show you how. So suppose initially we have an empty queue. So we'll have a current pointer which is initially set to null, it has nothing. And then we add a value to our queue, let's say we add red to our queue, then we create a list node and then our current pointer is going to be set to that list node because now we have one element in our queue. By the way, with this linked list, we will be maintaining a head and a tail pointer, which both are initially going to be at this node as of now. But we want to add another value to our queue. So we add another, in this case, blue to our queue. It's as simple as taking the next pointer of this node and setting it to the new node that we're inserting. At this point, our head pointer will be pointing at the first element here, and our tail pointer will be pointing at this, which is our tail. That's how we know when we insert a new element like this one, we're going to take the next pointer of the tail node and then set it to the new node. This is really easy with linked lists, but now it's time to do the other operation, which is dequeue, remove from the head of the list. Well, the good thing is it's as easy as taking our current pointer and setting it to be current.next. Since our current pointer is at this node, .next will follow the next pointer, which will be here. So it's as easy as that to take our current pointer and then point it to this node. And then if this is the beginning of our linked list, we can pretend like this doesn't even exist anymore. So dequeuing an element is very efficient. That's how we can do it in constant time, which you can't really do with arrays. But I do want to mention that technically it is possible to implement queues with arrays, but it can get a lot more complicated. It's much more simple to implement them with linked lists. Queues are a very commonly used data structure and we'll continue to use them throughout this course. Recursion is a very important concept for data structures and algorithms, and we'll be using it throughout the rest of this course. It can be pretty difficult to wrap your head around, so I think it's best to introduce this topic as soon as possible. We're going to start with what I call one-branch recursion, and we're going to do so using a math formula, specifically n factorial. If you're not familiar with it, n factorial is a shorthand of writing n times n minus 1 times n minus 2 all the way until we get to the base number, which is 1. So for example, to say 5 factorial would be to say 5 times n minus 1, so 5 minus 1, which is 4, and then n minus 2, which is 3, and then keep decrementing the number by 1 until we get to the base number, which is 1. And then, we do this calculation, it turns out to be 120. Now you definitely don't need recursion to do this calculation. The easiest way to do it would be with a loop, where we take this number and then decrement it by 1 and multiply it by the result until we get all the way down to 1. But we can also do this with recursion, and I think it's a good way to get introduced to recursion. Notice how 5 factorial is the same as 5 times 4 factorial, because we know 4 factorial is going to be 4 times 3 times 2 times 1, and we see that repeated over here. So another way of representing 5 factorial is to say 5 factorial is equal to 5 times 4 factorial, or the general equation, which we've written up above, would be to say n factorial is equal to n times n minus 1 factorial. The reason it's important to understand it in this way is because recursion is all about subproblems. We can see that it's not super simple to calculate n factorial, but we know it's going to be n multiplied by n minus 1 factorial. So we took a big problem and made it a slightly smaller problem. We call this the subproblem, and this is why we're allowed to use recursion for this problem, because we have a subproblem. Now I could show you what the code would look like to solve this recursively, and it's actually very short, but I think it's better to start with a visualization and then move to the code, which makes it easier. So suppose we're trying to compute 5 factorial. We know that the subproblem is 4 factorial n minus 1, right? So we take 5 minus 1 and we want to compute 4 factorial first. So suppose we want to compute 5 factorial. We know that the subproblem we have to compute first is 4 factorial, and then we can multiply that by n, which in this case is 5. By far the best way to represent recursion is using a decision tree. In this case, we only have one decision. That's why I call this one branch recursion. But a tree is still helpful to visualize this. So before we can compute this, we have to compute 4 factorial. So in terms of code, this step would look something like this, where we have a function called factorial. It's going to take in some integer where we're going to compute the factorial of that, and then we're going to return the result, which is also an integer. Now, so far we know that to compute n factorial, we have to solve the subproblem, which is n minus 1 factorial. So we call the function that we're inside of, we call our own function. We call the same function. This is called the recursive step. But this isn't all we need. That's why I've left a little space over here. So let's continue with this and see what happens as we continue to solve the subproblem. So we have 4 factorial. Well, again, we know that's equivalent to 4 times 4 minus 1 factorial. So we want to compute the subproblem 3 factorial before we have 4 factorial. But the same applies for 3 factorial. It's equivalent to 3 times 3 minus 1 factorial, which is 2 factorial. So let's compute that. And again, same applies to 2. It's equivalent to 2 times 2 minus 1 factorial, which is 1 factorial. Now this is where we get to something different. Once we get to a 1, that's the base of our series. That's the last term of the multiplication. So when we get to 1 factorial, that's equivalent to 1. So that's what we call our base case. That means that for 1 factorial, we're not going to use this formula because we assume that 1 factorial is mapped to a constant, which is 1. So we don't have to do this calculation because it would result in 1 times 1 minus 1 factorial, which is 0 factorial, which in math is valid. 0 factorial would also map to 1, but that's not so important for our case here. What's important here is that 1 factorial is when we can stop. So in terms of code, that would look something like this. If n is less than or equal to 1, we can return 1. The reason I say less than or equal is because of that 0 case. If we were given 0 as our original input, we would want to return 1. That's just the definition in math. But you can see this is very important because if we don't have this, we would continue this infinitely. We would continue to call the same function that we're inside of. It would never stop, and we would never go back up to compute our original result, which we were trying to do was compute 5 factorial. We would never go back here. We would just keep going down and keep getting more negative and negative and negative. So how is this actually going to run? Well, let's say we were given 5 as the input. 5 is not less than or equal to 1, so we say that we're going to return 5 times 4 factorial. So that's how we go down here. We're going to go down a step to here. And then for 4, we're going to see the same thing. It's not less than or equal to 1, so we're going to compute 3 factorial. So we're going to keep going down and down and down until we get to 1 here. So that's going to be our base case. That's when this is actually going to execute. We're going to end up returning 1. So we're going to go back up to our parent and have a 1 that we're returning. So at that point, this code is going to execute. We passed in 2 minus 1 factorial here. This return call evaluated to 1, and currently n is 2, so this is going to be 2 times 1, and then from here we're going to end up returning 2. So from here we pop back to the parent and return 2. So then this line is going to execute because what we passed into here was 3 minus 1, which was 2 factorial. We know 2 factorial now is equal to 2. That was the return value of this. So then we're going to call 3 times 2 and then return that. That's 6. So now it's starting to get a little interesting. We're going to return 6. From this line, we're going to return 6 back up to the previous call. So this, which was 4 minus 1, which was 3, 3 factorial is 6, multiplied by n, which in this case is 4. So 4 times 6 is going to be 24. We're going to return 24 up to the previous call. And then we'll know that 4 factorial was 24. N in this case is 5. So 5 times 24 is 120. That's going to be the result of the call, which is 5 factorial. So when we called factorial and passed in 5, this is going to be the result. N is 5, so 5 times 24 is 120. That's going to be our result. So when it comes to analyzing the time complexity, it can be difficult to determine just by looking at the code. That's why drawing a picture like this can be helpful. You can see that to compute n factorial, we basically have n steps. We have n calculations that we have to do, n multiplications rather. So to compute this, the time complexity is big O of n, where n is of course the input that we're given. This is the same as it would be if we used a while loop or a for loop, where we start with n and we decrement it by 1 each time to get this computation. So there's definitely no benefit in this case of actually using recursion. I'm mainly doing this to teach you, and actually in this case the recursive solution is actually worse than doing it with a while loop, because in this case we end up needing extra memory. This solution actually has big O of n memory complexity. We care about time complexity, but we also care about memory complexity. We'd rather not allocate additional variables that take up extra memory if we don't need to. Now in this case, we're not even allocating any major variables. We don't have any arrays or linked lists or anything like that. So why is this taking up O of n memory? The way this code is going to run is similar to how I've drawn this picture. We're going to have a function that's computing this. That function is going to take up space in memory, and we're going to save that. We're going to put that function on hold, and we're going to say, okay, stay right there. First, we have to compute 4 factorial, and then we're going to keep this in memory as well. We're going to save our spot here, and we're going to say before that compute 3 factorial, before that compute 2 factorial, before that compute 1 factorial. At the point where we're here, where we're calculating 1 factorial, we're going to have all 5 of these functions taking up memory. Now each function doesn't really declare any major variables, but each function is going to have its own input parameter. So you can think of the function declaring 1 variable at the very least. And the function itself actually takes up a little bit of memory so that it knows when this function is done, return back up to the parent. But that's getting a little too into the details. The important thing here is that we have n function calls that are all going to be alive at the same time, so this takes O of n memory. And by the way, the non-recursive solution would look something like this, where we just have a single variable. Let's call it our result or our factorial. It can be initialized to 1 because we know that's going to be the base case anyway. I don't think negative factorials are something that we actually have to consider. So we're going to assume that n is always greater than or equal to 1. And then while n is greater than 1, we would multiply the result by the value, so n, and then decrement it by 1. So then we would get, n minus 1, n minus 2 until n is equal to 1, and then we would stop. Now let's look at the more interesting case of two-branch recursion. And let's use another math example. In this case, let's calculate the Fibonacci numbers. Now the general formula to calculate the nth Fibonacci number is to take the n minus 1 Fibonacci number and the n minus 2 Fibonacci number and add them together, which gives us the nth Fibonacci number. But if we do it like this, we're going to go on forever if we try to calculate the 5th Fibonacci number, because when do we know we can stop? Well, we do have some base cases for us defined. The 0th Fibonacci number is 0. The first Fibonacci number is 1. So using this, what would the second Fibonacci number be? Well, it would be the n minus 1 Fibonacci number, which is 1, plus the n minus 2 Fibonacci number, which is 0. And we know that these are defined as a part of our base case. This is 1, so 1. This is 0, so plus 0. That means the second Fibonacci number is equal to 1. So now we have that. Then we can compute the third Fibonacci number, which we know is going to be n minus 1. That's 2 plus n minus 2. That's going to be the first Fibonacci number. So now we have the second Fibonacci number, which is 1. We have the first Fibonacci number, which is also 1. So this is equal to 1 plus 1. So therefore, the third Fibonacci number is 2. Now, the way I'm calculating it right now is very straightforward. I'm pretty much looping through these, and we could go as high as we want. We could now calculate the fourth, the fifth, the sixth Fibonacci number. But this is not recursion. The recursive solution for this problem is actually less efficient, but I still want to show it to you because it illustrates for us two-branch recursion. So let's say we want to calculate the fifth Fibonacci number. This is where our decision tree is going to get very useful. Maybe we can't immediately compute this, but we know this can be broken up into a couple sub-problems like n minus 1 and n minus 2. So to compute the fifth Fibonacci number, we can compute the n minus 1, which is 4, and n minus 2, which is 3. But for either of these branches, we still haven't reached the base case yet, which we know is 0 or 1. So let's continue down the left path. This can also be broken up into a couple sub-problems. Again, n minus 1 and n minus 2. So n minus 1 would be 3. N minus 2 would be the second Fibonacci number. For this, it's going to be n minus 1, which is the second Fibonacci number, and n minus 2, which is the first Fibonacci number. Now let's continue to draw this out. So the third Fibonacci number can be broken up into n minus 1, which is the second Fibonacci number, added with the first Fibonacci number. To get the second Fibonacci number, we can get the first Fibonacci number added with the 0th Fibonacci number. It's starting to get a little bit messy, but we're almost done. So over here, the second Fibonacci number, which we sort of just did over here, is also going to have two steps, which is the first Fibonacci number added with the 0th Fibonacci number. Now over here, do we also need to break this up into subproblems? No, because we finally reached our base case over here. So now to take a quick preview at the code, the base case we know is going to be either 0 or 1. So we could have an individual case for each of these. We could say if n, the input, is 0, then return 0, and if it's equal to 1, return 1. But we can condense that into a single if statement. If n is less than or equal to 1, that means if it's either 0 or 1, then return n, because when n is equal to 1, we're returning 1. When it's equal to 0, we're returning 0. So whatever it is, that's what we can return when it's less than or equal to 1. But for the recursive case, as we've been doing, we know we have to compute the n minus 1 and the n minus 2 Fibonacci number, and then when we have those, we're finally going to add them up and then return that integer value. But we're not quite done yet. We know that this here, the first Fibonacci number, it is 1. So that's what I'm going to put here. And actually, we've reached the base case with all of these, but there's just one branch left for us. So let's quickly complete that one, and then we can compute the result. So the second Fibonacci number we know is n minus 1, which is 1, plus n minus 2, which is 0 in this case. So adding these together will give us the second Fibonacci number. So now going down this path, let's say, for n minus 1, we're going to end up returning 1 in our code over here. For 0, we're going to end up returning 0. And then we're going to be back up here in our decision tree. For this, the code we're going to be at is this return code. We've computed n minus 1, which turned out to be 1. We computed n minus 2, which turned out to be 0. Now we're adding them together, 1 plus 0. So we're going to end up returning 1 from here. And this was also a base case. So recursively here, we would have executed this line of code and we would have ended up returning 1. You can see that it might not be easy to know what's going on just by looking at the code, especially when you get to two-branch recursion and beyond that. That's why we draw out these decision trees, which make it relatively simple. So we know to compute the third Fibonacci number over here, we get the results of the two paths. We were first computing the second Fibonacci number, which turned out to be 1, and the first Fibonacci number, which turned out to be 1 as well. We add those together. So we add the return values from here, and then we return 2 from here. So now we're trying to compute the fourth Fibonacci number. First, we needed to compute the third Fibonacci number to do that. We did that here. Now we need to get the second Fibonacci number. And to get this, we get its subproblems, the first and the 0th Fibonacci number, which both are, well, this is 1, and then the 0th is 0. We add those together. That's going to be 1. So from here, we return 1. So to get the fourth Fibonacci number, we have 2, which is the third Fibonacci number, and 1, which is the second Fibonacci number. We add those together and we return 3. Now at this point, you're probably starting to get the idea. So finally, to get our original result, which is the fifth Fibonacci number, we needed to compute the fourth Fibonacci number. We did that. We have 3. And now we need to compute the third Fibonacci number. And to do that, we need to get the second and the first Fibonacci number. And to get the second Fibonacci number, we need to get the first and the 0th, which are going to be 1 and 0. Add those together. We get 1 as the second Fibonacci number. Add this and this together. We get 2 as the third Fibonacci number. And then add this and this. We get 5 to be the fifth Fibonacci number. It's gotten very messy here, but we did finally get our result. And again, this is definitely not the most efficient way to solve this problem. Earlier, we were doing it with a loop. So to get the nth Fibonacci number with the loop technique I was talking about, the time complexity would be big O of n. But here we've drawn it out recursively, and clearly this is not big O of n. So to analyze the time complexity of this recursive solution, looking at the code is not going to help us a ton. The picture is a lot easier to use, but it's going to require a bit of math. First, to get the fifth Fibonacci number, or just some general nth Fibonacci number, we have to break that up into 2 subproblems, right? And then those 2 subproblems have to be broken up into 2 more subproblems each. And then those subproblems might need to be broken up into 2 more subproblems, unless of course we've reached the base case, which for this one we have reached the base case. But in general, for each of these we might have to break it up into 2 more subproblems. Now the fact that we have to break it up into 2 subproblems comes from the fact that we have 2 branches in our recursive tree. But in this recursive tree, how many times are we going to have to break it up into 2 steps? In other words, what is the height of this decision tree going to be? The height is basically how many levels does this tree have. You can see 1, 2, 3, 4, 5 levels. That makes sense because for the path where we have 5, then we have 4, and then to get that we have to go to 3, then to 2, and then to 1. That's what's the longest path is going to be. So the number of layers in this decision tree is going to be n, where that's the nth Fibonacci that we're trying to compute. Now this is the part where I could get overly technical if I wanted to, but I want to try to keep it simple in terms of math. So in general for this, for us to get the number of Fibonacci values in the last level, theoretically with math, it would be we start with 1 and then we double every time. So it would in theory be 2 times 2 times 2, and the number of terms that we would have is equal to n. Roughly speaking, it's equal to n because that's the height of the tree, right? If we're taking this and then doubling it and then doubling it, the number of times we double it is going to be n, and that's the same as the input value. So to get the number of values in the last level is going to be roughly, let's say, 2 to the power of n. Now in this case, we can see that the last level only has 2. So in reality, this is actually an upper bound for the number of values we could have in the last level. It's not the precise value, it's an upper bound. But what we know about this last level is the same thing we talked about earlier in math. When you have a series like 1 and then 2 and then 4 and then 8 where you're doubling it every time, this is special in math. It's called the power series. It's always dominated by the last term. So 8 is going to be greater than or equal to all the previous ones combined. If we add a value 16, it's going to be greater than or equal to all the previous combined. So what I'm saying here is that this is an upper bound for the last level. That means it's also an upper bound for the total number of values in this decision tree. If you don't believe me, well, Remember, we can multiply this by any constant. So we say, let's say our constant is 2. So 2 times 2 to the power of n is still, in terms of big O time complexity, equivalent to 2 to the power of n in terms of big O time complexity. Precisely, though, it would be n plus 1. But remember, we don't care about constants when they're multiplying or adding to variables. So 2 to the n plus 1 is equivalent to 2 to the n minus 1 as well, right? In terms of big O time complexity, all three of these are equivalent. So this is essentially a long explanation for saying that 2 to the power of n is how we can bound this in terms of big O time complexity. Even though this isn't the precise number of values in this decision tree that we drew, it's still a very good upper bound, because remember, we don't care about constants like +1 or -1. And this idea of 2 to the power of n is something we're going to continue to see throughout the course. It all comes from that idea of math, from that idea of power series. 2 turns out to be a very special number for computer science and math. Next, let's move on to a very fundamental topic, which is sorting. And we're going to start with the insertion sort algorithm. Sorting is used all the time, and there's a ton of different sorting algorithms, all with their own trade-offs. It's usually applied to arrays like this one, but you can also apply it to other data structures, including linked lists and others. So in this case, we have an array of 5 values, and clearly they're not in order. They're not in ascending order, which would be in increasing order, like 1, 2, 3, but they're also not in decreasing order, which in this case would be 6, 4, 3, etc. Suppose we want to sort them such that they are in ascending order. So our target array would look something like this, 1, 2, 3, 4, 6. We can achieve this with the insertion sort algorithm. Let's see how we can do it. Well, the main idea is to break the problem into subproblems again. So if we want to sort the entire array, the first thing would be to have the first portion of the array, meaning just the first element, have this sorted. Well, one value, like 2, is sorted by default. I mean, how could this be not sorted if it's just one value? So we consider any array of one value to be sorted. The next thing to do, the next subproblem, would be to sort the first 2 values, make sure these are sorted, and then have the first 3 values sorted, and then have the first 4 values sorted, and keep doing that until we have the entire array sorted. So thinking of it this way in terms of subproblems makes the algorithm a lot more simple. Now, since we are doing it with subproblems, technically if we wanted to, we actually could solve this using recursion, which is a technique we just learned, but it's not really useful in this case, so I won't do it. We can do this without recursion, aka we can do this iteratively. We can have an iterative solution, which is using loops. Now the idea is we're going to loop through the array, but we're going to start at the second element because we know that this subarray is already sorted. So starting here and assuming that every value before this position, meaning this subarray, is already in sorted order, our goal now is to have this array be sorted. So our goal really is to figure out where to put this value. We already know all of these are sorted. Where should we put this one in terms of this array? In this case, we don't have a lot of choices. The logical thing to do is compare this value to the only other value in our array. Is this larger? If this is larger, then it should stay where it is. If it's smaller, it should be swapped with the value over here. Since this is larger, it can stay here. Now there's the other edge case where what if both of these are equal? If that's the case, this value can also stay here because it doesn't matter whether this goes here or here if they are both equal because it'll be sorted either way. This is for ascending order, but it would work the same way with descending order as well. So now that we know where this value should go, it should stay where it is, we can now move to the next value. So by the time we get here, we know that this subarray is already sorted. So at this point, we're going to do a similar comparison. We're going to compare this to its left neighbor. Is 4 greater than 3? Yes, it is. So it's going to stay exactly where it is. And at this point, we didn't even compare 4 to 2, but we don't need to. Do you know the reason why? Well, we already know these were in sorted order. So if 4 is greater than 3, of course it's going to be greater than every value to the left of 3 because these are sorted. Every value to the left of 3 is going to be less than or equal to 3. And now every value to the left of 4 is going to be less than or equal to 4. So at this point, we know that these values are in sorted order. We can shift our pointer to the right by 1 over here. And now things are going to get a little bit interesting. So now we have this sorted portion and we have to figure out where the 1 should go. Should it go at the end of these 3 values? Should it go in between these 2 values? Should it go in between these 2 values? Or should it go over here? Well, let's see what the algorithm does. This is why it's called insertion sort, because we're taking one value and inserting it into a sorted array. So let's see what the algorithm does in this case. First, we're going to compare 1 to 4. Is 1 greater than or equal to 4? It's not. So now we finally execute the other case. And by the way, the pseudocode for this would look something like this. Remember our pointer, which is I, in this case, started at index 1, and we're going to keep going until we've reached, the end of the list. So that's pretty straightforward. And now we're going to get to the interesting part where we compare this to the neighbor. So we have a second pointer for the neighbor. We call that J. This is at I, or you could also call this J plus 1. That's what we're going to be doing. And then you compare these. And now the value at j plus 1 is less than the value at j. That's this part of the code. This part is basically to make sure that we don't go out of bounds. And you'll see what I mean in just a second. But now that this comparison holds, we're going to perform the swap. This is where we take this value and move it over here and take this value and move it over there. So the first thing we would do actually is take the value that was originally at j plus 1, which is 1, and put it in a temporary variable, because what we're going to do is now at this index j plus 1, we're going to move the value that was here. So we're going to put a 4 over here. And then over here, now that we've lost the 1, we have to use our temporary variable. So we're going to put a 1 over here from our temporary variable. And originally our j pointer was over here. We're going to decrement it by 1, which means we're going to shift it to the left by 1 over here. And the reason this is a while loop and not just an if statement is because now we're going to continue this whole process. We originally had the 1 over here, and we know it should be shifted to the left because it's definitely less than 4, but we don't know that we're done. We don't know that this is the final spot that this 1 is going to be. We have to continue comparing to the left neighbors. So now we're going to execute the condition again. First, we're going to make sure that j is not out of bounds yet, because as we keep shifting it, we know at some point it's going to be all the way over here. It could be out of bounds, but right now it's not out of bounds. We know that because it is greater than or equal to 0. And now we're going to compare the value at j plus 1 to j. J plus 1 is less than the value at j. 1 is less than 3. So now we're going to do the exact same thing. We're going to perform the exact same swap. So now we have our 3 over here and our 1 over here, but we're not done yet. We're going to decrement our j one more time. So now j is going to be over here. It's still in bounds. And the value at j plus 1 is again less than the value at j. So now we're going to do another swap. So the 2 is over here and the 1 is going to be over here. And now j is going to be shifted to the left by 1 again. Now it's out of bounds. So now there's no point in even doing a comparison. That's why we're checking that it's in bounds before we do this. We don't want an index out of bounds error. So since it's not in bounds, we can stop doing this loop. And we know now that our I pointer, by the way, was over here. So now at this point, our I pointer is going to be shifted over here because we're going to execute the next part of the for loop, the outer loop that's over here. And we know because of that, this portion of the array, these first 4 values are now in sorted order, and they look sorted as well. 1, 2, 3, 4. So now that our I pointer is over here, our j pointer is going to be initially over here. J is in bounds. So now let's compare the two values. Is 6 less than 4? It's not. So we know that this is greater than 4, therefore it's going to be greater than all of these as well. So that means that this is already in sorted order. Our outer for loop is now going to stop because there's no more elements over here, left for us to traverse. Now we've been talking about sorting integers so far, but of course this could be applied to characters. If we had something like B, C, A, as long as we have a way to compare characters, so in this case, let's say we're sorting based on just alphabetical order, we can basically sort any set of values as long as we have a way of comparing two values together. So in this case, we could sort these to be something like ABC. Of course, we could also sort strings themselves the same way a dictionary sorts words. So a word like apple would go before a word like banana. With sorting, there's also this notion of stable versus unstable sorting. Let's say we had this array of values, 7, 3, 7. Any sorting algorithm is going to take these values and put them in sorted order, which would be 3, 7, 7. Any sorting algorithm could do that, but the difference between a stable sorting algorithm and an unstable sorting algorithm is this. This is what a stable sorting algorithm would do. It would put the numbers something like this. The thing to notice here is that for 7, it appears twice in the array. So this first 7 could have gone here, and then the second 7 would have gone here. Or they could have been in reverse, right? This 7 could have gone first, and then this 7 would have gone second. Both of those are valid sorting order, but a stable sorting algorithm will preserve the original order when there's a tie. We know that there's 2 7s. And for some reason, if we wanted the original relative order of these 2 7s to be preserved, meaning this one showed up first before this one, so it should go first in sorted order. That's called stable sorting. Unstable sorting might achieve this, but there's no guarantee. It's not necessary that that will be preserved, so it could have flipped them for some reason. We'll touch on this again as we continue. But my question for you, based on this, do you think the insertion sort algorithm is stable or is it unstable? Well, let's quickly go through how it would execute on this. First, our pointer would be over here. We would compare the 3 and the 7. They're out of order, so we would swap them. So then our first 2 values would look like this. So that's good so far. And then our third pointer would be over here, right? And this would be a 3 and this would be a 7. And we would say, this 7, is it less than the 7 on the left of it, right? That's where this would execute. This 7 is not less than that, so it's going to stay exactly where it is. So therefore, we would achieve this output where the relative order in case of a tie would be preserved. These two would stay in the order they were in originally. So based on this implementation, this is a stable sorting algorithm. It's preferred to keep an algorithm stable if you can. We could code this in such a way where it's not stable, but that would have no benefit for us. So we're going to keep it as stable. So now finally, let's talk about the time complexity, which is interesting for insertion sort actually. And the best way to actually understand it is to look at a couple examples. Let's say we were running insertion sort on a list that's already sorted. What would the algorithm do? Well, we would have a pointer over here. We would want to, of course, iterate through the array, but then we would do a comparison. From here, we would compare it to the left neighbor. They're already in sorted order, so we don't have to do anything. We can shift our pointer over here. We compare these two values. They're already sorted. We don't have to do anything. We shift the pointer again. Then we compare these two values. They're already sorted. We don't do anything. We shift the pointer. We're out of bounds. That means we're done. So as you can see, when we have an array that's already sorted, we run insertion sort, and the execution is just iterating through the list, which is big O of n time complexity. Of course, we have nested loops here, but just because we have a loop here doesn't mean it's necessarily going to execute. I just showed you an example where this inner loop is never going to execute. So in this case, the best case time complexity is big O of n. Now technically big O means worst case, so I'm kind of misusing it here, but it's kind of common for people to talk about it this way. But in this case, I'm saying the best case time complexity, which would occur when the input is already sorted, is going to be linear time complexity. Let's look at the other case, where is the worst case time complexity, which would actually occur on the opposite example, where the input is in reverse order and we want to sort it in ascending order. So in this case, again, we would loop through the array. We would start here. We would compare the two neighboring values. We would see that they're out of order, so then we would have to swap them. We would put the 3 over here and the 4 over here. Then we would shift our pointer over here, and then we would compare these two values, and then we would see they're out of order. We'd have to swap them again. We would have to put the 2 over here and the 4 over here. And at this point, we're still not done yet. This 2 is going to be compared to its left neighbor now, and they're again out of order, so we would have to put the 3 over here and the 2 over here. So you can see it's definitely getting messy, but ultimately what we would find is we would have to take this 3, shift it over here. Then we would get our pointer over here, this 2, we would have to shift it here, and then we would have to shift it here. Then when we get to this 1, we would have to shift it to the left, then shift it to the left again, and then shift it to the left again. So for every single value that we iterate through, the inner while loop would have to execute the maximum number of times until that value is shifted all the way to the left. When we get to the 2, we'd have to shift it all the way to the left. When we get to the 1, we'd have to shift it all the way to the left. Now for an input size of 4 in this case, n squared time complexity would look like 4 squared, because the length is 4, which would be something like 4 plus 4, right? Added together, how many times? Well, 4 times. That's just the math formula here. But this isn't that. What we were doing right now was actually a bit different. What we actually have is something like 1, and then plus 2, and then plus 3, and then plus 4, because for this value, we might have to, consider it to be in these 2 positions. For this value, it could be in these 3 positions. For this value, it could be in these 4 positions, which correlates to that 4. And I just talked about the 2 and 3 case. And we might not have a 1 case, because remember, we're skipping the first index. But again, this is just an approximation. And that's enough for us when we're doing big O time complexity. Now, what most people do when they have nested loops, they automatically assume that the time complexity is big O of n squared. And usually it's the correct assumption, but I bet most people don't know why that's the case. And I'm going to explain it to you briefly right now. This equation is bounded by n squared. It's pretty obvious when you look at it like this, because every term here is greater than or equal to every term here. But I'm going to show it to you in terms of big O time complexity, where remember, we know that constants don't matter when we're multiplying by a variable, right? So some constant c times n squared doesn't matter regardless of what the constant is. I'm going to use this idea to prove it to you that this is bounded by n squared, and I'm not even going to use a math proof. Now, maybe I'm not smart enough to show you the math proof of why this is true, but I'm smart enough to draw a picture, and that turns out to be enough. We know that n squared, where n is 4, would look something like this in terms of geometry, right? 4 times 4, right? This is us having to iterate through an array of size 4 times. We have to do that. We have to iterate through it once, twice, 3 times, 4 times. But we also have the case where we iterate through just, let's say, the first value of the array, and then the first 2 values of the array, and then the first 3 values of the array, and then the first 4 values of the array. So maybe now it's becoming a little more obvious why this is bounded by this. And not only that, this is actually pretty much exactly half the size of n squared. And we even talked about how the first term in this case doesn't actually apply. So maybe this isn't even there, but it's still, you can see, approximately half the size of n squared. We didn't even use a math proof to figure this out. This is obvious enough from looking at a picture. So if this is half the size of n squared, we can write it as n squared divided by 2, or in other words, 1/2 times n squared. And this is just a constant, remember, and we don't care about constants. So we can say this, or in other words, iterating through an array like this would be the same as big O of n squared time complexity. That's the worst case time complexity of insertion sort. So that was a lot to cover, but to finally wrap up our first sorting algorithm, insertion sort, which is a stable sorting algorithm, has a worst case runtime of n squared, but it's also worth mentioning that the best case runtime is big O of n. That's not always true for other sorting algorithms, but it does turn out that there's better sorting algorithms than n squared worst time complexity. Merge sort is one of the most common sorting algorithms, and for good reason. It's a pretty efficient algorithm. The main idea is to take the input array and then split it into 2 approximately equal halves. And then for those halves, split them into approximately equal halves, and then continue to split each subarray until we can't split them anymore, which would mean we have individual elements left for us to then sort. The idea is to break up the original problem of sorting the entire array into subproblems. So in order for us to sort the entire array, first we can sort the first 3 values, 3, 2, 4. So we can sort the first half of the values. In this case, we have an odd number of values, so we can't split it exactly into half, but more or less it's approximately half. And then the second half of values, we want to sort these as well. But then for these subarrays, we also have subproblems. We can split this array into half, the first half and the second half, and sort those portions of the array before we sort this original array. And the same thing for here. You can see that since we have a natural way of splitting this into subproblems, until of course we reach the base case where we just have subarrays of a single element, like down here as well, this problem naturally lends itself to recursion. I promised you that recursion was going to come up a lot more, and this is one of those cases. And this is clearly 2-branch recursion because we're splitting this into 2 halves. And I'll talk later why exactly we're splitting it into halves. But to give you a hint, as you know, the number 2 is pretty important. And as we take the array and divide it by 2 each time, that lends itself to be an efficient algorithm. We'll talk about that more a little later. But this array as well is being split into 2 halves, 2 branches. This array, same thing. But these are the base cases. Now we talked about how we're going to divide this into subproblems. By the way, the technique we're using right now is sometimes called divide and conquer, because we're taking the original problem and dividing it into subproblems and then solving those subproblems before we solve the original problem. But I haven't talked about how we're even going to solve these subproblems and what we're going to do once we have that done. Well, let's start on the left side. We're going to first take this array, get the left half of it. We're going to take that and get the left half of that. And then we're going to take this and then split it into 2 individual elements, 3 and 2. Now this is technically a sorted array, and this is technically a sorted array. When you have 2 sorted arrays, we can merge these 2 arrays back into the original array such that they are in sorted order. That's why this is called merge sort, because we break it up into 2 subproblems and then merge them back together. So for getting the original values that were in the array, we create a copy of the value that was here, and we create a copy of the value that was here. And in this case, it's pretty simple because we just have 2 elements. So we're going to compare these 2. Which one is smaller? 2 is smaller. So the 2 is going to go over here, and the 3 is going to go over here. Now from the perspective of this array, we've solved the left subproblem. We have this portion sorted. Now we need this portion sorted. Well, it's just a single element, so this is the base case. So now we don't care about the original values that were over here. We have two sorted arrays and we want to merge them together into the original array. In general, the algorithm is going to be two pointers for us to do that. We're going to start at the beginning of this array and we're going to start at the beginning of this array, and we're going to compare the values because we know at the beginning of each array is going to be the smallest value because this is sorted and this is sorted. So we're going to compare the two values. Which one is smaller? 2 is smaller than 4. So 2 is going to go over here. The pointer that was over here is now going to be shifted to be over here. And now we're going to continue the algorithm. We're going to compare the value here to the value here. Which one is smaller? 3 is smaller. So the next value that we insert is going to be 3 in the next position of this array. And at this point, our pointer that was in the first array is now going to be out of bounds. So at this point, we have no choice but to place the value from the second array in the next spot, which is also the last spot. So we put the 4 over here. So now we finally arrive back at the original problem we were trying to solve. We sorted the left half of the array. Now it's time for us to sort the right half. So then we have this portion. We break it up into individual elements. We don't care about what's originally here. We compare these two values. Which one is smaller? 1 is smaller than 6, so we put a 1 here. That is what the original value actually was, and we put the 6 here. So in this case, the original was already in sorted order, but we still had to do this work anyway. But now that we took the original array, have it sorted into a left half and a right half, we can merge these two portions together to make the original array sorted. So forgetting about the original values that were over here, we again use our two-pointer technique. We have a pointer at the beginning of the left array and a pointer at the beginning of the right array. We compare the values. 1 is smaller than 2, so we're going to take the 1, put it at the beginning, and then we're going to shift the pointer that was here to be over here. By the way, we are going to have a third pointer in the output array. It's going to tell us where we should insert the next element. Originally, it's over here. Now that pointer is going to be over here. And then next it's going to be over here, and then here, and then here, and keep going until, we run out of elements to insert. But right now, we're going to be comparing the 2 and the 6. Which one is smaller? The 2 is smaller, so we're going to insert the 2 over here. We're going to take the pointer that was at the 2 and then shift it to the right to be over here. And we're going to repeat. Which one is smaller, 3 or 6? 3 is smaller, so let's put the 3 over here and then shift the pointer to be at the next element. Let's compare these two again. 4 is smaller, so we put the 4 over here and then shift our pointer to be over here now. It's out of bounds, so we have nothing left to compare this 6 to. So at this point, whether we have one element over here or maybe we would have a couple more elements over here, regardless, since we ran out of all elements of one of the arrays, at this point, we would just fill in the remaining spots from the other array that's non-empty. So in this case, we only have a 6, so we put the 6 here. But if we had more elements like a 7 and an 8, we would just start filling them over here. So taking a quick look at the code, like I said, this is going to be a recursive algorithm, clearly, where we're breaking it up into 2 steps. So this is going to be 2 branches of recursion. Now into this merge sort function, I'm passing in the starting index and the ending index as well as the array that we're actually going to be sorting. That's because as we break this up into subarrays, we don't necessarily have to create a variable for each subarray. We can just kind of keep track of this half based on the starting index and the ending index, rather than actually creating a brand new subarray like that. But how do we know if we've reached the base case? Well, if the length of the subarray is less than or equal to 1, well, how do we get the length itself? We can take the ending index minus the starting index plus 1. So basically, this element by itself is at index 0. So what we do is take the ending index, which is 0, minus the starting index, which is 0, plus 1 gives us 1. So this is of length 1. So that's how we know it's a base case. That means it's already sorted, so we can just return the array itself. But if we got to a case like this one where the starting index is 0 and the ending index is 1, then we're going to get the ending index minus the starting plus 1, which is going to give us a length of 2. That's correct. This is length 2. But that means our length is not less than or equal to 1. So what we have to do is calculate the middle index between these two. So we take the starting plus the ending and divide it by 2. So 0 plus 1 divided by 2. So most programming languages will round down. That's what we want to do, round this down. So a 1 divided by 2 is going to evaluate to be 0. So we're going to say the middle index is 0. This is the middle index. So what we're going to do now is break this up into 2 halves. We're going to call merge sort from starting to middle. So in that case, this means call merge sort on the array starting at index 0 and ending at the middle index, which is 0 as well. So we're going to call, basically that evaluates to this. We're going to call merge sort on just the first element, and we're also going to call merge sort on the second half of the array. So from index m plus 1, which is 1, and the ending index, which is also 1. So, that's pretty much correct. We're going to call merge sort on this portion of the array. And these, of course, are the base case. So after we call merge sort, we're going to expect those 2 halves to be sorted. So then what we're going to do is merge those halves together. Now, I haven't shown you the implementation of this. It's not super complicated. It's just a decent amount of code. It's basically the 2-pointer technique we were talking about a moment ago. But what we're saying with this function call is merge the left half of the array, which starts at index s and ends at index m, and merge that with the right half of the array, which starts at m plus 1 and ends at index e. So it will basically merge these two together into the original 2-element array. Now, I will say when we do merge the left and right half together, we do need to create extra memory. So for the left and right half array, we're going to create temporary arrays. So we are going to create copies of the left and right half arrays, but we're only doing that for the merge step. So only when we start to actually merge them together into the original are we going to create those copies so that we don't lose what the original values were. So in general, we start out with a big problem, we split it into 2 sub-problems, solve the sub-problems, and then merge the result of the sub-problems together. Now, in terms of time complexity, this is a relatively efficient sorting algorithm because we're splitting it into halves. We're doing that on purpose because it does make things more efficient. So the first question is, starting with an array of length n, how many times can we split it by half? In other words, how many levels are there to this recursion? Because it's going to be the same number of times where we can take n and divide it by 2. Because here we have, let's assume actually we just had 4 elements to keep the math simple. We would have 4 elements. We would split it into 2 elements on each side, and then we would split it into 1 element on each side, and these 2 wouldn't exist. I'm doing this just for simplicity. But we start with n equals 4, we divide it by 2, so n equals 2, and then we divide it by 2 until n equals 1. We know when n equals 1, that's our base case. So what's the math formula for how many times we can take this number and divide it by 2 until it's equal to 1? Well, if we were starting at 1 and then multiplying it by 2 every single time, that would be something like 2 to the power of n. But we're doing the reverse of that. We're dividing it by n. So what we're asking is we have a number n and we want to divide it by 2 and then divide it by 2 and then divide it by 2, which is the same as saying 2 times 2 times 2, etc., right? Which is the same as saying 2 to the power of some variable like x. Right, this is the number of times we're going to divide this by 2, and we want to keep dividing it by 2 until it's equal to 1. Well, by doing a little bit of algebra on this, we can rearrange this to be the same as n equals 2 to the power of x. We care about x. That's how many levels are going to be in this merge sort algorithm. So how do we solve for x? Well, in case you forgot a little bit of math, I'll tell you, we can take the log of both sides of this equation. That will give us, and by the way, I'm doing log base 2. Log base 2 of n is equal to log base 2 of 2 to the power of x. And if you forgot your log operations, this can be simplified to take this x away and put that x over here. Now, log base 2 of 2 is the same as saying 2 to the power of what is going to be equal to 2. Well, 2 to the power of 1 is equal to 2. So this whole thing, log base 2 of 2, simplifies to be 1 is what I'm getting at. So what I'm saying is we already solved for x. X is equal to log base 2 of n. So what I'm saying is if we have a number n equals 4 or any number, how many times can we divide it by 2 until it's equal to 1? Well, our answer is log base 2 of n. Log base 2 of that value is how many times we can divide it by 2 until it's equal to 1. And this turns out to be a reoccurring theme throughout algorithms and data structures. It's something we're going to see a lot more throughout the course. And this is kind of the math background of why most people don't touch on this and most people never learn it and never understand it. But I wanted to explain it to you because I think thinking about it this way and understanding your thought process is very important throughout algorithms and data structures. It's really what separates beginners from people who can solve problems on their own. So we did all that work just to figure out that the height of this is going to be log base 2 of n. I'm going to usually omit the 2. Usually it's implied that logs are base 2 most of the time. But that's not the entire time complexity. That's the number of steps that we're going to have. But what's the time complexity of each step of this algorithm? Well, it's big O of n. Let me tell you why. Basically, it has to do with this merge step. So suppose we're at this step of the recursion. We have our subproblems here, and now we want to merge them together in this array. What are we going to have to do? We're going to have to iterate through every element in each of the subarrays, which is going to result in an element being put in each spot in the original array. So basically, for this step, we're going to have to iterate through every position of the input array. So that's clearly an O of n time operation. But my argument is we're going to be doing that for every level in this recursion. So here for this subarray, we're going to split it into a couple smaller ones and then merge these into this array. But this is only half of this level, right? To do this part of the level, we're going to have to do the same thing. We have an individual element here and here. We're going to merge these together into the original array. And so this level, to build this level, took O of n. And similarly for the bottom level, it's the base case, but we still have to visit this, right? Like one operation is still going to run for this part, and then same for this and for every part of this. So this level takes O of n time complexity to construct this level. So basically the number of levels we have is log n. For each level, we're doing big O of n time complexity. So the overall time complexity becomes log n times n, or in other words, we could write it as n log n time complexity, where this is being multiplied by that. So overall, the big O time complexity of merge sort is n log n. Now the memory complexity is going to be big O of n, because at any point, like for this point, we're gonna have to create two temporary arrays, which are these ones, to build the original array. So that's going to have extra memory, which is roughly big O of n, which is the size of the original input array. So now the last question to answer, is merge sort a stable sorting algorithm? Does it preserve the order of elements where there's a tie? Like, when we sort this array, will this 7 come before this 7? Well, we can definitely code it in such a way that it does. So first we'll merge these two together. There's only one way to merge them together. The 3, of course, is going to go before the 7. It's smaller. It has to do that. And this value, there's only one 7, so that's the only way we can have that. And now as we build our new output, we're going to have 2 pointers, one pointer here and one pointer here. This one is smaller, so we have no choice but to put the 3 over here. Next, we're going to shift this pointer to go at the next position. Now, to make sure that this is stable, we have to put this 7 before this 7 because now there's a tie. How are we going to code that up? We're going to say as long as the element from the left array is less than or equal to the value in the right array, then this value is going to go in the next spot. So it matters how we handle the equality case. That's the edge case. If this one is smaller, it's going to go first. If this one is smaller, it's going to go first. But if they're both equal, then we're going to have the left element go because that makes sure that this is stable. Because if the element showed up in the left half of the array, that must mean it came in the original order. It came before the element in the right half of the array. So to add to our list, merge sort has a time complexity, a worst case time complexity of n log n, and it's also a stable sorting algorithm. So merge sort is in most cases preferred over insertion sort. That's why this is one of the most common sorting algorithms used. But you might be wondering, is n log n really that much more efficient than n? And the answer is yes. We know that the value n grows linearly and the formula 2 to the power of n grows very quickly. And the comparison between these two is the same comparison between n and log n. This grows so much more slowly than n. Think about it like this. If we had a value like 8 and we wanted to get it to be down to 1 and we were decrementing it, we would go like 7, 6, and then keep doing that until we got down to 1. That's pretty much big O of n. It's linear. But when you have something like log n, we start at 8. Instead of decrementing, I'm going to divide it by 2. I'm going to go way fast. We're going to hit 4, and then we're going to divide it by 2 again. We're going to hit 2, and then we're going to hit 1. This is a small example, but this is equivalent to log n. But you can imagine for really, really big numbers, it's going to be a lot faster to take a big number and keep dividing it by 2 to get it to 1 rather than taking a big number and then, subtracting 1, which would be linear. So log n is very, very efficient compared to n. Quicksort is another common sorting algorithm, and it's actually very, very similar to merge sort. The idea is that instead of splitting the array into 2 equal halves and then sorting those halves, instead, we're going to pick a random value, and for convenience, we usually pick the rightmost value, and this is called the pivot value. So the pivot value is special because what we're going to do is we're going to iterate through every single value in the input array, except for the pivot value, so basically every value before the pivot value. And we're going to compare that value to the pivot. And every value that's less than or equal to the pivot value is going to be in the left partition of the array. So what we're going to do is take the input and partition it into 2 pieces, a left and right piece, where every value that's less than the pivot, less than or equal to the pivot, is going to go in the left half, and every value that's greater than the pivot is going to go in the right side. And performing this partition is actually pretty simple in terms of code. And we can actually perform the partition in place. That means we don't need to allocate any extra memory to do the partition. We can do it with just a single array. What we're going to do is take the rightmost value. That's going to be called our pivot. We're going to have a pointer that's going to start at the beginning of the array. And the idea is If we took every value that's less than or equal to the 3 and then placed them in this leftmost area, if every value in the input array that's less than or equal to 3 was placed over here, then by definition, all the values that are greater than 3 would take up the remaining spots. As long as we swap them appropriately, that's going to be the case. So all we have to worry about is taking the values less than or equal to this and then filling them starting at the left side. If we do that correctly, then the less than or equal to values will be here and the greater values will be here. So let's start doing that. So we're actually going to have 2 pointers. One pointer is just going to help us iterate through here, and then the second pointer is going to tell us where we should insert the next value that is less than or equal to 3. So first we get to 6. 6 is not less than or equal to 3. So in this case, we don't do anything. We take our pointer over here and then shift it to the right by 1. This pointer stays here because when we do find a value less than or equal to 3, this is the first spot we're going to put it. So now we find a 2. 2 is less than or equal to 3. So we swap 2 with whatever happens to be in this position. So we can swap these two values. 6 goes here and then 2 goes here. Now this pointer that's over here is going to be shifted over here. Now this is the next spot that we're going to insert the value that's less than or equal to 3. So next we can take this pointer and then increment it one more time. So now we're at 4. Is 4 less than or equal to 3? It's not, so we don't do anything with it. We increment our pointer one more time. We get to 1. 1 is less than or equal to 3. So that means this 1 is going to be placed where this pointer happens to be. So we'll be swapping these two, placing the 1 over here, and placing the 6 over here. And then this pointer will finally reach the pivot index, and we don't really need to do anything. We basically ignore that. But at this point, our array looks something like this: 2, 1, 4, 6, 3. We wanted to partition the array such that every value less than or equal to this was on the left side, every value greater than this was on the right side. But where should we actually put this pivot itself to satisfy that? Well, this is where our pointer ended. That means our pointer is here. That means every value to the left of that is less than or equal to 3. So this is a good position to put our pivot at. So that's exactly what we're going to do with quicksort. We perform one last swap between where our left pointer is at and our pivot value. So we end with a 3 over here and a 4 in this position. So to make it more clean, after doing our partition, we have a 2, a 1, and a 3 over here, and we have a 6 and a 4 on the right partition. Now notice how the left side is not sorted and the right side isn't sorted. Just because we partitioned them does not mean they're sorted. But what is true is every value on the left is less than every value on the right. Every value on the right is greater than every value on the left. Now this is where the recursive step comes in. Now let's run quicksort on the left side and run quicksort on the right side. Now before we recursively run quicksort here and here, one thing to notice about the 3 is that it's already in sorted order. Everything to the left of it is less than or equal to it, and everything to the right of it is greater than or equal to it. So this 3 doesn't actually need to be part of our equation anymore. We can just ignore this. So it does exist, but we're not focusing on it. When we run quicksort on this subproblem, let's just focus on these two values. This is already exactly where it needs to be. And that's always going to be true of the pivot value. So now we're going to choose the rightmost element, which is going to be our pivot. So in this case, 1 is our pivot. We're going to start at the beginning of the array. We're going to compare 2 to the pivot value. Is 2 less than or equal to 1? It's not. So we don't do anything. And then we would take our pointer increment to be here. It's at the pivot, so we don't do anything. That's when we stop. And the last thing we do before we split the array is we take the pivot and swap it with wherever our left pointer would have been. Remember, our left pointer starts here, and since we didn't end up swapping anything here, our left pointer would stay here. So what we're going to do is take 1 and 2 and then swap them, because we know our pivot should go at the beginning. 1 should go at the beginning, 2 should be here. And so this is the index that our pivot went to. And I didn't mention this earlier, but when we take the array and then split it into 2 pieces, we do it based on where the pivot value was inserted. So the pivot value 3 was inserted right into the middle. That's why we took the first 3 values and then put them over here, even though we didn't actually include the last value. And then we took all values to the right of that pivot and then, ran quicksort on them over here. But so now that our pivot was over here, we're going to take the 1 and it will go on the right side, and then all the remaining values, in this case 2, are going to go here, and that's essentially the base case anyway. So when we run quicksort on this and this, we're not going to do anything. Of course, an individual element is already sorted. And remember, for quicksort, we're not allocating any extra memory. These swaps that we're doing are happening in place. That's the advantage of quicksort over a merge sort. We don't actually have to allocate extra arrays. Now, running quicksort on these 2 elements, this is going to be our pivot. This is where our pointer is going to start, and this is also where our left pointer is going to be the pointer that tells us where to insert the next element that's less than or equal to the pivot. So is 6 less than or equal to the pivot? Nope. So we take our pointer, our left pointer will stay here, but our I pointer will be incremented over here. And that's how you know we can stop when we reach the pivot. And then the pivot will always go to the position that the left pointer stopped at. It was over here, so we swap these 2 values. So this would be a 4, and then this would be a 6, and then we would run quicksort on these 2 subproblems, 4 and 6, but this is the base case. This is also the base case, so we're done. Now remember, this is happening in place. These are not extra arrays. So if this is in the first position, this is in the second position, we know that 3 was in the third position, right? And that was always going to stay there. This is in the fourth and this is in the fifth. We have a sorted array. Now, based on this example, the time complexity looks very similar to merge sort because we're breaking it up roughly into equal halves. But the thing about the pivot is we're always picking the rightmost value, and it might not result in equal halves. So if the elements were arranged a bit differently, in this case, they're already in sorted order, we would have 6 be our pivot. And what we would end up doing is partitioning every value less than or equal to 6 on the left side. All of these values are less than or equal to 6. So in that case, we would split this into 2 subproblems where we have the first 4 values over here, 1, 2, 3, 4. And then on the right side, we would just have 6. And then this 4 would be the pivot when we're running this subproblem, which would, keep the values in the same exact order. All these are less than or equal to 4. So then this would end up splitting it into something like this, 1, 2, 3, and then 4 would be over here. And we would essentially continue doing this until we complete it, which would look like this, 1, 2, 3. And then lastly, we would split this into 1 and 2, the individual values. But then this, all of a sudden, the height of this becomes n, where previously, if we split it into equal halves, we know then the height of it is going to be log n. But in this case, we're not splitting it into equal halves. So in the worst case, the height of this is going to be big O of n. Now for each level, we're still having to iterate through approximately the size of the entire input. That's approximately how many we're going to have on each level. So in that case, the overall time complexity becomes n squared in the worst case. So that kind of shows us that quicksort is not necessarily better than merge sort. But on average, this is not going to happen. This is the worst possible case where the input is already sorted. One way to get around this is not to pick the pivot as the rightmost element. It's to take, maybe the leftmost value, the rightmost value, and the middle value. And among those 3, choose the middle value and then use that as the pivot. So the way we've been selecting our pivot is a bit naive, but there are optimizations you can do which will help us to make sure that we don't hit this worst possible case. So on average, if we do split if we split the array into two roughly equal halves, then the time complexity of this obviously is going to be very similar to merge sort. In fact, the height is going to be log n, and since we know each step we're doing an O of n operation, then the overall time complexity for quicksort on average is going to be log n, not n squared. But the worst case still is going to be overall n squared. So quicksort is a pretty interesting algorithm. So the code for the partition would look something like this. Of course, the algorithm quicksort is recursive just like merge sort because we're splitting it up into subproblems. The base case is the same as merge sort. If the length of the subarray is less than or equal to 1, then the array is already sorted, we can return. Otherwise, we're gonna pick our pivot. In this case, we're doing it the naive way where we're just taking the rightmost element. We're also initializing our left pointer to S, which is the start of the array. And that left pointer is basically what's gonna tell us where we should insert the next value that's less than or equal to the pivot. So now to actually run the partition, we have a single pointer I, that's that pointer I've been referring to on the bottom, just scanning through the input. And we check, is this value less than or equal to the pivot? That's what we're checking here. If it is, we're gonna perform a swap. If it's not, we don't do anything. In this case, it's not less than or equal to the pivot. We don't do anything. We increment our pointer to be over here. Is this less than or equal to the pivot? Yes, it is. So let's perform a swap. First, we take the left value over here, put it into a temporary variable because we're about to overwrite it right now. We're going to replace it with the value at index I. This is that value. We're going to put 2 over here. And then we're going to replace this value with that temp value that we stored. So we're going to put 6 over here. And then lastly, we're going to increment our left pointer. So this pointer is now going to be incremented to be here. This is the next spot that we would insert a value that's less than or equal to the pivot, which is 3. So in general, this is how the partition is going to work. And don't forget, the last part of the partition is to take that pivot value and swap it with whatever happens to be at the left index. So in this problem, for this example, I'm pretty sure this is where we ended up swapping it with. And this is really the difficult part of the work. After that, the last thing would be the recursive step where we run quicksort on the left portion. We're taking left -1 because we know at left is the index where we put our pivot, and we know that the pivot is essentially in the perfect spot. In this case, 3 would be here, 4 would be here. The pivot is already exactly where it needs to be, so we're running quicksort on this half and running quicksort on this half. We're not even including the pivot value anymore. So we would do the left side and do the right side, and then we would return. So in this case, you can see the recursive step is pretty simple. The partition is where most of the logic happens to be. So the last question, is quicksort stable? And the answer is, generally speaking, no. There is a way to technically modify it so that it is, but generally speaking, quicksort is not considered a stable sorting algorithm, and let me show you why. The easiest way to do so is through an example. So we're going to partition this array. 5 is going to be our pivot. So we're going to be iterating through the array. 7 is not less than 5. 3 is less than 5, so we swap these two values. So now the 3 goes before the 7. We'll look at this value, it's not less than or equal to 5, and next we'll look at this. 4 is less than or equal to 5, so this is going to get swapped in the next position, which is over here. And you can probably see where I'm going with this. So swap these. So now our 3 is here, our 4 is here, and we have a couple 7s over here. I mean, the partition worked perfectly, but you can see that the original relative order of the 7s, the red 7 was here and the yellow 7 was over here. But now the yellow 7 goes before the red 7. So this definitely does not preserve the relative order of values when there's a tie between them. So generally speaking, quicksort is not stable. So adding to our list, we have quicksort, which is an unstable algorithm. Generally speaking, it is better than insertion sort, though the worst case time complexity, as I showed earlier, is n squared. The average time complexity is n log n. I know usually we care about the big O time, which is the worst case time. So if we're being super technical, it would be n squared, but generally speaking, people consider quicksort to be an efficient algorithm. On average, it's n log n. So that's how I'm going to list this as, but in a real interview, it would be worth mentioning that the worst case is n squared, but generally it runs more efficiently than that. Now it's time for another sorting algorithm called bucket sort. Are you surprised at how many sorting algorithms there are? You should be, because there's a lot more sorting algorithms that we're not even going to cover. But bucket sort is definitely worth covering because it's unique in that actually it can run in big O of n time, even in the worst case. So it's super efficient. So why did we even bother learning the other algorithms that run in, let's say, n log n time? Well, that's the downside of bucket sort. It's very rare that you're able to use bucket sort. It's sort of a forbidden technique, which very rarely gets to be used. And that's because there needs to be certain constraints for the problem. In this case, the constraint is on the specific values that we are sorting. We're only allowed to use bucket sort if we're guaranteed that all the values that we're sorting fit within a finite range. So in this case, the only values we have are 0, 1, and 2. So we can say that the range of values is in between 0 and 2. Now, typically when you have an array of integers, usually the integer is bounded, like it might be a 32-bit integer or a 64-bit integer, and therefore we would have a range, right, like -2 to the power of 32 approximately, all the way to 2 to the power of 32 positive approximately. So we could say that that's our range, but that's a really, really big range, and that usually doesn't qualify for bucket sort. We're talking about generally smaller ranges, but in this case, we have a very small range, 0 to 2. I mean, you could have a lot bigger, 0 to 100, or maybe even 1,000, or 10,000, or 100,000, right? Like that's still relatively small. Back to our example. We have this constraint, so we can use bucket sort. So what are we going to do? Well, for every single value in our range, in this case we have a 0, a 1, and a 2, we're going to create a bucket for every single value. That's where the name bucket sort comes from. So for 0, we're going to have a bucket, for 1, we're going to have a bucket, and for 2, we're going to have a bucket. So I have an array of 3 values. This is where each of our buckets is going to go. So each of our buckets is basically a value itself. So for this array, we have indexes 0, 1, and 2. So conveniently for us in this case, the 0 is going to map to the 0 index, 1 is going to map to the 1 index, and 2 is going to map to the 2. It's not necessarily always going to be the case like this. For example, instead of having a 2 here, we could have had, let's say, a 4. In that case, we would just, arbitrarily put the 4 in this spot. The point is, for each of these values, we have it mapped to a position, and what this position is going to represent is the number of zeros that we have. So what we're going to do here is go through this array, count how many zeros we have, and then put that count over here. So we know we have 2 zeros, so 2 would go over here. Here we're going to put how many ones are in the input array. We just have a single one, so we're going to put 1 here. How many 2s are in the array? We have 1, 2, 3, so we're going to put a 3 over here. Now, what would be the time complexity of counting all of these? You might think we have to pass through the input 3 times, 1 for each of our buckets, but we actually don't. Let me just quickly show you how we would actually go about counting these. It's mostly straightforward. We would have an index, right, like I, starting at the beginning of the array. And actually just jumping into the code really quickly, assuming we're given an array like this, which, looks exactly as our example, and we have our counts, we're going to have an I pointer going from the beginning of the array all the way to the end. And what we're going to do is take this value to, well, first let's talk about how we're going to initialize our counts. Initially, we're going to say we have 0 zeros, we have 0 ones, and we have 0 2's. But as we iterate, we're going to get to the first value, we have a 2. So what we want to do is increment our number of 2's. We can do that by going to counts at index 2 and incrementing it by 1, because we know that 2 maps to the index 2. That's convenient for us. It might not necessarily be the case, but we could have some kind of mapping. So we can increment this by 1. And we're going to continue to do that. We're going to go here. We're going to end up incrementing our number of 1's. We're going to go here. We're going to increment our number of 2's again. We have 2 2's. We're going to go here. We have 1 0. Now we have 2 zeros. So increment the number of zeros to 2. And then we have our last value, which is a 2. So we increment the number of 2's to 3. So now just cleaning this up a little bit. After counting, we know we have 2 zeros, 1 1, and 3 2's. Now it's time for the second portion of the algorithm where we actually sort the array. So the reason we counted each of these values is because we know when we take this array and we sort it, of course the zeros are going to go at the beginning, then the 1's, and then the 2's are going to go at the end. We know the output is going to look something like this. So if we could just know how many zeros to put at the beginning, then how many 1's to put, and then how many 2's to put, and of course, maybe we would have some 3's as well and have some 4's, but in this case we don't. But if we can do that, then we can fill this in without having to swap these values around. Every sorting algorithm we looked at so far would swap values. We have a 0, we know that's going to go at the beginning, so we swap it with the beginning. But bucket sort does not do that at all. By the time we get to this point where we have counted all of the values, we don't even need the input values at all. We don't even care what these are anymore. We're just going to start overwriting them, and we're going to do that with a couple loops. So our outer loop is going to have a variable called n, which is going to iterate through every position in counts. So we're going to iterate from 0 to counts.length. So we're going to go from here to here to here. By the way, this is just pseudocode. It's not necessarily syntactically correct, but this is the main logic that any program in any language would follow. So we have n. And then in the inner loop, we're going to have a second pointer. Let's call it j, which you can see j is not actually being used anywhere, but we're just using this pointer to iterate this many times. So let's forget about j. Let's just see how many times are we iterating. Well, 0 to counts of n. So basically what I'm saying here is we're going to iterate this many times. At this point, our n pointer is here, so we're going to iterate 2 times. Now, what exactly are we going to do? We can see we have a third pointer, I. This is important because I is going to tell us where to fill in the value. Initially, I is going to be at 0. Of course, we would want to fill in starting from the beginning. So we're going to fill this position with whatever n happens to be. We know n is the value, 0 is the value, so we're going to put 0 over here. And how many times are we going to iterate over this loop? Well, whatever counts of n is, 2 times. I hope it's starting to make sense now. We have 2 zeros, so we're going to put 2 zeros at the beginning of our array. So we're going to increment I now to be over here. We're going to put a 0 over here. And then our inner loop is going to finish executing. And then we're going to go back to the outer loop. Now our n is going to be incremented. Our n is going to go over here now. So now how many times are we going to execute the inner loop? Well, n is at 1. How many 1's did we have? We only had a single 1. So now with our I pointer over here, we're going to fill in a 1, and then we're going to increment our I to be at the next position. And this loop only executed a single time, and then our n is shifted here. So we're going to put a 2 over here. We're going to increment our I. We're going to put a 2 over here. We're going to increment our I, and we're going to put a 2 over here. We just ran that 3 times. So our inner loop is finished executing. Now we're going to go to the outer loop and end up shifting our n one more time. Now it's out of bounds. That's how you know we're done with the outer loop. We're done with the algorithm. Our array is sorted and we can return it. So now the question is, why is this algorithm big O of n? Because don't we have nested loops over here? Well, as I just showed you, this nested loop portion, how many times is this nested loop portion actually going to run? Just because we have nested loops does not mean the time complexity is n squared. We know that this I pointer is going to be incremented every time the code actually runs and evaluates. And as I just showed you, our I pointer is going to start at the beginning and then keep being incremented until it goes out of bounds. How could that possibly be n squared? Just because we have nested loops does not mean it's n squared. Because the first time the loop runs, it ran twice. Then the next time it ran once. And the next time it ran 3 times. All of those are always going to total up to be n, because of course we're only going to have n values. These are just the counts, and then we're going to put the values into the array, which of course is of size n. So what I'm saying is this nested portion is big O of n time complexity. Of course, we did have to iterate through the input one time before that over here, and the time complexity for that was also big O of n. Well, adding these together would make the time complexity big O of 2 times n, which we know reduces to be O of n because we don't care about constants. So the overall time complexity is big O of n. In this case, though, we are using a bit of extra memory. We're using an array, but what's the size of this array going to be? It's going to be whatever the range of values happens to be. The possible range of values. And we know, in this case, it's from 0 to 2, but it could be, from some constants n to m, something like that. And as long as it's some fixed size that isn't like insanely large, we assume that this is a constant. So therefore the extra memory we're allocating, in this case, it's big O of 3, but it's going to be some constant c. And we know constants reduce to big O of 1 space complexity. But I do want to mention that this is sort of a forbidden jutsu. It's very rare that you're going to actually use bucket sort. The only time you're probably going to end up using it is in an interview, to be honest. But there definitely are some practical applications, and maybe you'll come across them at some point in your career. Now, the last question for us to answer, is bucket sort a stable algorithm? Well, the answer is pretty short, no, and I think in this case it's actually pretty clear why. When we overwrite the array, we're not even caring about, which 2 came first, because we just counted that there were 3 2s and they're all going to go in the last 3 positions. We don't care which one goes where. In fact, we're not even swapping the values anyway. We're just overwriting them. So it doesn't preserve the relative order at all. So bucket sort is definitely not a stable sorting algorithm. But if we wanted to, technically we could make bucket sort a stable sorting algorithm, because for example, as we count the 2s, we could preserve that somehow. For example, if this was actually a linked list instead of an array, as we count the 2s, instead of just counting them, we could have actually taken each 2 and added it to a linked list. So we would have a series of 2s like this, where this one would have been the first one, this one would have been the second, this one would have been the last. And then when we finally build the result, we would have put them together something like this. Now, this isn't super important to understand. I'm just mentioning it anyway. It's pretty rare that bucket sort is used on anything other than an array anyway. So now lastly, let's compare our sorting algorithms. So bucket sort, which is generally an unstable sorting algorithm, runs in the worst case in big O of n time, but it's a little bit misleading. Remember I said this is sort of a forbidden jutsu. Most likely you won't be able to run bucket sort on the input that you're given. But if you ever are given an input where bucket sort can be run, don't ever use any of these other algorithms because they're not going to be as efficient as bucket sort. If you are given an input where the values are within some specified range, always use bucket sort. Otherwise, if you're given just a general input, most likely you will end up using either merge sort or quick sort. I think merge sort is generally more common. Next, let's look at the binary search algorithm, which is very related to sorting. And that's because binary search can only run on an input that is already in some type of sorted order. Because binary search is sort of an algorithm that you might already know intuitively. If you're searching for something, in the worst case, you would have to look at every single value in the input to find what you're looking for. And let's say you were looking for an 8. In this example, you wouldn't reach that until the last position. So you would have to look through all of these before you realized, well, the 8 was at the end. Now, only if you knew that the input was actually in sorted order, you could have done it more efficiently. And the idea is the same with dictionaries. When we have a really massive list of words, we put them in alphabetical order in a dictionary. So if you're looking for the word banana in the dictionary, let's say you go at the halfway point of the dictionary and we find words starting with the character J. At that point, where would we go? Would we go to the second half of the dictionary or the first half of the dictionary? Well, we know the character B starts before the character J, so then we would go to the first half of the dictionary and then look somewhere over there. The idea is the exact same behind binary search. Another example, if I told you to guess a number between 1 and 100, and I told you if you guess wrong, I'll tell you if your guess was too small or too big, of course what you would do is guess 50. So then if I tell you your guess is too small, then you know that the answer is somewhere between 50 and 100. But if I tell you your guess is too big, then you know the answer is between 1 and 49. Or the third case is your first guess was already correct. The good thing about this guess is you can eliminate half of the possibilities and reduce your search space. And you can't only do it once, you can repeat this operation. So if I told you your guess is too big and the real answer is between 1 and 49, what would you guess? Would you guess 2? No, you wouldn't guess 2. Because there's two possibilities. I tell you that your guess is too big. That's the good case, because if 2 is too big, then that means the only answer left is 1, so you found the answer. But what if I tell you your guess is too small? Then the answer is somewhere between 3 and 49. You didn't really narrow down much. You only narrowed down like 2 values. So that's why we guess the halfway point. It's less risky, because we know every single time we're going to eliminate at least half of the possibilities. So in this case, we would guess something like 25. And maybe I tell you your guess is again too big, so then we know that the real answer is somewhere between 1 and 24. We narrowed down half of the possibilities again. This is the idea behind binary search. Now, it's most common to run binary search on some input, usually an array. And it's very important for the input to be in sorted order, because if it's not in sorted order, then we can't run binary search. Because if it's not in sorted order, then the best we can do is just individually look at every single element, and we know the time complexity for that is big O of n. But binary search is going to be even more efficient. Let's continue. So in this example, our target is 8. We want to return the index that the value 8 appears in the array. And if the target doesn't exist in the input, and that's definitely a possibility sometimes, what we normally do is just return something like -1 to indicate, -1 isn't a valid index, so that indicates that we weren't able to find a solution. So what we would want to do is go somewhere close to the middle of our search space. In this case, we could either go here or here, but what's the main algorithm that we use? Well, first we want to have our boundaries. Our boundaries tell us what is the portion of the array that we're currently considering. At the beginning, the value 8, the target, could be anywhere in the input, so we have to consider the entire input array. So we have 2 pointers. I call them the left and right pointer, but sometimes people will call it the low and the high pointer. Basically, it's our 2 boundaries which make up our search space. So by taking our 2 boundaries and adding them together and then dividing that by 2, we can get approximately the middle. So in this case, that's going to be 0 plus 7 divided by 2, and usually we round down, so this is going to evaluate to 3. So this is what we call our middle index. I'm going to call it M for short. M is going to be at index 3. So taking a look at some pseudocode, this is what we've done so far. We've initialized our left pointer to 0, and we've initialized our right pointer to be the length of the array minus 1. And then we start looping. We calculate our mid pointer between the left and right pointer, dividing by 2. And then we want to check the value at the mid pointer. We know there's 3 cases. Either our target is greater than this value, meaning it's actually somewhere to the right, or our target is less than this value, meaning it's somewhere to the left. And the third case, which I've used as the else case, is we've found the target. Because if the target isn't greater and it's not less, then it must be equal. At that point, we're going to return mid, which is going to be the index. That's what we're trying to return, the index. So in this case, clearly our target 8 is greater than 4. So we know we should now start searching over here. So what should we do? Well, we have to update our search space to be over here. How do we do that? Well, our right pointer is already where it should be. So the only thing we have to do is take the left pointer and shift it over here. And how am I going to do that? Well, I'm just going to take mid plus 1 because we know this is not the solution. And we know that everything to the left of it is also not going to be the target because the input is in sorted order. We can only assume that because this is sorted. So we're going to eliminate all of these from consideration. And now we're going to go back up to our loop. And let's just assume that this mid is going to be changed now as well. So this is the case that we ended up executing. Target was greater, so we updated the left pointer. And actually, to make things a little bit more interesting, I'm going to change the target. Instead of being 8, I'm going to change it to be 5. So let's assume our target is 5. An initial part of the code would have executed the same regardless of whether it was 8 or 5, because 5 is also, greater than 4. We would have still executed that. But continuing, we're going to now calculate mid again because our loop is going to execute. I'll touch on this condition a little bit later on, but our mid now is going to be 4 plus 7 divided by 2. That's 11 divided by 2. We know we round down, so we're going to get 5 as our mid. So let's put mid over here at index 5. Now let's compare 6 to our target. Is our target greater than 6? Is 5 greater than 6? Nope, so we don't execute that. Is our target less than 6? Yeah, our target is less than 6. 5 is less than 6. So now we're going to execute this portion of the code. So now what we would logically want to do at this point is, since our target is not 6 and it's less than 6, we know it's going to be somewhere to the left. So would that mean it's somewhere over here? Well, we already eliminated all of these from consideration. So yeah, it's somewhere to the left, but it's not anywhere beyond this point. So how we're going to handle that is by taking our right pointer and moving it to be at mid minus 1. It's to the left of mid, so this is where our right pointer is going to go, and you can see our left pointer is also at that position. What that means is our search space was reduced to a single value. That's good because that means we're either close to finding our result or our result doesn't exist in the input. By the way, if we're searching to the left, that means we removed all of these from consideration. So now finally, we're going to execute the loop one more time. We're going to calculate our mid. Left and right are both 4. So we're going to say 4 plus 4 divided by 2. That's of course going to be 4. And that makes sense because this is the only position in our search space. So now we're going to check, is our target greater than 5? Nope. Is our target less than 5? Nope. That means the else is going to execute. That means our target, which is not greater than 5 or less than 5, must be equal to 5. So therefore, we found the solution. We can return the index mid, which is 4, so we return 4. We found the solution. Now, it's possible we would not have found a solution. Let's look at a slightly different example. Let's say our target was actually 9. We would have still gotten to this point. Our mid would have been over here, and we would have executed the loop again. Is our target greater than mid, which is 6? Yes, it is. So then we're going to execute this portion. We want to then search to the right. If our target is greater than 6, it must be somewhere over here. So we update our pointer left to be over here, and we remove these from our search space. So next we're going to execute the loop again, and the condition, by the way, for us continuing to execute the loop is if our left pointer is less than or equal to our right pointer. That basically means we have some existent search space that we're searching over. Even if left and right are equal, that means we have one element remaining. And if left is less than right, that means we have multiple elements remaining for us to search over. So now we calculate mid again. 6 plus 7 divided by 2 rounded down is going to be 6. We're going to check, is our target greater than 7? Yes, it is. And this is where our mid was, so we're going to take left and set it to mid plus 1, which is going to be over here. So we remove this from our search space. Our left pointer is over here as well. Now we check, are we executing the loop again? Well, left and right are equal, therefore left is less than or equal to right. We calculate mid again. It's going to be 7 plus 7 divided by 2. That's, of course, 7. So this is where our mid is going to be. Now, is our target greater than the value here? Yes, it is once again. So what are we going to do? The algorithm is going to say set left equal to mid plus 1. So now left is going to be over here. So basically, it's gone out of bounds. And then we try to execute the loop again, but at this point, left is definitely not less than or equal to right. And by the way, our search space is empty. So this is always going to execute. Left is not going to be less than or equal to right anymore after our search space is empty. And that means we did not find the target that we were looking for, so we're going to end up returning -1. This would have executed the exact same way if instead of our target being too large was actually too small. So maybe it's 0. We would have crossed all of these out, and our left pointer would have been here, and our right pointer would have gone right over here. Or what would have happened maybe if our target was actually equal to 2? It's not too small and it's not too big, it just doesn't happen to exist in this range. Well, to quickly simulate, first we would check mid. It's not the target. We would cross all these out. Our target must be somewhere over here. So among these, we approximate the middle. We check, is this equal to the target? No, the target is too small, so it's not this or this. Then our right pointer would be over here. And we would check, is this equal to 2? No, our target is greater than this value. So then we would take our left pointer and then move it to the right by 1. And then at this point, we would say, well, our left pointer is not less than or equal to the right pointer, and we don't have any elements remaining to search, so we return -1. That's the general simulation. That's the idea behind binary search. It can seem complicated at first, but once you get used to it, it's not too bad. But what about the time complexity? Why do we care about binary search at all? We could just scan through the input and find the target in O of n time. Isn't that good enough? Well, with binary search, with every iteration of the loop, we are eliminating at least half of the search space with one execution of the loop. And then we eliminate half of the remaining values. And then we eliminate half of the remaining values again until we have a single value. And then we eliminate that as well. So what's the math formula for what we're doing here? When we eliminate half, aren't we taking the length of the input? Let's say the length is n, and we're dividing it by 2 again and again and again until it's equal to 1. We talked about that earlier with merge sort. How many times can we divide a value by 2 until it's equal to 1? Because that's going to tell us how many times this loop executes. Well, we talked about it earlier. The formula for that is actually log base 2 of n, and usually we don't even mention the base 2, so this is log n. That's the time complexity of binary search. That's how many times the while loop is going to execute. Inside the while loop, we're just doing a constant time operation, so we don't care too much about that. But this is the worst case runtime, and we know log n is much, much more efficient than big O of n. And in terms of memory complexity, we're just allocating a few pointers. We're not allocating any additional data structures or arrays or anything of variable length. So the memory complexity is big O of 1. There's a slight variation of the binary search algorithm that I wanted to talk about because it can come up in interview problems and it's actually pretty simple to understand once you know it. It goes back to the idea I was talking about earlier, where let's say we were guessing a number between 1 and 100. In this case, we're not necessarily given an array of all the numbers from 1 to 100 in sorted order. That's not the problem that we're given. We're just given a range of values, and in this case, we need to guess the correct number. So in this case, we're not actually given a target either, where we're given some target, let's say 10, and we have to find the index of that. That's not the problem either. We're not given a target. Our goal in this case is to search along this space of values, this range of values, and find that correct value where that n value, whatever it happens to be, satisfies the conditions. And in this case, that would mean that n is the secret number that you're looking to guess. But in other problems, it might be something different. In this case, it's just a guess. There's nothing special we have to do with that n value, but what it could be is we're searching this range of values and we need to check if n satisfies some requirements. So let's say we have some kind of dummy function which calculates if n is correct. It is the value that we're looking for, and this function could have anything inside of it. It could be some computation, it could be, any kind of algorithm, but that's the idea here. But in our original binary search, we were just checking that value. We were checking n. We were checking if it's equal to the target. So this is sort of a more general case. For the original case we were looking at, our is correct would basically just check is n equal to the target, but it could get a lot more complex than that. So this is the general template that you might end up using. That's what I'm going to be talking about now. And it's very, very similar to the original binary search. I just think it throws some people off guard because they've never seen it before, which is why I'm showing it to you now. So this is a sort of template we can use to solve these range style binary search questions. Now this is Python code, but we're mainly focused on the main ideas of the algorithm, not the exact syntax. Now for this binary search, we're going to be given a range of values, let's say, and we're given a lower bound and an upper bound. We're not given an array, notice that. And the rest of the binary search is going to be pretty similar. While our low is less than or equal to our high, we're going to perform binary search. We're trying to guess the number between 1 and 100. We're going to calculate the midway point because we know we want to eliminate half of the possibilities every single time. So 1 plus 100 divided by 2 is going to give us a value of 50, somewhere in the middle. Now, since we're not given a target, how do we know if this is correct or not? Well, it's going to depend on what type of problem you're solving. But either way, let's have a helper function that's going to decide it for us. In this case, I'm calling it is correct. We pass in a single number, and then this function is going to somehow compute for us if our guess is correct. And if it's not correct, we do need to know, was our guess too big or was it too small? So that's for this specific example, but in other types of problems, this helper function could have some different type of computation. In this case, though, you can see I've hard coded it so that if n is greater than 10, we're going to return 1, which indicates that our guess is too big. If n is less than 10, I'm going to return -1, which indicates that our guess is too small. But if we execute the else case, that means n is exactly equal to 10, so we return 0. That means our guess was correct. So in this case, I've hard coded it such that 10 is the target value that we're looking for. But of course, there could be different types of more complex computations that we do. So in this case, for our guess 50, it's too big. We're going to return +1. So our is correct is going to be greater than 0. So then we know our guess was too big, so we're going to update our high value to be mid -1. So our guess, which was mid, is 50. So now we're going to update high to be 50 - 1, which is 49. We eliminated half of the possibilities. And now we go back up to the loop. Low is less than or equal to high. Let's recalculate the midway point. 1 plus 49 divided by 2, that's going to give us a guess of 25. We're going to call is correct. And in this case, our guess 25 is greater than 10, so we're going to return positive 1. This part is going to execute again. So that means our guess was too big. We have to update our high once again. Our high is 49. We're going to set it to be mid minus 1, so it's going to be now 25 minus 1, which is 24. And repeat, take these two, add them together, divide by 2. Our guess is going to be 12. We're going to call is correct. 12 is still greater than 10. So our guess was too high once again. We're going to update high to be 12 minus 1. It's going to be 11. So now our high is 11. We re-execute the loop, add these together, divide by 2. We get 6 as our mid. We check, is 6 correct? Is 6 greater than 10? Nope. Is it less than 10? Exactly. So we're going to return -1. So which one of these two is going to execute? The bottom one, because is correct is less than 1. Because is correct is less than 0. So now we're actually going to update our low pointer because our guess was too small. We're going to update low to be mid plus 1. So our low is going to be 6 plus 1, which is 7. And at this point, you can see how the algorithm is going to progress. Add these two together, divide by 2. Our mid is going to be 9. Is that too big? Nope. Is it too small? Yep. So we're going to take our low, set it to mid plus 1. So our low is going to be 10 now. So now, finally, we're going to take these two, add them together. Our guess is going to be 10 plus 11 divided by 2, so that is going to round down to be 10. So our guess is 10. We're going to check is correct. Is it greater than 10? Nope. Is it less than 10? Nope. It's exactly 10, so we're going to return 0. This isn't going to execute. This isn't going to execute. Our else is going to execute, so we're going to return 10. That was the result we were looking for. We weren't looking for the index. We were just looking for what is the correct value. It turns out to be 10. So of course, this is very simple, straightforward binary search, just that we're not given an array, but the time complexity is still going to be the same. So the big O time complexity is still going to be log n. But in this case, what is n? Before, n was the size of the array that we were given. In this case, n is just the range of values. So since we're going from 1 through 100, the n is basically 100 in this case. If it was 1 through 1,000, it would be 1,000. It's the range of how many values we're running binary search on. I hope this gave you a decent understanding of how binary search can have multiple variations and how, in general, this method could be extended to do a bunch of different things while keeping the core binary search template still the same. Now let's move on to probably the most complicated data structure we've covered so far, which is binary trees. We're actually going to be using pretty much every topic we covered so far to understand binary trees because there's a lot of complexity to them. To start with, we're just going to understand the structure of binary trees. They're similar to linked lists in that we have nodes which have some kind of value. I mean, it could be a character, it could be an integer, or it could be a string, it could be an object. There could be anything contained in the value of this node. To keep it simple, let's assume we have integers, and let's say we have the integer 2 here. And we know that these nodes are no fun unless we have some pointers to connect them together. With binary trees, as the name implies, binary, which means 2, these nodes are going to have 2 pointers. But with linked lists, we had some next pointers and previous pointers for doubly linked lists, so it's kind of similar to that in a sense. It's similar to a doubly linked list node, but in this case, we draw the pointers typically down, and that's because there are some relationships with these nodes. We call this the left pointer and the right pointer. And when we have a pointer like this that's connecting it to another node, let's say a 1 value here, that node is also going to, of course, have a left and right pointer. Now, these nodes have a relationship. It's not like a linked list where nodes are just connected left and right. We say the relationship between these nodes is that this node is the left child of this node. So there's a relationship called the child relationship. This is a child of the parent node. So this node is considered the parent node of this node. But as I said, since this is the left child, this node could also have a right child let's say the value is 3. This node is also a child of this node, and this node also has the same parent as this node. Both of these nodes have the same parent node. And what about these two nodes now? Well, this node does not have a left child as of now, and it does not have a right child either. We can assume that these pointers are pointing to some default value of null. They're not actually pointing at any real nodes. And when we have nodes like these that don't have any children, we call these leaf nodes. So this would be a leaf node, and this would also be a leaf node. But what if for this node we actually did have a child over here? Let's say it's 4. Then this node would no longer be a leaf node. This node would be a leaf node. It doesn't have any children, but its parent node over here does have a left child, so it's not a leaf node. With binary trees, we're always guaranteed to have leaf nodes. If we start at the top of the binary tree, which by the way is called the root of the binary tree, the top node is always called the root node, whereas, the bottom nodes are called leaf nodes. And these are, terms that come from trees in general. Trees have roots. Trees also have leaves. But the interesting thing here is, you might have noticed, the root goes at the top and the leaves go at the bottom, which is kind of the opposite of a regular tree where, let's say you had a tree that looks something like this, where the roots would be at the bottom of the tree and the leaves would be at the top of the tree, but we know that that's not the case here. So that's just an interesting point about trees. We kind of draw them upside down. But these are important terms that are used with binary trees. Of course, every tree is only going to have a single root node, but it could have multiple leaf nodes, and it's guaranteed to have some leaf nodes. But why is that the case? I mean, what if I had from every single leaf node, one of the pointers just pointed back up to the root? I mean, we had that with linked lists, right? In some linked lists I talked about, you could have a cycle. But when it comes to binary trees, we are not allowed to have cycles. That's part of the definition of a binary tree. We're not allowed to have cycles. So since binary trees can't have cycles, that's the same reason why two adjacent nodes like these can't be connected. We can't take the right pointer of this and then connect it to that. That would sort of form a cycle. Now, technically, this here does not form a cycle because each of these pointers connecting nodes can only be one way. We can only go along it in one direction. But the definition of a binary tree, we say that it doesn't form any cycles, basically assuming that these pointers are not directed. Right? Assuming we could go both ways, there should not be any cycle in the graph. So therefore, we can't connect these two nodes together. By the way, nodes like these that have the same parent are considered sibling nodes because they share the same parent. So, that's where this word comes from, sibling, like brother or sister. And I guess it's hardly worth mentioning, but all the nodes in a binary tree have to be connected together. We can't just have some random node over here which isn't connected to the rest of the binary tree and then call this one cohesive binary tree. It's not, because every node has to be connected. We can put the node here where it's actually connected to another node, but we can't just have it floating randomly. All nodes have to be connected to each other. Now, there's another property of a node in a binary tree, which is called the height property, and it's mostly straightforward. First of all, we would measure a single node. We can say the height of a single node like this one is 1. We say that because there's just a single node, so we call it to be 1. The height of this is 1. It doesn't have any children. But for a node like this one, where it does have some children, we measure the height starting from this node, going down to the lowest descendant of the node. This is another key word. Descendant basically means for some node, such as this one, a descendant of this node would basically be any child or any other node that comes beneath that one. So basically for the root node over here, every node in the tree is a descendant of that node. And it's also worth mentioning that another keyword used is ancestor, which is straightforward, just like descendant. It would mean that this node, any node that came basically in the parent chain of this node. So this is the parent node, this is sort of the grandparent, and basically any node going up that chain would be considered an ancestor of the original node. This node doesn't really have any ancestors because it doesn't have any parents, but it does have a bunch of descendants. But going back to what we were talking about, the height of this node is starting from this node going to its lowest descendant, which in this case it only has a single descendant. What's the length of the path? Or in other words, what's the number of nodes starting from here going to its lowest descendant? Well, we can count 2 nodes, so we say the height of this node is equal to 2. Can you tell me what would be the height of this node? Well, we could go down to the right. This forms a path of 2. That's the longest path we can form going on the right side. On the left side, we can form this path, which has 3 nodes in it. Clearly, 3 is bigger than 2, so we say the height of this node is equal to 3. I do want to mention that in some cases, people measure the height of a single node to be 0. So that would mean the height of this node is equal to 0. That would mean the height of this node, which we said was 2, would actually be measured to be 1. I don't prefer that way of calculating the height, but I just want to mention that sometimes in some textbooks and courses, people do that. So don't be too surprised if you see it, but the important thing here is whether we start at 0 or start at 1, the important thing is how you would actually calculate it. And I've illustrated to you that starting at the node, the height would basically be measured by finding the longest path going down. We have the opposite concept of height, which is depth. So what would be the depth of the root node? Well, it's measured as the path from here to the root node, and this is the root node, so we could say that the depth of this node is 1 based on how I like to calculate it, but some people would say that the depth is 0. What about for this node? What's the depth of this node? Well, what's the path from here up to the root node? Well, it contains 2 nodes, so I would say that the depth of this is 2, but some people, instead of counting the nodes, they would count the pointers connecting the nodes together, and in that case, you could call it to be 1. What's the depth of this node? Again, it's going to be the way I calculate it. It would be 2 because we have 2 nodes here. What about the depth of this? Well, it's going to be 1, 2, 3. So the depth of that node is 3 because that's the path from this node up to the root. So these are a lot of the key concepts that can come up when talking about binary trees. So I wanted to introduce you to some of the basics. So it wouldn't be complete if we didn't at least talk a little bit about the code. For now, I'm just going to cover the general structure of a tree node. It's pretty similar to a linked list node where we have a few properties. One is going to be the value. In this case, it's an integer, but it could be anything else. And also, we're going to have a couple pointers, which could be different based on the language that you're using. But in general, they're going to point at a couple tree nodes, the left and right child. Initially, they could be set to null. And to add a child node, you would simply reassign this to the child tree node. And generally, when you create a tree node, you want to, at the very least, initialize whatever the value happens to be. So the value for this tree node, of course, is 2. The left pointer is pointing at this node. The right pointer is pointing at this node. So now we have a decent understanding of the basics of binary trees. Next, let's talk about a special type of binary tree, which is called a binary search tree, or BST for short. Binary search trees are pretty much exactly like binary trees, except they have a certain sorted property to them. They're not literally sorted like an array would be, but they have a sorted property which actually allows us to use them similar to how we used a sorted array, especially when we were doing that binary search algorithm, which is sort of why these are called binary search trees. So what is that sorted property? Well, it's very simple. For every single node in the tree, the guarantee of BSTs is that every single node in the left subtree, we call this a subtree. This entire thing is the BST, but this is a subtree. Everything in the left subtree has to be less than the root value, and every single node in the right subtree has to be greater than the root value. Now, what about the case where there's equal values? What if instead of this being a 3, it was actually a 2? Well, generally speaking, binary search trees do not contain duplicates, so we don't have to worry about that case. So when we're talking about the left subtree having values that are strictly less than 2, and we're talking about values in the right subtree having values that are strictly greater than 2. But what about this tree? Is this a binary search tree? Well, every value in the right subtree is greater. 3 is greater than 2. What about the left subtree? 1 is less than 2. 4 is not less than 2. 4 is in the wrong spot. Can you tell me where the 4 should actually go? Well, first of all, it has to go in the right subtree. Okay, but where should we insert it now? Now we're at the 3 node. I mean, I guess the 4 could either go here or it could go here. Let's put it over here. Does this satisfy the requirement of a binary search tree? Well, 4 is greater than 2 and it's in the right subtree. Should that be enough? No, it's not, because the definition of a binary search tree is actually recursive, which means that the sorted property is not only true for the root node, it's true for every single node in the tree. In other words, it applies not only to the tree, but also to every single subtree as well. So we call that recursive because from the perspective of this node, this is its own tree. We call it a subtree because we know it does have a parent, but this is essentially the exact same as any other binary search tree. It should have the same properties. It has to be sorted. So when we look at this node, we check, are all the values in the right subtree greater than 3? Well, it doesn't have any right children. What about the left subtree? Are all values here less than 3? It's not true. 4 is not less than 3. So we can't put the 4 over here. We have to put it over here. Now you might be wondering why. Why do we care about having a sorted property with this data structure? What does it achieve for us? Well, pretty much exactly the same thing as having a sorted array. With a sorted array, when we need to search for a value, we can do it in log n time. If the array was not sorted, we would have to look at every individual element, so we would have to search for a value that we're looking for in O of n time. But with sorting, we can do it more efficiently. The exact same thing is true for binary search trees. If it didn't have a sorted property, we would have to look at every single node to find some target value. But with the sorted property, we don't. We can follow the same logic as binary search. Suppose we're looking for a target value of 5 in this case. We start at the root. We're looking for 5. Is this 5? No, it's 2. Okay, so we didn't find the target. But is our target greater than 2 or is it less than 2? Well, it's 5, so it's greater than 2. So this wasn't the target, but now tell me, which direction are we going to look? Are we going to go left or are we going to go right? Well, we know with binary search trees, all values greater than 2 are going to be on the right side. So if 5 exists, it must be somewhere over here. So by making that comparison, we not only eliminated this value, but we also eliminated everything in the left subtree. In this case, it's only one value, but it could have been a bunch of nodes. And by doing a single comparison, we eliminated roughly half of the possibilities. And then we would continue. Now we would look at the right child here, and we would do the same exact comparison. this is not equal to 5, but is 5 greater than 3 or less than 3? It's greater than 3, so we're going to go look to the right. We would have eliminated anything on the left, but there isn't anything here anyway. So now we're at pretty much the last node. Is this equal to 5? It's not. 5 is greater than 4, so we're going to go down to the right. But at this point, we reach null. There's no more nodes left that are greater than 4. So basically, we did not find the target that we were looking for. So let's say we were returning true or false, whether we find the target. In this case, we didn't find the target, so maybe we would return false. If we do find the target, we could return true. So that's the idea, and it's pretty simple when you're looking at a picture for how to perform this search algorithm. Now let's take a look at the code. Since binary trees are recursive in nature, meaning a subtree has the exact same structure as the entire tree, we can expect to use a recursive algorithm to traverse it and to search for values in it. Now, it's not required to use recursion, actually. There are other ways to do this, but the easiest way by far is recursion once you can get familiar with it, which is why we talked about recursion earlier in the course. Now, even though this data structure has two branches, right? It has left and right children. To search along a binary tree is actually one branch recursion. The reason is when we get to a node, we do our comparison based on whatever the target value happens to be, and we only go in one direction. We're going to recursively either go along the left subtree or the right subtree. There's no need to do both with binary search trees. That's the efficient part. Let's suppose our target was 3 in this case. You can see the search function is going to take the root of some binary tree and some target value. We're going to search for that target value. And let's start with the base case, which is the simplest one, but it's the one that we're going to reach lastly, of course. We saw in the previous example where we were searching for a 5, we started here, then we got here, and then we got here, and then we went to the right child of this node, but that's when we reached the null case. So in general, if the root node is equal to null, we're going to return false because that means we ran out of nodes to search and we didn't find the target, so we can return false. But if that's not the case, that means we have a valid node. Let's assume we started at the root. We're at this node currently. We're going to do a few comparisons that might look very similar to the binary search comparisons we were doing earlier. We're going to check, is our target greater than the root value, or is it less than the root value? Or if it's not greater and it's not less, that must mean it's equal, so we can return true. So in this case, our target is 3, which is greater than 2. So what we're going to do is recursively call search. But where are we going to do it? Are we going to go to the left node or the right node? Or are we going to stay at the root? No, we're going to go to the right node. So we're going to pass in as the node root.right. We're going to run search on this child node. So this is the recursion part. This is the sub problem that we're going to run search on. First, we started with the whole tree. Now we know it's not that, but this is the sub problem now. So now, being at this node, we know that this is not a null node. We're still looking for 3. Is our target greater than 3? Nope. Is it less than 3? Nope. It's exactly equal. So at this point, we return true. But when we return true, this return call is going to go back up to the parent because remember, we're inside of a recursive call. So where did the parent call search on the child? Well, we remember it was this conditional where we called search on this node. Now we're going to return whatever the result of that was, whether it was true or false. In this case, it was true. So we're going to end up returning true from here, which means we're returning true from here. That means this entire tree does contain this target value. So what's the time complexity of performing this search? Well, just like binary search, it's going to be log n. That's the benefit. But the asterisk with that is that it's only going to be log n if we have a binary tree that's roughly balanced, because our assumption is when we get to a node and we choose either to go left or go right, as we do that, we're eliminating half of the possibilities every single time, half of the remaining possibilities. So from here, we would eliminate half of the possibilities and continue doing that. But we can only do that if the tree is roughly balanced. When we say balanced, that means for every single subtree, including the root tree, the heights of the left and right subtrees are roughly equal, meaning that they differ by maybe 1. That would be a perfectly balanced tree. In this case, this tree is balanced because the height of the left subtree here is 1, the height of the right subtree is 2, so they differ by only 1. What about the left and right subtree of this node? Well, it's 0 here and 0 here, so they differ by 0. What about this node? The height of the left subtree is 0, the height of the right subtree is 1, so the difference is 1. And lastly, for this leaf node, again, the heights of the left and right subtrees are 0, so the difference is 0. So this is a balanced tree. But we might not have a balanced tree. What if we didn't have this node and we just had a big string of nodes going like this? Well, this is essentially a linked list, and we could have values like 5 and 6. While this is sorted, the way our binary search is going to run, we can't just go halfway in between all of these nodes. We're going to start here, say, okay, our target is too big, go here, maybe our target is too big again, and it could just keep going like that. And in this case, clearly, we're not eliminating half of the possibilities every single time. So if the tree is like this, where it's not balanced, the search algorithm in the worst case would be big O of n. But the reason we have binary search trees is to have balanced binary search trees. And it's usually assumed that if you're working with one, you do have a balanced tree, which would usually be log n. But in terms of technicalities, a lot of people will say the time complexity of running search is going to be big O of h, where h is the height of the tree, which makes sense. Because for an imbalanced BST, the height would be n, because we just have a string of nodes like this. But for a balanced tree, the height would be log n for similar reasons we talked about earlier in the course, especially when it comes to merge sort, right? We know this is being multiplied by 2 every single time. So then the height of that would be log n. So this was definitely a lot to take in, but there's one last question I want to answer for you, and that is, why do we have binary search trees if we can already have sorted arrays? If we already have sorted arrays which we can run binary search on, we can already search for values in log n time. So why create all this complexity to create a complicated data structure just to achieve the exact same thing? Well, the downside of having sorted arrays is if you want to add values to the array and remove values from the array and keep the sorted property of that, well, we know removing from an array in the worst case is going to be big O of n, because even if we can find the value really quickly, we still have to then maybe shift over every single value in the array. And if we want to add a value, like if we wanted to add a value over here, then we would have to take all of these and then shift them over by 1. So when it comes to inserting and deleting from an array, it's always going to be big O of n, whether it's sorted or not. But that's not true for binary search trees. With binary search trees, inserting values and deleting values can also be log n. That's what we're going to talk about next. And that's the main benefit of binary search trees. So we talked about how the main benefit of binary search trees over sorted arrays is that we can insert and remove in log n time, assuming the tree is roughly balanced, in which case the height of the tree would be roughly equal to log n. So inserting is going to basically traverse the height of the tree. Let me show you how it's going to work. Let's assume we call insert on our tree over here, and assuming this is the root, let's say we call insert on the root node of this tree with the value 6. That means we're going to insert a new node into this tree with the value 6. So we start at the root. Really, we just need to find which position we're going to insert the node at. Now, technically, there are two ways we could do this. There are two valid BSTs that could be the result. We could have a 6 as the new root node and then have a 4 as the left child of the 6. Because remember, all values in the left subtree should be less than the root node. All values in the right subtree should be greater than the root node. This satisfies that. Or we could have this, where 6 is actually the child. Now, we prefer to do it this way because it's easier to insert a node as a leaf node. In this case, we can do it just like this. And you'll see what I mean as we add even more nodes into the tree. But it's usually easier to add nodes as leaf nodes. So what we're going to do here is we're going to start at the root and we're going to keep traversing the tree pretty much the exact same as we did when we were searching for a value. So essentially we're going to be searching for 6, but we know duplicates don't typically exist in a binary search tree. And if they did in this case, we wouldn't want to insert another 6 anyway. But at this point, we're going to compare, is 6 greater than 4 or is it less than 4? It's greater. So we're going to go down to the right. Now we reach null. There's no more nodes here anyway. So what we're going to do is essentially create a new node over here with the value 6. And then we would take that node and return it up to the parent. And what the parent would essentially do is reassign its right pointer equal to the result that we returned. We'll take a closer look at that when we look at the code, but for now, let's insert a few more nodes. Next, let's insert a 5. So we start at the root again. We compare, is 5 greater than this or less than it? It's greater, so we're going to go down to the right subtree. We have another node, is 5 greater than this or less than this? It's less than it, so we go to the left subtree and there's nothing there. So now we can actually create that node with the value 5. And of course, we're going to end up returning to the parent where the parent is going to assign its left pointer now to this node. That's how we're going to connect them together. This example does a better job of illustrating why we insert at leaf positions rather than in the middle. Because here, if now we wanted to, add a 5, possibly as the root node, what we'd have to do is, create the 5, connect its right pointer to 6, and connect its left pointer over to 4. Now, this is actually the preferred way of doing this, because notice how this tree is more balanced than this one. But there are implementations where you can implement a balanced binary search tree where the insert and remove operations result in a balanced tree. There's a couple advanced data structures that can implement that. One is called the AVL tree, which I cover in my advanced algorithms course. But for now, we're just going to focus on the simple cases of just inserting and removing, because removing is actually going to be a little more complicated than you think. So taking a quick look at the code, you can see it is very similar to searching, where we're passed in a node, which is the root of the tree, and we're passed in a value. Instead of searching, though, we're going to be inserting this value. The base case is, again, if we reach a null node, but instead of returning null, we're actually, in that case, going to create the node and then return that node. So suppose, instead of this tree, we actually had an empty tree. Like for root, we were passed in null. Then this insert would actually return the new tree after, creating a single node. So, something like this where we were pointing at null, we call this, we end up creating a node with some value and then return that node. But normally we'd be inserting into an existing tree. If we don't reach the base case, suppose we were actually inserting the 7 right now. So let's say our pointer is here. In this case, we're not at null. We check, is our value greater than the root value? It is. So we call insert on the right subtree with the exact same value. We're still inserting a 7, but now we are going to check in the right subtree. And then once we've done that insertion, we're going to end up returning that tree with the 7 inserted. And then that tree is going to be assigned to the right pointer. So we'll have to see what happens with that. But for now, our right pointer is going to be down over here. We're in a recursive call now. So we called the function again. We're not in the base case. This is not null. We check, is our value greater than 6? It is. So we execute this again. So we're going to call insert on the right subtree over here and then return the result of that and assign it to the right pointer of this node. So here we actually do reach the base case. We're in another recursive call. We're at a null node. We create a node with the value 7. It's not connected to anything just yet, but then we return it. And remember, this is where we called insert from when we were at this node. So we're going to take that node, that's what we returned, and then assign it to the right pointer of this node. So I'm just going to redraw this over here. And now we're at the perspective of this 6th node, and this if just executed. So now we're done with that. And this is the else if is also not going to execute now. Only one of these is going to execute. And then we're going to return the node, which we're currently at. That's what root is at the current node that we're at. So this 6, we're going to return the node itself and then assign it to the right child of this node, because that's where that recursive call was made as well. But we know that that assignment already exists. So in this case, it didn't do anything. But if we, ended up inserting the 7 right over here, that's where that would have been useful. So that's the idea of inserting. We didn't cover the else if case, which is basically if we were inserting in the left subtree. So for example, if we were inserting the value 2, we would start at the root. We're not at null. A 2 is not greater than 4, but it's less than 4, so we'd call insert. Then we'd make another recursive call, execute the base case, create a node 2, return that node, and then over here, instead of assigning it to the right pointer, we'd assign it to the left pointer of 4, and after that, we would return the root, this node. So that's basically how it works, pretty similar to searching. Now, the time complexity is also the exact same as searching, because notice how we're not, as we iterate through the tree, we're either going to go left or go right. We're not going to go both ways. So we're basically, in the worst case, going to go visit one node for every level in the tree as we keep going down. So again, the time complexity is going to be the height of the tree, which usually is log n if we have a balanced tree. So now let's talk about the more difficult algorithm, which is removing a node. But before we even do that, let's talk about how we can find the minimum of the tree, because we're actually going to need that in our remove function. But the good thing is that finding the minimum is pretty straightforward. Just like with an array, a sorted array, the smallest element is not going to be in the middle or at the right. It's going to be all the way at the left, assuming we have it sorted in ascending order. The same is true for a tree. We know the recursive property, all values greater are going to go to the right side, all values less are going to go to the left. So of course, we're going to go to the left. And from here, the same property is true. All values greater are on the right, all values less are on the left. So if we keep going down to the left, we will arrive at the minimum. So to take a quick look at the code, we get something like this, at least in Python, but obviously it would be similar in most languages. We're passed in some node. We want to find the minimum node. We could return the value itself, or we could return the node. In this case, we're going to return the node because that's what we're going to need in our remove function. But you're given a node, let's assign some variable to that node. We don't have to do that. We could use the parameter variable itself, but either way, we have some pointers, suppose at the root node, while our pointer is not null and the left pointer is not null, we are going to go to the left. So from here, we satisfy that condition, we go down to the left. Here, we satisfy that condition, we go down to the left. Now, in this case, current is non-null, but the left pointer is null. So we're not going to continue. That means there aren't any nodes that are smaller. So here we're going to stop, and here we're going to return. You can see that this isn't even a recursive function because there's no need for it to be recursive. Because as we go in one direction, we're essentially traversing a linked list, and we know that it doesn't take recursion to do that. So when it actually comes to removing a node, we break it up into two cases. The easy case is case 1, where the node that we're removing either has 0 children, like this node or this node or this node, or it has just one child. For example, this node only has a left child. The more difficult case is when we're removing a node that actually has 2 children. For example, this node has 2 children, and this node also has 2 children, and its children even have children, so that could definitely get complicated. But first, let's start with the simple case. So let's say we're removing the value 2. The call would be similar to the insert call, where we're given the root of some tree and some value that we're looking for to remove. Now in this case, it's also going to be similar to searching, because first, to remove the 2 value, which is over here, we have to search for it. We don't have to look through every node because we know we have a sorted property in the BST. So we start at the root. Is 2 greater than 4 or less than 4? It's less. So we go down to the left. Is 2 greater than 3 or less? It's less. So we go down to the left. Is 2 greater than 3 or less? It's not either. It's actually exactly equal. So we at least found the node. Now, how do we remove it? Well, similar to the insert call, from this subtree, we're expecting to remove the 2 node, and then we're going to return to the parent the new tree after we removed the 2 node. It could be here, it could be somewhere down here, or somewhere down here. We know in this case it's at this node. So after we remove this node, what would this subtree look like? It would basically be null. So that's what we're going to return to the parent. We're going to return null up to the parent, and then the parent node 3 is going to assign its left pointer to be at null. So this node is essentially not going to exist anymore. It's not going to be connected to the tree anymore. Now that was really simple because this node did not have any children. How about instead of removing the 2, we actually remove the 3? This is still case 1 because 3 only has a single child. Searching is going to go the same. We start at 4, 3 is less than 4, we go here, this is 3. So now what do we return? We can't return null because if we return null, then that's going to disconnect the 3 from the 4, but it's also going to disconnect the 2. So what we're going to do is check. Is one of my pointers null? Is the left pointer null or is the right pointer null? In this case, the right pointer is null. That means we have at most 1 child, so we can execute case 1. So since the right pointer is null, we're going to return the left child here. What that means is when we're not going to return this. We're going to essentially remove it. We're going to return the left child here. So then when we get back up to the parent, from 4, instead of having the pointer pointing at 3, this pointer is actually going to now point at the return value, which was this node. So that's essentially how we remove this node from the tree. And by the way, if this node actually didn't have a left child either, the code would execute the same. We would check we don't have a right pointer. Okay, then return the left pointer, which in this case happens to be null. So then we would return null back up to this parent, and then it would basically not have a left child anymore. That's the case if this node actually didn't exist. So you can see it works out the exact same whether we have 0 children or 1 child. Now for the difficult case where we are removing something like 6 where it has 2 children. So it's going to start the same. We start at 4, 6 is greater than 4, we go down to the right, we arrive at 6. Now we check, is our right pointer null? Nope. Is our left pointer null? Nope. So we don't have the simple case. So if we remove this node, it's going to disconnect everything from the 4, right? Like it's basically going to delete the entire subtree, which is not what we want to do. So what we can do to fix this, the easiest thing we can actually do is replace this node with one of its children or, one of its descendants. In this case, we can replace it with either node. We can replace it with 5 or 7. So what we would do is take the 6 here and replace it, suppose, with 7 from over here. And then what we would do is recursively call our remove function on the right subtree. Instead of 6 though, we would remove 7. And then once that removal is finished, assuming this node doesn't exist anymore, this is what our tree would look like, where the 6 is now replaced with a 7. The 6 is removed from the tree now. So that's the idea. And it looks really simple in this case, actually, because the children of this node are leave nodes. We can, just move one in here. But it would be a little more complicated if we were removing a 4. Let's look at that case. With 4, we can try the same idea, replace this with a value from its right subtree. Naively, let's try 6. Okay, we put the 6 over here, but now we have to replace the 6 with something. It works in that the 6 is greater than the 4, therefore it's going to be greater than everything in the left subtree of 4, so 6 can be over here, but 5 can't be in the right subtree of 6 because 5 is less than 6. That's what complicates this. That's why when we replace the 4 value here, it's best to replace it with a leaf node. But which leaf node should we replace it with? Well, if we're going to replace the 4 with some value from the right subtree, should we pick the largest value in that subtree or the smallest? Well, we have to choose the smallest value. We can take this 5 and put it over here, and this is still a valid binary search tree because the 5 was the smallest value. So now if it becomes the parent of all these nodes, it's going to satisfy the sorted property because all these nodes are greater than 5. So what we can do here is to replace this value, we can take the smallest value in the right subtree and do that. Now, technically, you could also take the largest value from the left subtree and replace it with that, and that would still work as well. If we take the largest value here, which in this case is 3, and put it over here, we know the sorted property is still going to be valid because we know since 3 was originally less than 4, it's also going to be less than all of these values. And since 3 was the largest in the left subtree, it's going to be greater than all of these values. Now, I'm going to decide to do it with the right subtree because it doesn't really matter. But you can see where this is coming, right? We wrote our find min function so that we could find the minimum in the right subtree. We also could have written a find max node function to find the max in the left subtree. Now, if finding the minimum is as easy as going all the way left, finding the maximum is as easy as going all the way to the right. So they're both easy algorithms to implement. So now to finally look at the code, let's actually walk through this with the example of removing 4. You can see we have our find min node. That's the exact same. Now with remove, we do have several cases. Let's say we're passed in the root node and the value is 4. We get here. We're not going to execute the base case because this is non-null. 4 is not greater than this value. 4 is not less than this value either. So we're not still searching for the value. We found the value, which is this else case. So now we're going to check, are we missing the left child? Nope. Are we missing the right child? Nope. So we can't execute the simple case where we have just a node with 0 or 1 child. In those cases, we would return whatever the non-null child is. So for example, with this node, both of its children are null. So we would end up returning root.right, which is null itself. That would end up deleting this node. For this node, we would check that root.right is null, so we would return the left node, which is here, so that would be the new child of 4. But we're not executing either of those simple cases. We're executing this else case for this node. It has 2 children. So what we're going to do is first find the minimum node from the right subtree, which is this node, and we're going to return it. So we're going to do a search, find this node, and then return it. And we're going to change the value of this node to the value from the minimum node. So this is now going to be a 5. The good thing about nodes is we can just change their values. And in this case, it turns out to be useful. Now, the last thing we're going to do, we know now we have 2 copies of this 5. So we actually have to now remove this 5. So recursively, we call the remove function again on this subtree and pass in the value 5. Now, the good thing here is since we found the minimum value from this subtree, we know that node was a leaf node. So we know that this remove, even though it's recursive, we might end up calling the same function within the function. We know that the second time we call it, it's going to be the simple case where actually this is not necessarily going to be a leaf node. It could have, a right child over here or something like that. But it's not going to have any left child for sure. That means at most it could have 1 child. Therefore, it'll be the simple case over here where we don't have to, make a recursive call. So let's actually run through that really quickly. So we're looking for the 5. 5 is less than 6. So we're going to go down here. Now we found 5, right? So it's not greater or less. We have the exact node. So if not root.left, in this case, it doesn't have a left child. So we return the right child, which in this case is null. But that's okay because we return null from here. So up to the parent 6, where we called this function root.left is equal to removing 5 from this subtree. We did that, so we end up returning null here. So the left child of 6 ends up becoming null. And then, of course, we would return this up to this parent, but that wouldn't change anything. These are still going to be connected. But you can see we removed 4 from the tree. We moved the 5 up here, replacing the 4. Now, this case that we just talked about right now was actually the worst case time complexity because we had to find the node we're removing, which was pretty easy in this case. We found it immediately, but then we had to find the minimum of the tree, which we had to traverse the whole height of the tree, which let's say is log n in this case. And then after we did that, we replaced the 5, and then we had to remove 5. So we had to traverse the height of the tree again. So we had to do it twice. That's the worst case. We won't have to traverse the height more times than that because we know that the second time we remove a different node than we were originally removing, that's going to be the last time we remove a node because it's going to be a node with 1 or 0 children. So the worst case is we traverse the height twice. 2 is a constant, so the big O time complexity is log n. So this is the benefit of BSTs over sorted arrays. We can remove and insert in log n time. So when we have a sorted array, there are many times where we want to iterate through that sorted array, and we can do that pretty simply just by going left to right. It would be useful if we could do the same thing with a binary search tree. And actually we can. We can go through all the values in sorted order and then do whatever we want with them. But it's not going to be as simple as iterating through an array, but it is going to be as simple as going from left to right. What I mean is if we want to traverse through the entire tree and we want to do it in sorted order, we call that an in-order traversal. We want to go through the values in order. So like I said, we want to go left to right because starting at the root node, we know that the smallest values are going to be in the left subtree. So before we even process this value, we want to process the left subtree, the entire left subtree. And the same applies. This is a recursive definition. It's a recursive function to go through them in sorted order. So we go to the 3, and from here we know that all values smaller than the 3 are going to be in the left subtree. So we do that. Now from here we're going to do the same thing. We know all values smaller than 2 are going to be in the left subtree, but there aren't any values less than 2. So we are at the 2. Now what do we actually want to do with this value? Well, we could do anything we want. We could print it. We could add it to some output array. For now, let's just say that we're printing it, and I'm going to write them up here. But okay, we're going to go ahead and print the 2. Next, before we pop back up to the parent, there could be some values over here. In this case, there's not, but if there were, we would want to traverse the right subtree of this node right after we process the node itself because we know all values in the left subtree of the 3 are going to be less than it. So any values here are going to be greater than the 2 and less than the 3. In this case, there aren't any, so we don't have to do anything. But we pop back up to our parent, and from here, we know we just processed the whole left subtree. So now let's process this node, the 3, and then let's do its right subtree. Well, it doesn't have one. So same thing. We go back up to the parent. We process this node because we just did the whole left subtree. So 4, we print it. And now it's time to recursively do the right subtree. In this case, we actually have a right subtree for us to traverse. And of course, we know all values here are greater than all the values we printed so far. You can tell that just by looking at it. So now let's start at the 6, but before we can print the 6, let's recursively traverse its left subtree. We get to 5. Before we print 5, let's recursively traverse its left subtree. We get to null. That's going to be the base case of our recursion. So now it's time to print 5 because we just did its left subtree. Now it's time to do the right subtree of 5. It doesn't have one. That's the base case. Then we can return back up to our parent, 6. We just did the whole left subtree of 6, so let's print 6. And now let's recursively do the right subtree of 6. It does have one, so we get to 7. Let's do its left subtree. It doesn't have one. Then let's do this value, 7. and then let's do its right subtree. It doesn't have one. But notice how for every node we went left, then we did the current node, and then we went right. So it is similar to going through an array in sorted order. We are kind of going left to right. It's just different. We're doing pointers and we're doing recursion. Now, even though this is kind of complicated to understand, especially if you're a beginner, it took me a while to understand this the first time I learned about it. The good thing is that the code is really, really simple. Let's take a look. So in-order traversal is another recursive function. We're given some root node like this one, and the base case is similar. If the current node that we're at is null, then we can simply return. There's nothing for us to traverse. That would be the base case when we go down here, or when we go down here, or the right child of here, or of course here, 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 and here. The recursive case though is where we want to run in-order traversal on the left subtree first. So we recursively go to the entire left subtree, and then from here we do the same thing. We go to its left subtree, and then from here we do the same thing. We go to its left subtree, which ends up being null, so we return. And then from this node too, after we've done its entire left subtree, we print the node itself. We print 2, and then we run in order traversal on its right subtree. That's the base case. It's null, so then we're done with that subtree. We're back up to 3. We just processed its left subtree, so now let's print 3 and then do its right subtree. It doesn't have one over here, so you probably get the idea. At this point we go to 4. We've already done its left subtree, so now print 4 and then do the entire right subtree. So recursively we would do the exact same thing here. Now, what's the time complexity of doing this? Well, in the worst case, and pretty much every case, we're gonna have to traverse the entire tree. So we visit every single node once, and that makes the time complexity the size of the tree. So it is big O of n, the same as if we were traversing through a sorted array. There's no way to get around this. I mean, we have to go to every single node. It can't possibly be less than big O of n. But you might have noticed something. If we were given some random values, like we were given these values, but we weren't given them in sorted order, we were just given them in some arbitrary order, we could sort them using a binary search tree and then get a sorted array. So instead of printing each value, we could have taken each value and added it to some array. What would the time complexity of that be? Well, first, if we were given these values, we would have to build a binary search tree. So for every value, we would have to insert it into the search tree. And we know an insertion into a binary search tree is big O log n for a balanced tree at least, which is what we're assuming. And we would have to do that for all n values. So n times log n would be the time complexity of building the entire tree itself. And then to traverse it, to build, the output array in sorted order, we would have to do big O of n from this in order traversal. So the time complexity would be n log n plus n. So we can write the time complexity like this. But remember how I said that any constants are ignored? Like for example, if we had 2 times n log n, we wouldn't care about the 2. And by the way, in terms of math, this is equivalent to saying n log n plus n log n, right? That's the same as 2 times something. It's just adding it together twice. Now, obviously, n log n is going to be greater than n itself, right? As n increases, as it becomes a really big number, of course, this is going to grow faster than n itself. So therefore, this equation down here is larger than this equation up here. And we know that this is equivalent to this, and we know that this reduces to just n log n because we can get rid of the constant. So what I'm saying here is when we have added terms where both have variables in them, we only care about the larger one. We don't care about n here because this is going to be less than 2 times n log n, and we know that that reduces to just n log n. So when we have something like this, we only care about the larger term. So in this case, we wouldn't even care about the n. This is dominated, the time complexity is dominated by the larger term, which is n log n. So basically, what we found here is that to be given some random values and to sort them using a binary search tree, it takes n log n, which is similar to some of the other sorting algorithms that we talked about, like merge sort and quicksort. So sorting, as you can see, is really not going away. I told you that there were a lot more sorting algorithms that you might have thought, and there are a lot more, including some that we're not even going to cover in this course. There's just a ton of sorting algorithms. Now, if you actually want to go through the values in order, which is usually the most common thing with binary search trees, this is the way to do it. But there are some cases where for a tree, and it could be a binary search tree or it could just be a generic binary tree, there are some cases where we would want to visit the root node and then visit its children and do that recursively. So by the time we get to this node, we want to visit this or print it or add it to some array or do something with it before we do anything with its children. We call that pre-order traversal. So let me ask you, if we wanted to traverse this tree such that we visit for, we print for, and then we print its entire left subtree, and then we print its entire right subtree, aka pre-order traversal, how would you augment this in order function that we have over here? The good thing is we don't have to change much. We just have to swap the order of these two lines over here. Instead of going through the entire left subtree before we print the 4, we just print it before we go through its left subtree, and then we go through its right subtree. So to make it more clear, this is exactly what that code would look like, printing it before we run pre-order on the left and then we run pre-order on the right. Otherwise, it's the exact same base case, the exact same parameters. Now there's the other case, which we call post-order traversal, which is the opposite. So if we wanted to, for this node, traverse all the values in the left subtree and then traverse all the values in the right subtree and only then print the root node, we would recursively run post-order traversal on the left and post-order traversal on the right and then print the value. So these three functions are very, very similar. We just swap kind of the ordering the way that we do the traversal. That's kind of the nice thing about doing this recursively. It's hard at first to wrap your head around recursion, which is why I've really tried to emphasize it throughout the entire course. But once you do understand it, things can become really, really simple. So we got in order, pre-order, and post-order. By the way, we could do reverse order as well. Do you know how we could augment this? What I mean is we printed the values in order. We got 2, 3, 4, 5, 6, 7. But what if we wanted to do the opposite? We wanted 7, 6, 5, 4, 3, 2. How could we do that? Well, if we want to get the largest value first, when we arrive at the root node, we should probably go to the right subtree and then print 4 and then go to the left subtree. So then we get to the 6. We should probably go to the right subtree before we do 6. So let's get down here. We should probably go to the right subtree first. There's nothing there. Then we print the 7 and then we print the left subtree. There's nothing there. And then we get back to 6, print 6, and then we do the left subtree, 5, print 5, and then we're at 4, print 4, and then we go here. We would print 3, go to its right subtree, there's nothing there, and then print 2. So that's how we would do it in reverse order. How would you augment the code to do that? Pretty much just swap these two lines. So instead of doing the left subtree first, we want to do the right subtree first, and then print the value, and then print the left subtree. By the way, for all these traversals, pretty much every way that you can traverse the entire tree, the time complexity is going to be big O of n. Now, believe it or not, we just talked about probably the most common algorithm when it comes to coding interviews, and one of the most common algorithms in general. It's called depth first search, aka DFS for short. All three of these recursive functions are examples of DFS. And it's pretty much like the name implies. As we search, we go depth first. So for example, we start at this node and we go in one direction. We could go in the left or we could go to the right. We could process this first and then go to the left subtree, or we could process this after. But either way, it's a traversal. We're going as far deep as we can first. We're not going to, do this node and then do this node and then this, and this. We're going to go as far deep as we can in the left subtree before we go into the right subtree. So we go here, we go to the left, we're going deep as we can down here now, right? In this subtree here, we're going to go as deep as we can. We go to the left node again. Here, we're going to go as deep as we can. This is what we did first. This is the first thing we did. We reached the bottom of the tree. We went depth first. We got to the bottom of the tree. This is the first thing that we did. We went as far deep as we could in one direction before we even visited any other node. And obviously the tree could have been even larger, but you probably get the idea. And we would have done that with all of these functions, whether they go in the left subtree first or the right subtree, whether we process the first node before or after, it doesn't matter. We go deep first and we pop back up again, and then we get here, and then we recursively run DFS on the right subtree. We go as deep, we starting from 6, we go as deep as we can. We go to the left child here, 5, and then we keep going. There aren't any children, but we did the same thing. We went as deep as we could, and now we pop back up to 6, and then we go as deep as we can in the right subtree. There's only a single node, but you get the idea, right? We're going depth first. So imagine for every leaf node, we're going as deep as we can for every single leaf node first individually. Now, it's hard to understand DFS without understanding an alternative way. I kind of glossed over it a second ago. The opposite of DFS would be breadth first search, aka BFS, and for that, we would go layer by layer. We would go the first layer, just this node itself. Then we would do, this node and this node. We would do this entire layer, and then we would do this entire layer. This is clearly not depth first search because we're not reaching the bottom immediately. We're kind of going, like this. And breadth first search is actually what we're going to start talking about up next. So next, let's talk about breadth first search, or BFS for short. And just like DFS, this actually doesn't necessarily need to be applied to a binary search tree. It could be applied to any tree, whether it has that sorted property or not. But the idea here is that we want to traverse this tree layer by layer. So breadth first, meaning we want all the closest nodes first, and then we want the next layer of the closest nodes and then continue doing that. We don't want to go depth first, right? We don't want to, go all the way to the bottom before we traverse the closest ones. We want to do it the opposite way. We want to do this layer. And typically what we do with breadth first search is we go left to right, but you don't necessarily have to do that. But for trees, it usually makes sense to go left to right. So traversing this, and let's say we're printing each value, we would have the first node, the root node, we would print 4, and then we would go to the next layer. How would we do it? Well, if we're going left to right, we should go to the left child first. So from here, we print 3, and then we do the right child. So from here, we print 6. Now, if we print 6 after we print 3, how are we going to get to this node? Because now for our breadth first search, we want to do this next level. We want to do 2, then 5, then 7. So how are we even going to get to the 2? I mean, assuming we had a pointer here when we were at 3, next we're going to have a pointer here when we're at 6, we kind of have to save that pointer. So this algorithm actually doesn't really suit recursion very well, because it's not like we're going to recursively traverse this and then recursively traverse this to get that breadth first search. So we're going to have to do this iteratively, but let's continue. Next, we would want to traverse 2. How do we know we want to traverse 2? Well, we're going to traverse all the children of this node. Just like before, first we processed 4, and then we processed all of its children. Next, we processed 3 and 6, and now we want to process all the children of these nodes from left to right. So we get all the children of 3 and then print them. So we get 2, then we get all the children of 6, and then we print them. So we get 5, and then we get 7. Now this didn't, create anything super useful for us. We didn't print it in order or anything, but BFS is definitely a useful algorithm to know. It could also be called level order traversal because we're going level by level in this tree. So the code for it is going to be pretty interesting. Remember how I said that as we process a node, after that we want to process the children of that node from left to right. And then as we process, another level or another node here, we want to process its children from left to right and then process its children from left to right. So as we go through every node and process it, we should take the children of that node and add it to some data structure to remind us to next process these nodes, and then next process these nodes, and then next process these nodes. Well, there aren't any more nodes here for us to process, so that's how we know we can stop. What kind of data structure can we use? Well, actually, we've already implemented the data structure that we need, and it's called a queue, because we're going to add these elements first in, first out. So if after processing this, we add its children in the order left to right, we add the 3 and then the 6, those are added to our queue, we're going to process these first in, first out. We're going to process the 3 and then we're going to add its children to the queue. So at this point, we would have a 6 and a 3 in our queue. We're gonna do it first in, first out. Since the 6 was added first, we want to process it first, and that makes sense because we want to finish this entire level before we get to the next level. Let's take a look at what the code for this would look like. So this is the Python code, but it would be very similar in other languages. The idea is that we're going to use a queue. In this case, in Python, it's called a deck, which is a double-ended queue. But it's basically the same queue that we implemented earlier in the course. So we have a queue. For our BFS, we're given the root of some tree. Now, of course, it could be empty, in which case we're not going to add anything to our queue. But in this case, suppose we were given this node. That would mean we added this node, not the value, but the node itself to the queue. So as of now, our queue has a single element, this node. In this case, suppose we actually wanted to count the levels as well. Like as we print these values, we say this is level 0, this is level 1, this is level 2, etc. We don't have to do it that way. It would be simpler if we didn't need to do it that way, but let's do it like this because sometimes this can be more useful and this requires a couple extra lines of code. So it's a little bit more complex, which is why I'm showing it. But here, we're at level 0. Is the length of our queue greater than 0? Well, this is our queue right now, so it is greater than 0. We can print the level now, so level 0, and then we're going to print every node in the 0th level. There's only going to be one node in the 0th level because there's only one root node for every tree. So from our queue, we're going to pop. In Python, it's called pop left. But you can just kind of imagine this is what the queue looks like. We add elements like this. So we're adding to the right and we're popping from the left. This is just our standard queue pop. We're popping from the opposite side that we're pushing. So it's first in, first out. So we pop the node 4, we get it, we print the value of it, then we check its left and right children. We want to take its children and add them to the queue. But if its left child is null, we don't want to add it to the queue. So we check, is the left child non-null? Yes, it is. So we add it to the queue. It's important to add the left child before the right child if you want to traverse them, if you want to traverse each level like this. Of course, we could do it the opposite way if we really wanted to, but usually it's more common to do left from right. So we add the left to the queue, then we add the right child to the queue because it's also non-null. So this is what our queue looks like so far. We've printed 4 so far. And at this point, actually, our inner loop is done executing because we took the length of the queue, which initially was 1. We just had a single value in it, and then we're finished. Now, we did add a couple more elements to the queue, but in this case, what this does is it takes a snapshot. So we just took an integer 1, and we had a loop that iterated 1 time because we only had 1 node. It's basically like we have a constant value here. Right? We only calculated the length of the queue a single time. So we did that, and now we finished this inner for loop. So we increment the level by 1, and then we go back to our outer while loop and check, is the length of the queue greater than 0? We have 2 elements in the queue, so it is greater than 0. So we print the next level, level 1, if we're starting at 0, and then we pop from the left of the queue. So we would pop the leftmost. Let's say this is the leftmost because we inserted it first. So we pop it, we print it, we check its children. It has a left child, so we add it to the queue. It does not have a right child, so we don't add it to the queue. So we've printed 4 and 3 so far. So our queue is going to look something like this. We first had the 4 on the queue, we popped it. Then we had the 3 and the 6 on the queue. We just popped the 3 and printed it. And we still have the 6 on the queue, and we just added the 2 to the queue. But we're going first in, first out. So next we're going to pop the 6. We pop this one. We print its value, we look at its left and right children. First, the left child, it's non-null, so we add it to the queue. By the way, I'm drawing it as the value, but in reality, in the queue, we would actually have the node itself, because when we pop the node, we want the pointer to the left and right child of that node. We wouldn't have that if we were only storing the value. It's important to store the actual node itself. So we do the same thing with the right child. It's non-null, so we add it to the queue. And at this point, we continue. So we pop the next node in the queue, which is 2. We can print 2. And 2 does not have any children, so we don't add anything to the queue. So you can kind of start to see how this is going to finish up. Now we pop the 5. We can print the 5. It's getting a little bit messy over here, but it's not so important, the values that we're printing themselves. It didn't have any children either. We pop the 7 next. It doesn't have any children. We will print the value or do something with it. And then this is our level order traversal. At this point, our queue is empty. So we stop, and that's gonna, in terms of code, gonna stop here. The length of our queue is not greater than 0, so we stop. By the time though we got to the last level, when we were here with a 2, 5, and 7, we would have taken the length of the queue to be 3. We would have executed this loop 3 times, popping a node each time, and we would have tried to add the children, but the children don't exist, so our queue at that point would have been empty. We would have gone back up to the outer while loop. The length of our queue is now empty, so we stop. So that's the idea behind breadth first search. Now, what's the time complexity? Well, people get really confused when they see nested loops. People automatically assume when you have nested loops that the time complexity is going to be n squared, but that's not the case here. And the simplest way to understand that is just by looking at what we did. You watched me go through this tree. We only traversed each node once, right? We printed each node once. We added it to the queue once, and then we popped it from the queue. So you could say for each node, we had, let's say, 2 operations. Technically, you could say we have 3 because we're printing the node, we're appending the node to the queue, and then we're popping it, but it doesn't matter. It's some constant c times n, where n is the number of nodes. So this is the number of operations we did. We know that reduces to big O of n. Don't worry so much about, the nested loops. Yes, we have nested loops, but clearly the total number of operations we're going to do is big O of n. So that's the time complexity. Just like any traversal, we visit every single node once, so just like DFS, the time complexity is going to be the size of the data structure that we're traversing, which is the number of nodes. I mentioned DFS is probably the most common algorithm you'll use. BFS is probably the second most, and maybe it is the most common. And we definitely have not seen the last of BFS. I'll tell you that much right now. I want to introduce a couple data structures to you, which are sets and maps, and that's because these 2 data structures are commonly implemented using binary search trees. So a set is pretty straightforward. It's some set of values, right? Like 1, 2, 3. It's pretty similar just to having like an array, but usually the word set implies that there's some other underlying data structure being used, not an array. One implementation could be a binary search tree. So if we have the values 1, 2, 3, but they're in a binary search tree, it could look something like this. And the advantage of having a set implemented with a binary search tree rather than like an array is that we can search for values, insert and remove values in log n time. So that's pretty straightforward. Now I also want to introduce to you the idea of a map. Let's first understand why it's important. Suppose we had something like a phone book where it's sorted in alphabetical order from A to Z, right? And that's based on the name of the person. Now, most people don't use phone books anymore, but I think it serves as a good example. So we have a bunch of names in the phone book, something like this. We could have Alice, Brad, Colin. Now notice these are in alphabetical order. But what's important here is that for every name, we don't just care about every single name. Every name is mapped to something else. That's where the word map comes from. In this case, every name is mapped to some number, some phone number. Let's just put 1, 2, 3 for simplicity. And, Brad could have some other number, 4, 5, 6. And then Colin could have something else. Now, the idea here is that we want to store all this information, but we want to sort by the name. But for every name, we want to have some other information. We call this a key value pairing. So we map a key to a value, and the data structure is typically sorted by the key. So in our case, when we had a binary tree, originally we had nodes that just had key values. That's our simple case where we have a set. But using a map, each node could have a key, which is what would decide how to structure the binary tree in terms of sorting it. But each node could also have an associated value, which in this case would be like a phone number. The value could even be its own object if we wanted it to be. Right? It could be multiple values. It could be, all the information about the person, their phone number, their social security, their email, a bunch of stuff. The idea, though, is that we're sorting by the key. So if we want to search for somebody in the phone book, it's efficient for us to do so by searching the names. We can do that in log n time because we know it's sorted by the name. But once we have that name, we have all the information about the person, aka the value. So this is one way of implementing sets and maps. Using binary search trees, we can implement sets and maps. So the binary search tree is the underlying data structure. It's similar to how we talked about stacks earlier. Stacks are kind of the interface or also the data structure we can push and pop, but underneath that, it's implemented with dynamic arrays. Similar to how queues are implemented with linked lists. Sometimes they can also be implemented with dynamic arrays as well. But sets and maps, they can be implemented with other data structures, which we'll be talking about later. One example is hash maps and hash sets, but like I said, we'll talk about that later. Depending on how you implement these, like which data structure you use, whether it's a BST or a hash map, there can be different trade-offs. We talked about the time complexities of binary search trees already. Now, depending on what language you're using, these can have different names, but for binary search trees, it's typically called an ordered set or a tree set. And for maps, it's called an ordered map or a tree map. And just to take a quick look at what it looks like in some common languages, the good thing about Java is it has a built-in tree map. So you can create a tree map where the key is a string and the value is a string. We could also use integers and other things as well. C++ also has native tree maps. They're just called maps in this case. The downside about Python and JavaScript, they don't really have native tree maps. You can install other packages. For example, in Python, you can use the sorted dict package, and this is essentially a tree map under the hood. For JavaScript, there are other packages as well, which implement tree maps. Now, in terms of real interviews, it's most common that you're actually implementing a tree map or running some algorithm on a tree map, like searching or inserting or something like that. It's not super common that you actually need a tree map, like the built-in tree map at least. But if you run into that case and you're using Python or JavaScript, most likely your interviewer will let you assume that some object or some interface like that already exists and you can use it, and you don't necessarily have to implement it from scratch if that's not what the problem is. Now, sometimes the interview question itself might be to implement, the data structure or parts of it from scratch. But what's most important is understanding what kind of interface a tree map would have. Like the things that we talked about. You can insert, you can remove, you can search, you can iterate, you can do the in-order traversal, and understanding the associated time complexities of those operations, which we talked about. So I think we've learned enough to understand the backtracking algorithm pattern. It's essentially based on the DFS algorithm that we already talked about. In this case, we're going to apply it to a binary tree, not a binary search tree, but just some regular binary tree. So it's going to be recursive, and the best way to understand it is to talk about an example. So let's look at one example question we could be asked. We're asked to determine if a path exists from the root of this tree to a leaf node, but the restriction here is that it may not contain any zeros. So we want to find a path from the root to any of these leaf nodes as long as the entire path does not contain any zeros. And let's say we can return true if that is the case, and if we can't, we return false. So obviously we're going to try this recursively. So we're going to start at the root node. What we want to verify is that this is not a zero, because obviously if the root node is a zero, there won't exist any paths from the root to any of the leaves that doesn't contain a zero. So in this case, 4 is not 0. So we're here so far. Let's try to check if there's a path that exists in the left side of the tree. So we get to the left child, it is a 0. We're not allowed to have any zeros. What we say in this case is we're backtracking. We tried one possibility, now we're going back up. The idea is similar to going through a maze. Let's say you start here and your goal is to get to the end of the maze. You go and try every path. You go this way, but then you realize that it's a dead end. So basically you backtrack and then try another route, another way to reach the end. So basically we're recursively trying every single path. It's kind of a brute force approach. We haven't talked about brute force yet, but it's a style of algorithm where basically you go through every single possibility. For example, with binary search trees, we know that to find a value that we're looking for, we can take advantage of the sorted order property. If we're looking for a value greater than 4, we would look in the right subtree. We wouldn't even consider the left subtree. But if we're given a binary tree, not a binary search tree, then we can't use that. We actually have to check both the left subtree and the right subtree. So we kind of have to brute force it in that case. So that's the idea behind backtracking. We have to go through every possibility. When you go through a maze, you have no idea which path could actually lead to the end. So you have to go through every possibility. In this case, even though there's a 7 down here, we can't go there because this is basically a roadblock. We can't go through any zeros. So we're not allowed to go this way. So in this case, we backtrack up. And now we're going to try the same thing in the right subtree. Recursively, we're going to go to the right child. It's a 1. That's good. It's not a 0. Unfortunately, this is not a leaf node, so we do have to continue. Now we try the left subtree. It's a 2. That's good. It's not a 0. And then it does not have any children, so that means we found the path. So from here, we didn't find the path, so we would have returned false. That's how the root node would know that we didn't find the answer in the left subtree. Let's try the right subtree. In this case, we did find the answer here. So what we're going to do is from this node, we're going to return true up to the parent over here. And then this node knows that since we already found the solution in the left subtree, we did find a path, there's no need to look in the right subtree anymore. So we don't even go in the right subtree. From here, we again return true up to our parent over here. And then from here, we end up returning true that yes, the answer to this question for this tree turned out to be true. Now suppose if we changed this node instead to a 0, we would have gotten here, we would have went to the left path, we would have found that no, this was not the answer, we returned false up to our parent here, so we would backtrack basically back up, try it from the right subtree, we would see that this is a 0, so this was not the path either. We ran out of options. We backtrack up, and then from here, we return false to our parent, and then from here, we would also return false. The answer to this question then would have been false not true. So the code for this solution would look something like this. You can see it's pretty similar to the other tree traversals, the recursive ones that we already looked at. So in this case, the base case would be if we reach a null node like empty, or we reach a node with the value 0. That means that, for example here, this would not contain a path that we're looking for. So in that case, what we do is return false. Now, if we get to a leaf node, that's another base case. So for example, if somehow we were able to reach this leaf node where we did not encounter any zeros, and at this point we would return true, but we know we can't get there because there's a 0 blocking us. But eventually we get to this node, we get to 2, it's a leaf node, and we know we got there without encountering any zeros, because if we encounter a 0, we have to return false. So if we ever get to this point where we reach a leaf node, we can return true. Otherwise, we are going to recursively check, suppose from the root, we would recursively check the left subtree and then check if that contains a path. And if it's true, then we can return true. If it's not, we don't do anything. We know in this case, the left subtree did not contain that, but we ran recursively. Can we reach a leaf node on the right subtree from here? And we know we did. Eventually, we went here and then we went here. That was the base case, we return true. So then from here, we end up returning true, and then that pops back all the way up to the root. And then from the root node itself, from the original function call, we can return true. Now, if this was a 0, for example, and none of these would execute to be true, we would return false. So now let's look at a slightly more complicated version of this same problem. Now, instead of just returning true or false, let's actually return what the values of that path would look like. For example, the solution here would be we have to build a path that looks like 4, 1, 2, because those are the values in this path. So the solution to that would just be slightly modified. So in this case, we'll call it leaf path. We're passing in our root, but we're also passing in another variable path, which in this case will be an array or a dynamic array. So it's sort of going to serve as a global variable for this function. It's basically going to be the same array that we pass in to every recursive call. So initially, let's say we have an empty array. We start at the root. The root is not null and it's not equal to 0, so we don't execute the base case where we return false. Now, we're still going to return true and false to indicate whether we found the path or not, because that's going to tell us whether we can stop looking or we should continue looking. For simplicity, let's assume that there's only one path from the root to a leaf node that's a valid path that doesn't contain any zeros. Because if we have multiple paths, then we get into the question of which one should we return. To keep it simple, we're going to assume only one path will exist at most. So maybe we'll have 0 paths or we'll have one path. In this case, we have one path. So we start at the root. We don't execute the base case. So what we're going to do to our path is we're going to push the value from the current node. So we're going to push the value 4. So assuming that this is our path so far, we're going to push the value 4. And by the way, I'm actually going to swap the two values of these two nodes because that's going to illustrate this algorithm a little bit better. So let me do that. Now, how the rest of the algorithm is going to execute, we're going to check, does this have any children? It does. So we don't execute this. We haven't reached a leaf node. We call recursively to check if there's a leaf path in the left subtree. We pass in the same path variable. Basically, we're not creating a new copy of this variable. We're just passing the exact same reference to this array into the recursive function. It works pretty much exactly the same in most languages. So we're at the left child, but here we know that the same base case is going to execute because the value is 0. So here we're going to return false. So we pop back up to our parent, we backtrack. So then from this 4 node where we checked if the left subtree contained that, this is going to be false. So we're not going to end up returning true just quite yet. We still have to build the path. So now we're going to be back here. We're going to recursively call a leaf path on the right subtree over here now. And actually, I realize I want to modify this tree a little bit more to actually illustrate the complete backtracking here. So what I'm going to do is change this to, let's say, a 3, and I'm going to add a right child, which is 0 here. So this will give us the full picture of this algorithm. But now we're at the 1. It's not null and it's not equal to 0. So we're going to consider it part of our path so far. So this 1 is going to be added to our path down here. We're going to check, is it a leaf node? Nope. Then recursively, we're going to check if a path exists in its left subtree. So then we're going to get down here to 3. We're going to continue the algorithm. It's not a base case. So we end up adding 3 to our path. So far, this is our path. We add the 3 down here. Now from this 3, it's also not a leaf node. We recursively check if we can find a path from the left subtree, but we see that the left child is null. So here we're going to return false. So from the left child, it didn't have a left child, so we returned false. So that means we didn't find a path yet. Then from this node, we're going to check its right child using this recursive call. And this is also going to return false because while this node is not null, the value is equal to 0. So from here, we return false up to our parent. So then this is going to evaluate to false over here. So we're not going to return true. Now, this is the interesting case. This is part of the backtracking. Since we originally were considering this path, we were checking, does this path lead to a solution? Now we know that none of the paths from 3 lead to a solution. So while we were building up our path, now we have to backtrack. We have to say we tried this path, but it didn't work for us. So we have to pop 3 from our array. And by the way, a dynamic array in this case is essentially being used as a stack for us because we're pushing to the array and we're popping from it. So we're essentially using it like a stack. But we're popping. This is important to backtracking. So then we recursively get up to this 1. We know that its left subtree did not lead to anything. Let's try the right subtree. So here we would call leaf path on its right subtree. We would get to 2. We would check, is it null or equal to 0? Nope. So then we're going to say to our path, let's append 2. So right now our path is 4, 1, 2. We removed the 3. That was very important for us to do because otherwise we would have gotten the wrong answer. At this point, after we append it, we check, is this a leaf node? It is a leaf node. It does not have any children. So at this point, we found our answer. This is the first time we're returning true. So we're going to return true. So we're going to return true from 2 back up to the parent over here. And from here, we know we were calling leaf path on the right subtree over here. And so since that evaluated to true, we can return true from there. And then all the way at the root node, we're going to execute this again, and it would return true. So then we did find the path. And in our path variable that we passed in, it would now be populated with the path that we were looking for, 4, 1, 2. So backtracking is an algorithm that can actually be used on more than just binary trees. It's similar to the recursive algorithms we talked about earlier, like the Fibonacci sequence, but understanding the fundamentals that we talked about here will serve as a really good foundation for understanding more complicated versions of backtracking. The ideas are the same, where you maintain some kind of solution, keep adding values to it as we're trying to search for a solution, but as we find out that we went down the wrong way, we pop from the solution then. By the way, in this case, since in the worst case we would have to traverse over the entire tree, the time complexity for both of the backtracking algorithms we talked about would be big O of n, where n is the size of the input tree. And that's usually the case for backtracking. It usually is a brute force algorithm, so it would, in the worst case, run over all possibilities. In this case, that means the size of the tree. Next, let's look at another really important data structure, which is called a heap/a priority queue. Let's start with kind of the meaning behind priority queue. We already talked about regular queues where first value in is the first value out of the queue. But we might want to order the queue a little bit differently. Instead of ordering it by the first in, first out, we could order it based on some type of priority value. For example, we add some values like 7, 3, 9. So now which value are we going to pop first? Well, it depends on the priority of the values. There's typically two variations of this. One is, the minimum priority and the other is the max. So in this case, we could prioritize the minimum values first. So if we did it like that, we would first want to pop the 3 and then pop the 7 and then pop the 9. Now this is dynamic, meaning as we add values, we might choose to pop a different one. Right now we want to pop the 9 if we pop a next value. But if we add a smaller value, suppose a 4, in that case, we're going to want to pop the 4 first and then pop the 9. That's if we did it based on minimum. Of course, we could do it based on the maximum as well. In that case, we'd do 9 first, then 7, and then 3. So the idea is actually pretty straightforward. Now, the reason we have two different names here is kind of the same idea. When we originally had queues, those queues were actually implemented with linked lists. So in this case, the relationship between these two terms is similar. The interface that we're using is called a priority queue, right? That's kind of the idea behind it. But underneath the hood, that's implemented using a heap. So people kind of use these two terms interchangeably. So you'll see that a lot. I'll probably be doing the same. And outside of this course, people use these generally interchangeably. I think it's more common to use the term heap, just probably because it's shorter, to be honest. But in this case, a priority queue is going to be implemented with a binary heap, which is this data structure that we have here. This is what we're going to talk about. And by the way, that heap, that binary heap, could either be a min heap or a max heap, depending on how we want to implement our priority queue, whether we care about minimums or maximums. I'm mainly going to be focusing on the minimum case. Generally, it's more common to use a min heap rather than a max heap. That's what this is here. But the implementation is pretty much exactly the same. It would just be swapped. It would, instead of taking minimums, we would take the maximums. I'll talk about that more now. Now, at first glance, this looks like a binary tree, and that's because it is a binary tree, but it's not a binary search tree, and you can tell because the root here is 14. With a binary search tree, every value in the right subtree would be larger than 14, which it is in this case, and every value in the left subtree would be smaller than 14, but that's definitely not the case. Actually, when you look at the root node here, it's smaller than every single descendant in the tree. That's going to be the order property that we talk about in a minute, but let's first start with the structure property. A binary heap is essentially a binary tree that is considered a complete binary tree. So a complete binary tree basically means we have a tree where every single level in the tree is going to be completely full. There's not going to be any holes anywhere except possibly the last level. The last level might have some holes, but every other level in the tree is not going to have holes. So you can see that requirement is satisfied in this case. Now, maybe if we're missing this node, it would not be the case because we're supposed to have 4 nodes in this level, but we only have 3. So if any of these 4 nodes is missing, we don't have a complete binary tree. If any of these 2 nodes are missing, we don't have a complete binary tree. Now, the last level here, we can have some missing nodes. That's perfectly okay. But if we insert a node over here now, regardless of the value, tell me, is the structure property satisfied? Definitely not, because while the last level has some missing nodes, that's okay. The second to last level now also has missing nodes. That's definitely not okay. Now, another thing about the structure property, as we add values, you can see they're added left to right. It's not enough that only the last level is allowed to have missing nodes. If it does have missing nodes, they should be at the end of that level, meaning that as we add nodes to it, like assuming that this level doesn't even exist, as we add nodes, we'd first add the node here and then add the node here and then add a node here, then here, then here, then here. So it's kind of intuitive that we want to have a complete binary tree, and as we add nodes, we're adding them in a pretty straightforward way, right? In the next available position, essentially. So that's the structure property. Next is the order property. Remember, the whole point about having this heap, aka priority queue, is about finding either the minimum or the maximum value really quickly, really easily. That's the entire point of having a priority queue. In this case, we're talking about minimums. So it makes sense that we would want the minimum value among all of these to be at the root, because from the priority queue, we want to be able to find the minimum easily. By looking at the root, we can do that pretty quickly. We can look at it in O of 1 time, as long as we're not removing this. So what order property should we give this to do that? Well, we should say recursively for this tree, we want every value in the left subtree to be greater than 14 and every value in the right subtree to also be greater than 14. That's the only requirement we have, but it's recursive. That means that for this subtree, for the root node of this subtree, we want every value in its left subtree to be greater than 19. That is the case, as you can see here. And we want every value in the right subtree to be greater than 19. That's also the case, as you can see here. Same thing for 16. 19 should be greater than 16. It is. 68 should be greater than 16. And technically, in heaps, we're actually allowed to have duplicates. You can see we have two 19s. So actually, when we look at this value, we don't necessarily need every value in the left and right subtree to be greater than the root node. It's okay if they're equal as well. That wasn't true for binary search trees, but it is true for heaps. We could have some duplicates, and that's okay. It's just that for every node, all the descendants have to be greater than or equal to that node. At least when you're talking about min heaps, which is what we're doing here. Obviously, for a max heap, we would want the opposite. We would want for every node, all of its descendants should be smaller than it, because in that case, we would want the maximum to be the root. Now, one of the most interesting things about binary heaps is that while we draw them as binary trees that are connected via pointers and nodes and all that, they're actually implemented under the hood using arrays. And another interesting thing is that we actually don't start at index 0 for this array. We essentially don't care about the 0th index, and I'll show you why. So what we're going to do is put the root node at index 1. That's always going to be the case. The root is always going to be at index 1. So we got the root node. Next, we fill in the next level. We go left to right. So for the 19, we're going to put it at index 2. For 16, we're going to put it at index 3. And we're just going to continue going like this. But one thing I want to point out is that we know the root is at index 1. To get its left child, we go to index 2. To get its right child, we go to index 3. Let's continue this, and then I'll show you what's the pattern behind it, and then we'll understand exactly why we use arrays rather than nodes and pointers. So filling in the next level, we have 21, which goes at index 4, 26, which goes at index 5, 19, which goes at index 6, and 68, which goes at index 7. And the last couple nodes we have 65 and 30. They're going to go in index 8 and index 9. So the main reason we skip index 0 is to get the math to work out. What do I mean by math? Well, for index 1, to get its left child, we basically have a few formulas. So for any node, so for 14, which is at index 1, to get its left child, we simply take the index that it's at and multiply by 2. So we know that its left child is going to be at index 2, which is 19. That is the case over here. We know its right child is going to be 2 times I plus 1. I in this case is 1, so 2 times that plus 1 is going to be over here. So just the next position over, 16 is its right child. And as we continue, so for 19, we want to get its left child. We multiply by 2, we get 21. that is the case. To get its right child, we multiply by 2 plus 1. That would land us over here. 26 is the right child. Now, these properties, by the way, are only true because we have a complete binary tree, which means every node is filled except possibly the last level. This would not be true for a regular binary tree or a regular binary search tree. That's why we use these for binary heaps, because they're complete binary trees. That's also why we can use this array to represent the binary tree. Because if we had holes and stuff over here, right, like this 26 doesn't exist, then it wouldn't really make any sense to use an array because we just have random holes everywhere using a regular binary tree. But with a binary heap like this one, we're never going to have holes. That's the entire point of having a complete binary tree. And by the way, if we can go from any node, multiply by 2 to get its left child, multiply by 2 plus 1 to get its right child, then from any node, we should also be able to go to its parent, and we can do that by dividing by 2. Now, it's pretty obvious why if we multiply by 2 here to get the child, we can divide by 2 to get to the parent. But why is that also true for the plus 1 case? If we multiply by 2 plus 1, we get to the child. And then if we divide that by 2, we get to the parent. Why is that the case? Well, pretty much because when we divide by 2, we round down. We know that this number is always going to be even. You know, we're multiplying some number by 2, so by definition, it has to be even. We know that this number is always going to be odd because we have an even number and we're adding 1 to it. This is the odd number, 9. When we take this and divide it by 2, we're essentially getting rid of this 2, so we're left with I plus 1, which is also divided by 2, and we know we always round down. Pretty much every language will round down automatically. With Python, you have to use double slashes, but we can still do that. And when you round down, this term is basically eliminated, and then we're left with a single I. That would be the exact same if we took this and divided it by 2. We would just get rid of this. We'd be left with a single I. So when you take 9, divide it by 2, you get 4.5. You can round that down. That leads us back to 4. So for example, if we wanted to, start at this node, we'd start at index 1. Suppose we want to go to the left. We would just take its index, multiply by 2. That would lead us over here in the array. Now, suppose from here, we wanted to actually go right. We would take the index, multiply by 2, which leads us to 4, plus 1, which leads us to 5. Then we'd be here, or here using the tree representation. And from here, maybe we want to go to the left child. So we take the index, multiply by 2. That leads us to 10. That's out of bounds because it's greater than the last index. Therefore, we reach null. So, it basically can be used the exact same as we traverse a regular tree. As long as you have these properties, you can traverse it as if these were pointers. So this is kind of a good introduction to heaps, the structure property, the order, how they're implemented using arrays. Next, we're going to talk about how we can actually insert values into a heap and remove values into a heap while maintaining the structure and the order properties, because that's very important. Without these properties, we don't have a heap anymore. So now let's talk about inserting into the heap, aka pushing into the heap. That's usually the term that's used when it comes to heaps or priority queues. So if we want to push a new value into the heap, suppose we want to push the value 17. Well, thinking about the structure property, the obvious place we would want to put the node is over here. I mean, we could, I guess, put it here, but then there's like a hole over here. We want these to be contiguous. We always want to insert in the next available position. We definitely don't want to put it here. So we're going to put the value here. It's a little bit messy over here, but bear with me. So we have a 17 over here. So the good thing is that the structure property has been satisfied. What about the order property? Well, remember, this is a min heap. So for every node, we want its children to be greater than it. So for this node that we just inserted, we want its parent to be smaller than it. So let's compare the value here to the parent. By the way, in our array, it's going to look something like this. The 17 would have been inserted over here, and we want to compare this to the parent. How do we get the parent? Take the index, divide by 2. So from 10, we would compare it with what's at index 5. Clearly, that's the same value. And in this case, the parent is actually larger, but it should be smaller. I mean, technically they're allowed to be equal, but in this case, they're not equal. So these should be reversed. The smaller one should be the parent. So what we do here is just simply swap the two values in our array. So it's a bit messy, but we swap the values in our array, and that means that the tree representation would look something like this. And then we would continue the algorithm for the node. Now that we, moved over here, we want to compare it to its parent now. We want to make sure that the order property is being satisfied. We know, of course, it's satisfied everywhere else in the tree, but with this new node, it might not be satisfied. So we look at it, compare it to its parent. Its parent would be 5 divided by 2, rounding down. So at index 2, in that case, you can see that that's, also the same node. So the parent should be smaller, but the parent in this case is larger than the child. So again, we want to swap these two values. So now we swapped these two values. 17 is at index 2. It's over here. 19 was moved down here. Now, before we compare this one to its parent, I want to mention we moved the 17 up here. The reason we don't have to compare this now to its left child and pretty much everything over here is because we already knew 19, which was in this position, was valid. 19 was allowed to be here because 19 was smaller than all of the values over here. But now we replaced 19 with a value even smaller than it, which is 17. So therefore, 17 must also be smaller than all the values over here. That's just basic math and logic. So we don't have to compare it to every single value that's a descendant of it. But now doing our last comparison, comparing this to the root node, 17 should be greater than 14. And in this case, it actually is. We compare this to the parent, and the order property actually is being satisfied. So in this case, we know we're allowed to stop. That's how you insert, aka push, into a min heap. It would work similarly with a max heap, just, the order would be the opposite. Now, in the case that we had an even smaller value, suppose instead of 17, we had a value like 10, in that case, we would end up swapping it with the root node, then 10 would be over here, and then 10 would not have a parent, right? This is the root node, it would not have a parent, so at that point we would stop. So either we go all the way up to the root, or we get to a spot like this one where the order property is already being satisfied. Now, taking a quick look at the code of what we've talked about so far, this is what the class implementation of a heap would look like. So for the constructor, we would initialize the heap as just a single value array where the value in this case is just a 0. That would just be kind of the dummy. We know that the 0th index is actually not going to be used. So this is essentially an empty heap that we've initialized. Now to actually push values into the heap, we would do what I just talked about, which is taking that new value that we're inserting and appending it to the heap. So putting it at the last index. So the heap itself, remember, is just an array, a dynamic array, but essentially an array. Then we would get the index that we just inserted at, which would be the length of that array, -1. So we would be at index 10. And then we would do something called percolate up. That's pretty much what I just talked about, where we insert the node here. The node that we did was 17, and then we percolate up, which is basically shift it up while the order property is not being satisfied. So, we shifted 17 up here, then we shifted it up here, and then we stopped. So this code is essentially doing the exact same thing. You can see that index I, which would be 10 initially, is being compared to its parent, I divided by 2. In Python, we use double slashes when we want to round down, but the general idea is going to be the same in any language. We're going to compare it to its parent. If it's less than its parent, then we're going to swap it with its parent. So we, have a temporary variable, move the parent into the child position, move the child into the parent position, and then we want to take our index and then divide it by 2 because we just went from here to the parent position, and now we want to potentially from here swap this with its parent, or at least compare it with its parent, and then we would continue the loop to do that comparison and keep doing that until this is no longer true. until the node is in the correct position. What would be the time complexity of this, by the way? Well, essentially the height of the tree. And in this case, we actually know that the tree is always going to be balanced. That's kind of the point of having a complete binary tree. So in this case, we can definitively say that the time complexity is basically going to be log n, where n is the number of values in our heap, aka in our array. Next, let's talk about removing from the heap, aka popping from the heap. We don't actually specify a value that we want to pop because remember, our priority queue is about popping the priority element, and we know that the minimum is going to be at the root, so that's the one that we're always going to pop. So it seems simple enough, but actually popping is more complicated than inserting. If we just wanted to read the top element, we just wanted to read what the minimum element is in our priority queue, we could just go to index 1 and then return that. That would be easy. But to actually pop it is going to be a little bit more complicated because we have to maintain the structure and order properties. Now, after removing this node or removing that value from the array, your first instinct might be to just take the minimum of its two children and replace it with that. That would kind of maintain the structure because we have a hole here we need to fill. We can fill it with one of its children, and the order property, we want to make sure that the minimum value goes here. So the minimum must be one of these two children, because all of these are going to be greater than 16 and all of these are going to be greater than 19. So the minimum has to be one of these two. It seems simple enough, but if we do it like that, we're going to put the 16 over here, which works. And then we have to replace this with the minimum of its children, which is 19. So we remove the 19 and then put the 19 over here. Now the order property is being satisfied, but not the structure property. Notice how this level is full, this level is full, this level is not full. We introduced a hole over here. We didn't want to do that. If we're removing a node, we should remove it from the bottom level, but we weren't able to do that. This is why this way doesn't work. It's a good idea, but it doesn't work. To get pop to work and to maintain the structure and order property and do it efficiently, we actually have to use sort of a genius technique, but it's actually a relatively simple one once you know it. What we actually do is remove the 14 and replace it with the last value in the array, the last node in our tree, which would be over here. Because remember, that's the way to maintain the order property. So we remove this node and move that 30 over here. And of course, under the hood, this would actually be going on in our array, but I'm not going to be drawing all that out because it's actually going to get kind of complicated here. Now, the good thing here is we satisfied the structure property, but not the order property. But we can fix that. Instead of percolating up like we did when we inserted a node, we can do the opposite by taking this and percolating down, because we don't know that this is in the position it should be at. We need the minimum to be in this position. We know that this is probably not the minimum. The minimum is one of these two. So what we do is we take the minimum of our two children, the left and right, the minimum is 16. So now we compare that minimum to this node, 30. Which one of these is smaller? 16 is smaller. Therefore, we're going to swap these two nodes. We're going to put 16 over here and 30 is going to go down here. Now we already know 16 is smaller than all of these because it's smaller than 19, which is smaller than all of these. Remember, heaps have a recursive order property, but we're not done yet because we need to satisfy that recursive order property. 30 should be smaller than all of its descendants, meaning it should be smaller than both of its children. So let's take the minimum of the two children. It's 19. Is 30 smaller than 19? Nope. That means we need to perform a swap. So let's swap these two values, move the 19 to be in this node, and the 30 will now be in this node. It's definitely gotten pretty messy. Sorry about that, but we're pretty much done at this point. So it's really counterintuitive that we would do it this way. We would literally just take the last node, move it to the root, and then percolate down. But that is the most efficient way to do it. That's why I say it's a genius thing to do, because you wouldn't really come up with it, but once you know it, it seems really simple. And now our min heap is satisfying all the min heap properties. Now let's take a quick look at what the code would look like for this. It's actually a little bit complicated. So this is what pop would look like in Python. Self is just a Python thing, which gives us access to all the member variables of the class. We're assuming that this is inside some class. I didn't write out all the code because we're already kind of running out of space. But remember, the ideas that we're talking about here could be applied to any language. So when you pop from a heap, first of all, if our heap is empty, there's nothing to pop. And we know it's empty if the length of it is equal to 1, because remember, we have like a dummy value in it. So in that case, we would return null. If it's equal to size 2, that means we just have a single value, the root. We would remove it from our array and then return that value. So we would return 14 and then remove this, and then we'd have nothing. But the complicated case is if we have, multiple values in the heap. So we'd first assign the result. We would take 14, copy it into some temporary variable because we know that's what we're going to end up returning. But before we return that, we actually have to delete it from the heap and then, reorder the heap. So next, we're going to take the last value and move it into the root position. So we're popping the last value in our array and then moving it to index 1. So we're putting the 30 over here. Next, we set our I to index 1. That would mean our pointer is at the root node. And then we would percolate down. So this is a lot of code, and there are many different ways to write this. But what's important here is the logic. So we know that there's multiple cases when we're at a node. It could have both children. It could have just a left child. For example, if this node didn't exist, then this node would only have a left child. It wouldn't have both children. Now, it's impossible for a node to have a right child and not have a left child because that doesn't satisfy our complete binary tree definition. So we only worry about the cases where we have 2 children or just a left child. And the third case is, of course, we don't have any children. So that's what these conditionals are all about. The first case is where we have both children. But before that, first of all, this loop of percolating down is only going to be running while we at least have a left child. How do we know we have a left child? Well, we take where we're at. This is where our I pointer is at. And we take 2 times I, which will give us the pointer to the left child. And we check that that is less than the length of our heap at this point. That means we do have a left child. So next in our loop, we check, do we also have a right child? We know for sure we already have a left child, but do we also have a right child? We can check that by saying 2 times I plus 1. That's going to be the pointer here. We do have a right child, and if the right child is smaller than the left child, which in this case is true, 16 is smaller than 19, and the current node that we're at is greater than the right child. In this case, the current node that we're at is actually going to be 30 because remember, we swapped it with this node down here. So then we compare these two. 30 is greater than 16. So all 3 of these conditions are met and they're ANDed together, logic ANDed. So therefore, in this case, we're going to end up swapping this with the right child. And that's kind of the code down here to do that. Now, if these were not satisfied for any reason, then we would check maybe we want to swap this with the left child instead. And we would only do that, of course, if 30, the current value that we're at, is greater than the left child, which is 19. So in that case, we would potentially swap it with the left child. But let's just continue it on this example. So suppose we put 16 over here and we put 30 down here. Now we're going to go to the next iteration of the loop. And before we actually continue to the next iteration of the loop, we would want to update our I pointer. Initially, it was over here. Now we want to put it wherever we moved the node to, which was here. So we would take I and set it to 2 times I plus 1. So now our I pointer is over here. Does this at least have a left child? Yes, it does. So that means possibly we might continue to shift it down. Let's check. First of all, does it have a right child? Yes, it does. Is the right child less than the left child? Nope, it's not. So in this case, we don't execute this first if statement. We take a look at the else if. Else if 30, the current value, is greater than the left child, which is 19, then we swap it with the left child. That's exactly what we're doing in this case. So we move 19 up here and we move 30 down to this node. And in that case, we would set I equal to 2 times I because we're taking it from being pointing over here to now being pointing at the left child. And then we would execute the loop again, but we would see actually that in this case, we don't have a left child anymore, so we can stop the loop. And at that point, we would return the result, which was the original root node that we were trying to get rid of. Now, the last thing that I didn't kind of go over, the last case would be, suppose we had a 16 here, we were moving the 16 down here. We would compare it to its right child. It's not greater than its right child. We would compare it to its left child. 16 is not greater than its left child. That would mean that the last else case would be the one that would execute, and that would basically break us out of this while loop. So then the while loop would terminate, and then we would return the result. Why we would execute it like that is basically we know that the node that we're percolating down is already in the proper position. We don't want to swap it anymore. We don't want to shift it down. It's already where it needs to be. That's why we would break out of the loop. So this is definitely pretty complicated. There are many ways of writing this. I tried to write it where there are distinct cases for each of the things we're doing, swapping right, swapping left, not swapping at all. Most likely you won't actually have to implement this in a real interview. I think it's pretty rare, but knowing the general idea of how this works can definitely be helpful. Now, the time complexity is again going to be the height of the tree. We know it's a balanced binary tree, so the height is basically going to be log n. So that's the big O time complexity. And that essentially comes from percolating down. So we already talked about one of the advantages of heaps over binary search trees. We can get the min or the max depending on what kind of heap that we've actually implemented. We can do that in constant time. Whereas if you had a binary search tree, you would need to do it in log n time because you have to kind of go all the way left in the tree. Now, another advantage of heaps is how we can actually build them. We know that when we have a binary search tree, you have to insert a node every single time to build that binary search tree, and the time complexity of that is n log n, because we have to do n insertions, and to insert each one takes log n time. Now for heaps, you can do it the exact same way. You can keep pushing elements into the heap and it will also take n log n time. But there's actually a special algorithm with heaps, which is sometimes called heapify or just build heap. And the idea is that we could be given some set of values, some list of values, suppose in the format of an array like this. And we can take those values, and they're in no particular order, and we can take them and turn them into a heap that satisfies the properties of a heap, and we can do that in O of n time. Let me show you how. First of all, if we're given an array in this format, it doesn't even satisfy the structure property because we know that we don't really want to have a real value at the 0th index. So the simple thing to do here, since we know these are already in no particular order, let's just take this one and move it to the last position. So at this point with this array, what would our heap look like? It would look exactly like this here. We would have the 50 in the root position, then the 80, then the 40, etc., etc. So we satisfied the structure property pretty easily, but now we have to satisfy the order property. And remember, the order property is recursive. It essentially means that for every single subtree, every node should have a value that's smaller than all of its descendants. So that's what we're going to do. For every single node, we're going to check, does it have a value that's smaller than all of its descendants? And that's because we're doing this for a min heap. For a max heap, you would just do the exact opposite. So we can start at the bottom nodes and then move our way upwards. So we can start at the last node over here. But when we get here, we know it doesn't have any children anyway, so there's no point in doing any kind of comparison here. Same thing for this node, same thing for this node, and this node, and this node. They don't have any children, so we have nothing to compare them with anyway. So that's actually going to be true for half of the nodes. So what I'm saying here is we can actually just skip all of these if we want to. I mean, we could start at the end and, run the algorithm like that. but there's no need to. So to be a little bit smarter, we can just skip half of these. How would we do that in terms of code? Well, we can get the number of nodes in the heap, which is not necessarily the number of nodes in the array because we know we have a dummy. So we would take the length, which in this case would be 10 minus 1, which would give us 9 because we know there's 9 actual nodes here. And then we would take that and divide it by 2. So 9 divided by 2, rounding down, of course, would lead us to be at index 4. So 30 is the first node that actually has children. Taking a look at our picture, that is definitely true. If you don't end up remembering a fact like this, it's okay to still start at the end and then go backwards anyway. It shouldn't change the overall time complexity, but this is how it's taught in most courses. So we already know that all of these subtrees are valid. They don't even have any children anyway, but now moving to 30, let's check, is 30 valid? Is it smaller than all of its children? Well, it has 2 children, it's smaller than 90, and it's smaller than 60, so we don't have to do anything. Notice how what we're actually doing here is the same percolating down algorithm that we talked about earlier when we were removing nodes. This is the exact same thing. What we're doing here essentially is going through every single node that has children and percolating down if it can be moved down. So we did it for 30. We didn't need to, perform any swaps. Now let's move to the next one, 40. Take a look. Let's compare it. First, does it have 2 children? Yes, it does. Is the right child smaller than the left child? Yes, it is. Is the right child smaller than the parent? Yes, it is. So we swap it with the right child. So now that we've done that, we already knew this subtree was a valid heap. This subtree was a valid heap. Now we know this entire subtree is also a valid heap. Now let's move to the left. We get to 80. That's this node over here. Does 80 have 2 children? Yes, it does. Is the right child smaller? Yes, it is. So if we're going to swap 80 with something, it would probably be this one. So let's compare these two together. Is 10 smaller than 80? Yes, it is. So let's swap 80 with this node over here. So originally we already knew this subtree was valid and this subtree was valid. Now we know that we've percolated down for this, that this entire thing is valid. Now, when we are percolating down, we are going to keep percolating down, but at this point, this one doesn't have any children anyway, so there's nothing for us to do. Now we get to the last node in our array. Well, the first node actually, 50. It's the root. So time to percolate. Let's compare the 2 children together. Which one of them is smaller? 10 is smaller. So if we're going to swap 50 with anything, it's probably going to be this one. Let's compare 50 to 10. Is 10 smaller than 50? Yes, it is. So let's swap these two now. It's definitely starting to get a bit messy now, but let's try to continue. We're almost done. We're at the 50 now. We're continuing to percolate this down. Let's compare the 2 children together because we have 2 children. Which one of them is smaller? 30 is smaller. So let's compare 50 with the smaller child, 30. Is 50 bigger than 30? Yes, it is. So let's swap them. And at this point, I'm not even going to be maintaining this array because I think it's getting too complicated, but you get the idea that anytime we perform swaps here, under the hood, there's an actual array that's maintaining all of that. So the 30 is now going to be over here, and the 50 is going to be over here. Now continuing to percolate this, let's check. We have 2 children still. Let's compare the 2 children. This one is smaller. Now let's compare that smaller child with 50. Is 50 bigger than 60? Nope. So 50 can stay exactly where it is. We found the correct spot to put the 50. So now at this point, this is what our heap would look like. And tell me, does it look valid to you or not? Well, it's a little bit hard to read because it's gotten messy, but the smallest value is in the root. 20 is smaller than all of its descendants. 30 is smaller than all of its descendants. 50 is smaller than all of its descendants. 80 doesn't have any descendants, and the rest of these nodes don't have any descendants either. So we definitely were able to do this. Now let's take a quick look at the code. So the heapify algorithm is pretty similar to remove that we talked about earlier, only in this case, heapify, or build heap you could call it, is going to be passed in some input array. And when we have that input array, we're basically going to take the 0th element and move it to the last position. That's what append is doing. It's basically pushing it to the end. And then we're just assigning that array to be our heap. We know it satisfies the structure property. Now it's time to satisfy the order property. We have a current index. We basically take the length of the heap, subtract 1, and then divide it by 2, just like I talked about earlier. This is integer division in Python. It'll round down, but most languages will round down by default. And current is going to be at this point, just like we showed in the walkthrough. And then we're going to have another copy of current, we're going to call it I. And at that point, we're just doing the exact same percolate down algorithm I talked about earlier when we were doing removing or popping from the heap. So I won't go super into detail. It'll be the exact same idea. But after we've percolated this down, in this case, we wouldn't actually do any swaps, we're going to be done with this while loop, and then we're going to take our current index and subtract by 1. Because remember, we're going in reverse order. We're going to go to this node, and then we're going to go to this node, and then we're going to go to this node. And for each of these, we're going to percolate them down if we can. Now, if you were actually implementing your own class for a heap, you'd probably put this in like a helper function since it's being used not only here, but it's also being used in heap pop. So you could probably just put this in a helper function. The reason I wrote this out explicitly is just to kind of show you exactly what is going on with the heapify algorithm. Now, why is this heapify algorithm a linear time algorithm? Because at first glance, it seems to be an n log n algorithm because we're going through pretty much every node in the tree and having to percolate it down. Percolating down might be a log n operation, let's say. So why is the big O time complexity big O of n? Well, first of all, I'll just say that you're probably never going to have to prove this or even argue that it is a linear time algorithm. Just knowing it is enough. But I'll quickly go over the general intuition of why it's the case. First of all, if we had to take every node and percolate it up, or if we had to take every node and percolate it down, which one would we rather do? Which one seems more efficient? Well, if we're percolating down, then only the root node actually has to go through the whole height of the tree. And then these two have to go to the whole height minus 1. And then a bunch of nodes here go an even smaller distance. And we get more and more nodes as we go down. Because remember, this is a complete binary tree. But if we're percolating up, it's worse because now we have a bunch of nodes that have to go the whole height of the tree. And then we have a smaller amount of nodes that have to go the whole height minus 1. So percolating down is going to be more efficient. When we get to the root node, we just have a single node here that doesn't have to be percolated up. Whereas if we percolate down, we have a bunch of nodes that don't have to be percolated down. So shifting these down is generally going to be more efficient if we have to do it for all of the nodes. Now let's say n is the total number of nodes in the tree. And let's say in this case, we actually had a full binary tree just to make the math a little bit more simple. We know that roughly half of the nodes are going to be in the last level. Right, that's kind of something we talked about earlier in the course, right? This is going to be 1, 2, 4, 8. Each term is going to be roughly equal to all the previous terms combined. Let's say we have roughly n divided by 2 nodes in the last level. Now for each of these nodes, how much are we going to have to percolate them down? Well, remember the last level doesn't need to be percolated at all. So we get a 0 times n divided by 2. What about the next level? Well, that's going to have half of the nodes that this level had. So we can call that n divided by 4. How much are we going to have to percolate these down? Well, 1 each. So we're adding these two terms together, 0 times n divided by 2 and 1 times n divided by 4. And if we expand that, we get a summation that looks like this. Now the number of terms that we're going to be adding together is going to be roughly equal to the height of the tree. So if you remember your math, we'll get something like this, but at this point you probably don't care. And this would roughly evaluate to n. So we know that the big O time complexity of this is indeed big O of n. You won't have to memorize this, don't worry. And you most likely don't care about it either. I just wanted to mention it for the sake of completeness. But the important thing here is that just because we can be given some random n elements and then turn that into a heap doesn't mean we can actually sort all of them in O of n time. Because just because we have a heap, if we wanted to turn that heap now into a sorted array, we first built the heap in O of n time, but then we'd have to pop every single element in the heap. We know popping is still going to be a log n time operation. If we have to do it for n elements, then it'll take n log n. So what I'm saying here is we can actually use heaps also to sort values, and we can do that also in n log n time, just like binary trees, just like merge sort, and the rest. So this is yet another example of sorting. So we talked about some of the advantages of heaps over binary search trees. We can get the min and max in constant time. We can heapify, we can build the heap in O of n time. But the downside of heaps is that we can't just search for a random element and then do that in log n time like we can with BSTs. With a heap, suppose we're looking for the value 30. We get to the root node, we're at 14. It's not 30. Well, we know all values in the right subtree are greater than 14, and we know all values in the left subtree are greater than 14. So the 30 could be in both subtrees. It could be here or it could be there. We don't know where it is. We haven't narrowed it down. So to search for an element, we'd have to go through every single node in the tree. That would be an O of n time operation, but with binary search trees, it's log n. So binary heaps are not good for searching, but that's okay because they're not intended for that. They're intended to get the priority element, which is either the min or the max. And the last thing I want to mention about heaps is that when it comes to coding interviews, you actually have to use a heap more often than you have to use a binary search tree. At least I'm talking about like a built-in data structure where the data structure is a part of the solution. BST problems are also common, but it's usually you're implementing a part of the BST. You're searching for something, you're calculating something. But when it comes to problems where you actually have to use the data structure as like a utility data structure, it's pretty rare that you end up actually needing binary search trees. It's more often that you need a heap, because it's more often that you need like a minimum or maximum value. You need to continue doing that. There are a ton of algorithms where heaps are really important. So it's a very good data structure to understand. You should at the very least understand that heapify runs in linear time, and you can push and pop from the heap in log n time, and you can get the min or the max depending on what type of heap you have in constant time. Those are all important to know, even if you don't necessarily remember how to implement all of them. So next, let's move on to probably the most common data structure you're ever going to use, whether we're talking about coding interviews or real coding at your job or projects or anything like that. Hash maps and hash sets are really, really useful. And to start with, I'm going to be focusing on the application of these rather than the implementation, because it's much more important to know how to use these than it is to actually implement them. We already talked about sets and maps earlier, specifically the ones that are implemented with binary search trees. Now, I talked about how sets are just kind of a set of values like 1, 2, 3, whereas maps are a little bit more complicated. That is kind of a set of keys, which are then mapped to a different value. We gave the example of like a phone book where some name is mapped to, the phone number 1, 2, 3, something like that, right? So we're primarily going to be focusing on maps because they are generally more common and they're a little bit more complex, but the main ideas behind a map are nearly exactly the same as a set. Instead of just having like a set of keys, we're going to have that set of keys, except each key is going to be mapped to some separate value. But the key is what's used to sort the binary search tree. It's also what's used to access values from the hash set or the hash map. First, let's compare tree maps and hash maps though. There are typically three main operations you want to do when you have a map. You want to insert. When it comes to tree maps, the big O time complexity is log n to insert into that tree. That's definitely better than maintaining a sorted array, because inserting into a sorted array in the worst case would be big O of n. Removing from the tree is the exact same. It's also log n. Likewise, with searching, we essentially run binary search on the tree map, and we can search for any value in log n time. That's pretty good. And there are other bonuses of tree maps because they're ordered. We can iterate through it in sorted order. If we have that tree map, we can iterate through it in sorted order in O of n time. So that's like our in order traversal. Just by having a tree map, we are kind of maintaining that sorted order. With a hash map though, things get interesting. Inserting is actually a constant time operation. Removing is also a constant time operation. And searching is also a constant time operation. So you can already see why hash maps are probably the most useful data structures you're ever going to use. They really just beat tree maps out of the water. But there's a bit of a caveat here that this is actually not the worst case time complexity. Even though I'm writing it as big O, which means worst case, hash maps actually don't have this as the worst case time complexity for these three operations. This is actually the average case time complexity. But the vast majority of the time, people still assume that it is the worst case time complexity. So we write it as big O of 1. Like if you're ever doing a coding interview, it's safe to assume that these operations run in constant time. That's what people assume in jobs and just in general. I think if you ask them, most people don't actually know that these operations are actually average case. In the worst case, inserting, removing, and searching actually could be O of n time depending on how you implement the hash map, but that's not so important, and we'll actually touch on that a little bit later. Now, the downside of hash maps, and there's always a downside when you have something this good, it's that hash maps don't maintain any kind of ordering, actually. So if you wanted to iterate through all the keys of the hash map, you could not do it in O of n time. You'd basically have to take all of the keys and then sort them, and then depending on what sorting algorithm you use, you could use, merge sort, you could even use a binary tree sort. It would be n log n typically though. So that's sort of the downside, but you can see that the positives definitely outweigh the negatives, especially if you don't need to traverse it in order and you just need to insert, remove, and search, which is what we would probably do with a phone book. Then hash maps are very important. So let's take a look at a common use case of hash maps. Let's say we were given a list of names, maybe in the form of an array, and we want to count for each name, how many times does it show up in this array? So how would we use a hash map to do that? Well, the obvious way would be to map every single name, so use that as the key, and the value in this case will be an integer with the count of that name. So initially our hash map is going to be empty. We start at the first name, it's Alice, so we go ahead and add Alice to our hash map. But before we would even do that, what we could do is run search on our hash map. We would check, is Alice already in the hash map? No, it's not. And remember, search will run in constant time. So it's not in the hash map. So when we do insert it into the hash map, we should put the value 1 because this is the first time we're seeing this name. Next, we would go to the next position. By the way, for us to have done that, for us to have gone through one position, we did it in constant time. If we were doing it with a tree map, in the average case, that would actually run in log n time. I mean, we know that inserting a node into an empty tree is probably going to be O of 1, but in general, it's going to be log n. So now we're going to get to the second name, Brad. We're going to search for it in our hash map. That search is going to be O of 1. It doesn't exist. So we're going to do the same thing with Brad. We're going to add it as a key, and the value initially is going to be 1. We're going to get to the third one. We're going to get to the third name, Colin, do the exact same thing. Colin is also now added to the hash map. The value, the count of it is 1. Now we're going to get to our first duplicate, Brad. We've already seen Brad. So when we search our hash map, we're going to find that it already exists in the hash map. And it's at this position. So instead of assigning 1 here, we don't know. The count could be anything. Right now it's 1, it could have been 2, it could have been 3, it could be some value. We know it's not going to be 0 though. So what we should do here is instead of assigning it to 1, we should add 1 to it, which would put it to be 2. So we overwrite that value with a 2. By the way, doing that, iterating through this position was also a constant time operation. And notice we don't have duplicates in this hash map. I mean, we could have added another entry for Brad and put 1 here, but that isn't what we're trying to do. For Brad, we're trying to count how many times did it show up. It doesn't make any sense to add a second entry. And this brings us to a property of hash maps. They cannot contain duplicates. Duplicates are not allowed in hash maps because it doesn't really make sense for us to do that. That's not the use case for a hash map. Why would we want multiple copies of the same thing? And that's the exact same with binary search trees. Remember, we don't allow duplicates in binary search trees, so a tree map is also not allowed to have duplicates. So now let's go to the next position, Dylan. It doesn't exist in our hash map. We figured that out by searching, which is an O of 1 operation. So we add Dylan to the hash map, and the count is going to be initially assigned to 1. We get to the last person, Kim, and they also are not in the hash map. We add Kim and then set the count to be 1. Now for each position in the input array, we basically did a few O of 1 operations. So that means to have gone through this entire array and built this data structure, it would have been an O of n time algorithm Now also the space complexity would also be O of n, because in the worst case, every single name could have been unique. That would have led the size of our hash map to have been O of n. But this is definitely better than using a tree map. A tree map would have had the same amount of space, roughly speaking, it would have been O of n, but the time complexity for each one of these insertions and searches would have been a log n operation, and we know we have n values in the input, so the overall time complexity would be n log n with a tree map if we were doing it. But now we have a hash map. Hash maps are much more efficient. By the way, the code for this type of algorithm using a hash map would look something like this in Python. Suppose we're given an input array, names, and the same exact names that we have listed up here. We create our hash map. This is how you do it in Python. It's a little bit different than most languages, but in most languages you would declare like a hash map data structure with like a constructor or something like that. We're calling it count map. Then we're going through every single name in our list of names. And remember, we have two cases if count map does not contain this name. Now, in Python, the syntax for that is like this: if name not in count map, but most languages will have a count map data structure, and that will have a method or function which is called, let's say, contains, and then you'd pass in this key as the parameter to that method call. But basically we're checking this name does not exist in this count map, therefore we're going to assign that name to have an initial value of 1. The else would be that the name already exists in the count map, therefore we would increment that count by 1 like we did for Brad. So it's a pretty straightforward algorithm. It runs in linear time. Next, let's talk about how we can actually go about implementing a data structure like this. Now let's talk about the implementation of a hash map. Now most likely you'll probably not be asked to actually implement a hash map in an interview. It's pretty rare that you have to do that. And the implementation of hash maps can get really, really complicated. We'll be talking about the general concepts, and then we'll be coding up a relatively simple hash map. But I think the concepts are what you should really focus on, because the concept of hashing and the other ideas we're going to be talking about definitely come up in software in general. So this is definitely not the last time you're going to be hearing about these ideas of hashing, key value pairs, and things like that. First of all, under the hood, a hash map is actually implemented with an array. So in this case, we'll have some index, and that index will be mapped to the key value pair. And just because we have an empty hash map right now does not mean the size of our array is zeroed. Even an empty hash map is going to be non-zero. In this case, let's say we have an empty hash map, but our array is of size 2. We have index 0 and index 1. Now, the actual key value pair in this case, suppose it's just null, right? Some kind of default value, it's empty. We're basically indicating that we don't actually have anything stored here just yet. Now, with an empty hash map, the first thing we would probably want to do is start inserting some values. But how does an insertion actually work? In this case, let's say we're calling it put. It could be called insert or something like that. In this case, the key value is going to be a string, and the value itself is also going to be a string. That doesn't necessarily have to be the case. This could be an integer, or this could be an integer, or they could be some other type. It could actually even be an object. But what's important here is that we have a way to convert the key. We don't care so much about the value, but the key should be able to be converted into an integer. And how we're going to do that is called hashing. We're going to have some kind of hashing function, which is going to take the key value and then convert it into an integer. And when we have that mapping, you can see where I'm going. We're going to use that integer as the index, and that's how we're going to decide where to put that pair, that key value pair, into our array. So in this case, this array is actually an array of objects where the object itself is a pair, a key value pair. Well, the simplest thing would be able to map each character to some integer. For example, the first character A could be mapped to 0. I think L is the 12th character, so that could be mapped to the integer 11, and we could do that for every single character, and then we would add them up and we would get some big integer. Let's just assume that the integer we get is a 25. I'm just making that up, but the idea is that we converted each character to an integer, then added them all up, and we got another integer, 25. Now, the only problem here is our array is only of size 2, so this is not really a valid index for our array. How can we fix that? Well, this is where a little bit of math is going to come in. We can take any integer, no matter how big it is, as long as it's positive, and we can take it and then mod it by the size of our array. So in this case, mod it by 2. If you're not familiar with modding, we're basically dividing 25 by 2, and we're getting the remainder that's left over. So in this case, 24 divided by 2 would equal 12 with a remainder of 1, because 2 can keep fitting into 25 until we get to 24. And then if we add a 2, we're going to get to 26. So that's too big. With 24, we have a remainder of 1 left over. Now, if we instead of 25, we actually had 24 and we were modding it by 2, then we would have a remainder of 0, because 2 does fit into 24 perfectly 12 times, and then we're left with a remainder of 0. And those are really the only two possibilities. But what's important to notice here is that when you mod by the length of the array, no matter what integer you're modding, you're always going to get a valid index as the output. The result that we get would always be a valid index if we're modding by the size of the array, which in this case is 2. It could have been 3, it could have been 4, but the mod is always going to result in a valid index. And the reason behind that is pretty simple. No matter what integer we're modding by, it could have been 5, the result, the remainder, is always going to be less than 5, because the remainder always has to be less than 5. It always has to be less than the number we're modding by, because if it wasn't, then it wouldn't really make any sense, right? We can't say 25 modded by 5 is equal to 5, because we can still divide this by 5 and then get 0, right? So it's just a little bit of math. But that's the main idea. So we mod by the size of the array to convert any integer like 25 to a valid index. So modding this by 2 in this case would lead to 1. So then we'd say Alice is going to be inserted at index 1. So in this case, Alice is going to be at index 1. The key is going to be Alice, and the value is going to be the city that she lives in, which let's say is New York City in this case. Now we're going to insert a couple more values, but suppose we wanted to first get Alice. We could do that in O of 1 time. We call get on Alice. We would, using our exact same hashing function, take Alice, convert it to an integer. Let's say again it's 25, mod that by 2, then we get 1. So in constant time, we were able to get the index that Alice is stored at. Then over here, we could go to that index and then say, okay, what city does Alice live in again? Well, it's New York City. So that's the idea. And that's why it's so efficient. Now, we're going to run into a few problems though. Let's say we now want to add Brad to the hash map. Let's say we convert Brad to some integer, right? Taking the sum of the characters. And by the way, when we actually convert a character to an integer, most likely we're going to be using the ASCII representation of the character. There are more complicated ones, but if you're using a set of 128 characters, so if we had a relatively small alphabet size, we could do this. Basically, it's a way of converting each character into a integer. And in that case, capital letters are actually different than lowercase letters. Like for example, capital B could be evaluated to like 70, lowercase b could be something like 44. But that's not so important. Let's just assume that we have a way to convert each character to some integer. But let's say we took Brad and the integer that it turned out to be was 27. Now we mod this by 2, we get 1 again. So what are we going to do? We're going to say, okay, at index 1, let's insert Brad. But Alice is already at index 1, so we can't really do that without losing the information we've already stored. This is a problem, and this is the problem with pretty much all hashing It's something that you can't entirely avoid. It's called a collision. Clearly, it's bad to have collisions, but there are ways that we can work around it. We can minimize collisions and we can try to work around them, but we can't entirely get rid of them. That's really important to know. Hashing collisions pretty much always happen. Now, first, let's understand how we can try to minimize collisions. There's sort of a problem here. No matter what we convert Brad into, no matter what integer it gets converted to, modding it by 2 is either going to lead to a 0 or a 1. If our hash map is half full, like one of the spots is already taken, we basically have a 50-50 chance of having a collision or getting the position that's empty. Those aren't great odds. So typically what happens with hash maps is we keep track of the size of the array and we keep track of how many keys are actually inserted into the array. In this case, the size of the array is 2, and we only have 1 key actually inserted in the array. So we say that the hash map is half full. And typically when it becomes half full is when we resize the array. And resizing the array actually works pretty much exactly the same as when we did it with dynamic arrays, meaning we take the size and roughly double it. And we would have done that not at the time that we're inserting Brad. We would have done that as soon as we inserted Alice. We inserted Alice and then we realized our hash map is half full. So at that point, we would have resized the array. We would have doubled it roughly. So the array would now have index 2 and index 3. So 4 elements now. But ignoring Brad for a few more seconds, what if now we try to get Alice? Well, we convert Alice to the integer 25. We mod it now. Instead of modding it by 2, we're actually going to mod by the size, which is 4. And it turns out that the index is 1 again. So we see that, okay, Alice is still in the correct spot. In this case, it works out, but it's not always going to work out. For example, what if instead of Alice being a 25 was a 27? In that case, when we mod it by 2, it would have gone at index 1, exactly where it's still at. But then when we resize and we try to get Alice again, we try to search for it, we mod this by 4 now because the size has increased, and modding 27 by 4 leads us to 3. So we would say, okay, Alice is probably at index 3. We would check and we'd see that no, Alice is not there. What I'm saying here is when we resize the array, we can't just leave the values where they previously were because the size changed. Therefore, the index using our hashing function might have also changed. So what we have to do when we resize, we take every single key that's already in the hash map, we recompute the hash of it using the new size, and then move it to where it should now be. For Alice's case, 25 modded by 4 is still 1, so it can stay where it is. But if it wasn't, we would have to move Alice to the new position. By the way, we call this process of increasing the array size and then moving all the elements to their new position, we call that rehashing the array. And since we're doing it when the size is half full and we're doubling it every time, it's still relatively efficient because it's going to be infrequent that we have to do this rehashing. Obviously, it's pretty expensive because we're going to have to go through every key that's in our hash map. But as long as we double it the same way that we did with a dynamic array, it's going to be relatively efficient in the average case. So now finally, let's get back to Brad. Instead of modding it by 2, now that our hash map is size 4, we're going to be modding this by 4. 27 modded by 4 is 3. So in this case, we don't have a collision. And it makes sense because our chances of a collision have definitely decreased. We have a bunch more empty positions. So Brad is going to go over here. And the city that Brad lives in is Chicago. And since once again our hash map is half full, we're going to again resize it. So we would double the size. So now it would be of size 8. I'm not going to draw out the whole thing because it's not super important. But let's just assume that the size of this has now become 8. This will help us minimize the chance of a collision. But we're going to insert one more person now, Colin. Let's assume that after hashing the name Colin, we get an integer value of 33. We mod that by the size of our array now, which is 8. We mod that by 8. We get a remainder of 1. So even though we tried to minimize the chance of a collision, which is good, sometimes we still run into the case where we have a collision. We are going to insert Brad or Colin at index 1, even though Alice is already there. And by the way, when we resized this from 4 to 8, we would have actually had to recompute the position for each of these and then potentially moved it to that position. So for Alice, since I think Alice was 25, that was the hash of Alice, and then we'd have to mod it by 8, which in this case would have been 1 once again. So Alice actually would have stayed exactly where they are. The hash of Brad was 27. We would mod that by 8, and that actually would have also been 3, exactly where it still is. That's mainly just a coincidence, to be honest. I didn't even plan that, but it's convenient for us because we don't have to redraw this now. How would we actually handle this now? I mean, if we really wanted to, we could resize the array and maybe that would decrease the chance of this being a collision, but it still might end up being a collision. So we need a different way of handling collisions, and there are actually multiple ways of doing that. One way of doing it is actually at every index, instead of just storing a single pair, we actually store a linked list of pairs. So we could actually have multiple pairs occupying the same index. Now, the downside of that approach is we have to kind of maintain that memory and the pointers and all that. And when we actually run the get operation and we arrive at, let's say, index 1, we're looking for Colin, we would first see in the linked list, we'd have to traverse through the entire linked list. We'd first see Alice is there. That's not who we're looking for. We'd go to the next position in our linked list, and then we'd see, oh, Colin is over here. And then we'd return whatever value we're storing for Colin, which in this case is Seattle. But that's kind of the downside of, and that linked list approach is commonly referred to as chaining. There's another approach called open addressing, and it's called that because we kind of loosely define the position that a key should go at, like the index it should go at. Even though we computed the index 1 for Colin, we don't have to put it here. We can say, well, this is already occupied. Let's try the next position. So we take that index 1 and add 1 to it. So we try index 2. Is this empty? In this case, it is. So we can go ahead and put Colin over here and the city that they live in, C for short. Now, in this case, when we run get on Colin, we're looking for Colin. What city does Colin live in? We would compute the hash, 33 mod by 8. We would again get 1. We would see, well, this is not where Colin is. So if Colin exists, maybe they're at the next index. Maybe we open addressed this. So let's try the next index. We look at the key. Well, this is the same key we were looking for, Colin. So we found him, and the city he lives in is Seattle. Now, possibly we weren't looking for Colin. We were looking for somebody else named Dylan, who actually does not exist in the hash map. Maybe we somehow computed the exact same index for Dylan. We would look at index 1. We'd see this is not Dylan. We would open address. We would try the next available address. Is Dylan over here? No, they're not. We'd try the next available address. Is Dylan over here? Nope. Is Dylan over here? Nope. And at this point, we know we can stop. We don't have to search through the entire index. First of all, that wouldn't be efficient. That would be O of n, and we definitely don't want to do that. But we know that if Dylan did exist, the hash of Dylan would be at 1, but this was occupied. So we would have put Dylan over here, but Dylan was not over there. So then we would have tried the next position. Dylan would have been inserted over here, but he's not there. And then we would have tried the next position over here, but this is empty. So if Dylan existed, he would have been here, but he's not. Therefore, Dylan does not exist in our hash map. This will make a little more sense if I explain how we would insert Dylan. So let's say instead of getting Dylan, we're inserting Dylan. Let's say hashing Dylan, we got the index 1. Then we try to insert Dylan over here. Well, this is occupied. So now we try the next available index. This is occupied. Next available. This is occupied. Next available. Well, we're going to insert Dylan over here and whatever city that they happen to live at. So this is a sort of naive way of doing open addressing because we're just trying the next available position every single time. The downside of this approach is we're going to cluster the hash map potentially. if we have a really big hash map and we get a lot of collisions, all the keys are going to be stored close to each other. There are better ways of doing this open addressing. Instead of just computing the +1, maybe we take that value and square it and do other things with it. But the important thing to focus on here is that we have collisions and we have ways of handling those collisions. And there are, more optimal ways of handling that. And you could spend a lot of time learning about that. It's pretty math heavy, to be honest. So we won't go too in depth into it. And you likely won't need that kind of knowledge for coding interviews. But it's important to know that there are ways of handling things like this. Now, the last thing I want to mention before we actually take a look at a simple code implementation of a hash map is that when we maintain the size of the array, it's more optimal for the size to actually be a prime number. For math reasons, that ends up resulting in less collisions for the hash map. So typically, the size of the array is going to be a prime number. So instead of this being 8, it would actually be better for the size to be 7. And then instead of actually doubling this to be 14, because 14 is not a prime number, we would actually, just try to find the next available prime number. Let's say it's 17 in this case, and we would roughly double this, but roughly double it to a number that is prime. So maybe the next one would be something like 37, if that's prime. I'm not even 100% sure, but that's the main idea. Now, this is kind of complicated to implement this in code, so I won't be doing that, and it's very rare you'd actually be asked to implement a hash map like this. I mean, if you're asked to implement a hash map and you have to do it so perfectly where the size of it is prime and you're doing all these kind of crazy optimizations, that would be a very, very long interview question, and it's very unlikely you'll be asked that. Even if you are asked to implement a hash map, it's probably okay to do it a very simple way. That's why I'm going to be showing you the simple way to do it right now. So first, let's look at how we would kind of initialize our hash map. Like I said, we're actually going to be storing pairs in this array. This is one way to implement that. We have like a class, and that class will store 2 values, the key and the value of that pair. In our case, we were doing strings, but these could be any kind of type as long as you have a way of hashing the key. And this implementation will mostly focus on if we had strings as keys and strings as values. So initializing our hash map, this is Python, but of course you could implement this with any language. The logic will be pretty similar. We're going to initialize the size of the hash map. The size is the actual number of keys in our hash map. Initially, that's going to be set to 0. We're also going to initialize the capacity. I'm arbitrarily setting this to 2, but it could be any number. Optimally, it should be a prime number. But in this case, it's 2, just like we kind of started with in the example. And then our map itself, remember, it's maintained as an array. And in this case, there's only 2 values, remember, and to indicate that it's empty, I'm initializing the 2 values as null. If they were non-empty, we would have some pair for those values. The next really important thing for a hash map is to have some hashing function. Given some key, we should be able to convert it into an integer that fits within the boundaries of our array. In this case, it's size 2, so it should fit in our array of size 2. Assuming the key is a string, we go through every single character in the key and we convert that character to some integer. This in Python will convert it into the ASCII value of the character, but that's not super important. As long as we have a way of converting the character to some integer, we're going to take that integer and just sum all of them up. So initially our index is going to be 0. We're just going to keep adding that integer to our index. We could have some really big integer. It could be out of bounds of our capacity. So what we're going to do before we return is mod it by the capacity. So if our index ended up being something like 10, we would mod it by our capacity, which is 2, we would get 0. If our index is actually not out of bounds, for example, maybe it's 1, we would mod that by 2, and we would still end up getting 1, which is still in bounds anyway. So if it's in bounds, that's okay. If it goes out of bounds, then we'll mod it to bring it within bounds. So by the time we return the integer for this hashing, it will be some index that is in bounds of our array. Now let's move on. So first, let's look at searching for a key, aka the get operation. So given some key, we want to return the value of that key if it exists. If it doesn't exist, we can return null, or we could throw an exception, or we could do something, but the details aren't super important. We care mostly about the logic. So first, we're going to convert that key into an index using the hashing function we talked about a second ago, and then we're going to loop. This implementation, by the way, is assuming we're doing open addressing, where if we find a collision, we're just going to try the next index. So given that index, first we're going to check, is it non-null? Suppose we're searching for Alice and we get an index of 1. We would look here, it's non-null. So then we would check, is the key of what we're storing here of that pair equal to the key that we're searching for? In this case, it's Alice. What we can do is just return that value. We found what we're looking for. But maybe we're actually looking for somebody named Colin. In that case, we would have not found what we're looking for. This is not Colin. So instead, we would have not returned. We would have incremented our index, right? Try the next index. And here, the reason why we're modding by the capacity is assume that actually this part of our array didn't exist. We're looking for Colin. We took 1 and incremented it by 1. Well, that took us out of bounds. To bring us back in bounds, we can mod the index by the capacity, just like we were doing earlier. That would bring us up to index 0. Now we're still looking for Colin. We execute the loop, but at this point, we see that there's null here. This is empty. That means if Colin existed in the hash map, he would have been here, but he's not. Therefore, we know he doesn't exist, and our loop stops. We can return null, or we can throw an exception. We can somehow indicate that the key Colin does not exist in the hash map. Now let's insert into the hash map, aka put. We pass in some key and some value. We want to insert that into the hash map. The idea is similar. We convert the key to some index, and then we start looping. We're looping while true because at any point that one of these executes, we're going to return immediately anyway. So this is just kind of a convenient way that I like to write it. So there's two possibilities. One, that this key does not exist in the hash map. Let's say we're trying to insert Colin. The index we computed was 1. Our loop would execute like this. First, we would check, is this index empty? It's not empty. If it was, then we would insert Colin over here, but it's not. Then we execute the else if case. Else if the key of this is already equal to Colin, in that case, we would just overwrite it. But this is not Colin. This is Alice. So then neither of these execute. We just increment the index by 1 and modding it to make sure it stays in bounds. So then we would try this index, and we would go back to our loop. We would see that this index is actually empty. So what we can do is create a new pair for Colin and whatever value Colin has, assign it to this index, increment the size by 1. And this is important. Remember, if the size is greater than or equal to the capacity, we are going to call our rehash function, which I'm going to show you in just a second. And after we do that, then we can go ahead and return. Now, assuming we were inserting Alice and we wanted to change her city from New York City to something else, then the else case would have executed. We would have found Alice is already here. We would just simply overwrite the value. We don't have to increment the size by 1 because we're not adding anything. We're just overwriting the value, and then we could return immediately. So lastly, let's look at the rehash function. It doesn't really take any parameters because we already have all the member variables of the hash map. We know we're going to double the capacity. At least that's the naive way to do it. More optimally, we could find the next prime number that's roughly double. So we're going to declare a temporary variable for our new map. It's going to be an empty array so far, but we want it to be of the size of the capacity that we're trying to do, which is roughly double the previous capacity. So we could do a loop for that. We could just append null to it to indicate that there aren't any actual pairs in this just yet. And then we're going to take our current map, our current member map, and assign it to a temporary variable old map. Then we're going to take our new map and then assign it to the member variable. So now our new map is the map that we're maintaining, but all we have to do now is take the values from the old map and then put them in the new map. So as we iterate through every pair in the old map, if that pair is non-null, we're just going to run the insert function or the put function that we talked about earlier, putting the key of this pair with the value of this pair. The reason we reset the size to be 0 is because we know internally this put function is going to be incrementing the size by 1 each time anyway. So that will give us the correct size. So that's why we reset this to 1 here. So these are the main ideas I wanted to talk about. You don't have to focus so much on memorizing every detail, just understanding the main concepts behind collisions, rehashing, increasing the size to minimize collisions, having some kind of intelligent hashing function where we also minimize collisions, having the size be prime also helps to minimize collisions. These are the important concepts to understand when it comes to hash maps. And even more important than that is just understanding how to use hash maps and hash sets, which we talked about earlier. We didn't talk too much about the details behind why inserting, removing, and searching runs in O of 1 time on average. The analysis could get complicated, and I don't think it's super important to understand. It's pretty safe to assume that those operations run in O of 1 time. That's what most people do, and to be honest, most people don't even understand what we've discussed so far. So if you understand even half of this, you're far ahead of most people. Next, let's talk about graphs, which are a really common topic when it comes to real coding interviews, and they're actually pretty challenging. There's a lot to cover here, but the good news is that we've actually already been talking about graphs since pretty much the beginning of the course. Linked lists are actually a form of graphs. They're a subset of graphs. And another subset that we talked about are actually trees, whether it's binary trees or other kinds of trees. A graph is essentially made up of nodes like we have over here and possibly some pointers connecting them together. We've been calling these nodes throughout the course, but another way of referring to them is as vertices. So it's kind of a synonym. A vertice is essentially the same thing as a node typically. And when we talked about pointers connecting nodes together, another word for that is edges. So suppose we had a graph that looks like this. I mean, this is sort of shaped like a tree, right? This node could have some kind of child. Maybe, it has another pointer that's pointing to null. In this case, it doesn't. What I'm getting at here is that we could have graphs of all kinds of shapes. When we talked about binary trees and binary search trees, we mentioned that they never have cycles. But what if I take an edge from C and connect it to A? Here you can see we have a cycle going from A to B to C and then back to A. So when it comes to regular graphs, to some generic graph that we have, there are no restrictions. We could have any number of nodes and any kinds of edges connecting them together in any way. Now, technically, there are some restrictions, and that is that E is going to be less than or equal to V squared. Now, this is math, so maybe it's a little bit scary at first, but V just refers to the number of vertices that we have, aka nodes. In this case, you can see we have 3 nodes. So let's write that down. 3 squared is, of course, equal to 9. So we're saying that the number of edges is going to be less than or equal to 9. But why is that the case here? Well, what we're saying is from every single node, aka vertex is basically the singular for vertices, from every single vertex, we could have a pointer going to every other vertex. So a pointer, aka an edge, going here to one node, and then going to the second node. And actually, we can have an edge going in on itself. So a node can be pointing to itself. So we really don't have any restrictions here. So for every single node, we could have V edges, where V is the total number of nodes. So you can see that's how we're getting V squared from. To actually draw it out, let's now go to B. B could have a pointer going to A. It could have a pointer going to C. It could have a pointer coming onto itself. Same thing with C. It could have an edge going to A. It could have an edge going to B. And it could have an edge coming into itself. So each node has 3 edges going out of it. So we get 3 times 3 edges, right? This is the maximum number of edges we could have. I mean, technically you could have duplicate edges, but usually we don't consider that when it comes to graphs. So you're pretty safe to assume that we never really have duplicate edges. One thing you might have noticed here is that we have a pointer from A going to B. We also have a pointer from B going to A. So that means we can go between A and B, back and forth. And, you could also say that there's a cycle formed between these nodes. And, there's many other cycles throughout this graph that I'm sure you can find. Another thing to mention about this graph is notice how every single pointer, aka an edge, has a direction. This is referred to as a directed graph. A directed graph means that the pointers, the edges, have a direction. So, maybe we don't actually have pointers going both ways. So an example would be from B and C. From B, we can go to C, but from C, we can't necessarily go to A. That probably makes sense to you because we've already seen instances of directed graphs. Trees are directed graphs. Linked lists are directed graphs. But what does an undirected graph look like? Well, when it comes to actually drawing them, they can be drawn, many ways. Like you can just have a pointer that looks like this. This indicates that this edge is undirected, meaning you can go in either direction. You can go from B to A or A to B. Another way of drawing that, and I think it's more common, is just to draw it like this without any direction. So if we had an undirected graph that looks like this, that would essentially mean that every single one of these edges you can go in either direction. And that would be true for every single edge that we add to the graph in case we had more nodes or something like that. So this is a bit of background, and this graph that we've been looking at is a very generic form of graph. It's most common to represent a graph like this using adjacency lists, which we'll talk about in a bit. But first, we're going to start with matrices, or matrix if you're just talking about a singular matrice. And we're going to go through all three of these because these are three very common ways of representing graphs. And to be honest, this second one, adjacency matrix, is much less common. The most common ways, especially when it comes to coding interviews, is a matrix or an adjacency list. So those are the two that we're really going to be focusing on throughout this section. So let's start with a matrix. We haven't really talked about this much throughout this course, and you might already be familiar with what a matrix is, but in case you're not, I'll go over it briefly. It's essentially a two-dimensional array, but it can be used to represent a graph, which is what we're going to do in this case. But like I said, it's a two-dimensional array. So in a language like Python, it would look kind of like this. You have one array. This is the first row. Then you have the second array, which is the second row, and we keep going like that. So in this case, you can see we have 4 rows and 4 columns. Sometimes people use X and Y to, refer to the coordinates, which in my opinion can get confusing because in math, X is actually commonly used to refer to a row, and Y is used to refer to a column, which is something you might not be used to, especially, when you think about the XY coordinate system, right? And when it comes to algebra or something like that. So this can get confusing. That's why I very much prefer to think of it in terms of rows and columns. So I use R and C to do that, and I would recommend that you do the same thing. Whenever I've conducted an interview, I've seen so many candidates get messed up when they're using X and Y to implement their coordinates. So moving on, how would you access some arbitrary coordinate, like for example, this one? Well, remember that everything is indexed by 0. So this is the 0th row, this is the first row, this is the second row, this is the third row, this is the 0th column, this is the first, second, third column. So if we want to access this point, we'd go to row equals 1 and column equals 2. So with this coordinate system, we would say grid at index row equals 1. So this will give us the first row. Remember, this represents a array. So this is not a coordinate. This is a array. Before we had grid, which is a two-dimensional array, we've accessed index 1. This gives us a one-dimensional array. So now within this one-dimensional array, we can access a value like you normally would with a one-dimensional array. we want to access the value at index 2, aka column 2. So we would get this, and this is equal to 0, right? We're not assigning it to 0. I'm saying here that this is already equal to 0. This is the value that would be returned when we do this. So that's a bit of the basics. Now let's talk about how this is commonly used to represent a graph. You might have a scenario like this. In this case, you can see this matrix is populated with zeros and ones. Let's say that 0 represents a free space, meaning, this is a space that we're allowed to be located at. Any 0 is something we can, if we're creating a path somewhere throughout this matrix, we can move along the zeros. We can move there, we can go here, we can, go there, and maybe here and then down here, right? We can go through all these positions. We can't access any of the ones because they're blocked, we say. Right, this is just how I've defined it, and this can be a common way when it comes to coding interviews to define things. So how exactly does this represent a graph? Well, you might have already noticed. Typically, when it comes to two-dimensional grids, you're allowed to move left, right, up, or down. So you're allowed to move in 4 directions. You might be able to move diagonally, but it's typically less common. So again, how does this represent a graph? Well, you could say that we have a bunch of nodes. Let's say that in this case, the free spaces are nodes. So just to draw a circle, basically everywhere we have a node, it would look something like this. And of course, the ones are going to be blocked out. Now here we have nodes, but where exactly are the edges? Well, remember I said we can move left, right, up, and down. So this is what the edges would look like. In this case, let me ask you, are the edges directed or are they undirected? Well, since we can move left, right, up, and down, typically they're going to be undirected. From here, we can move to the left. From here, we can move to the right. So these edges are undirected. But what about, over here? Well, we can move up, I said, but there's nothing above here. So, this is essentially, you could say, a null pointer. But in reality, this matrix does not have pointers at all. These edges are implicit. These nodes are also implicit. These edges exist because of the rules that I defined. I said we can move left, right, up, and down. Maybe I could have defined, us being able to move diagonally 2 spaces. That's pretty uncommon. I've never seen that happen before, but we could define it that way. So this is a really, really common way of representing graphs when it comes to coding interviews. And for now, we're just going over how this is represented. Later on, we'll actually talk about how common algorithms can be implemented using this. There can be a lot of edge cases, as you might have noticed. So next, let's talk about what an adjacency matrix is. And these, like I said, are much less common than regular matrices and adjacency lists, and we'll talk about why. So we're going to use pretty much the same matrix we had before just for simplicity, but that does not mean that these are nodes themselves. When it comes to an adjacency matrix, the dimensions represent the nodes. So typically it's a square matrix. Let's say in this case the size is V times V, where V represents the number of vertices. So that's of course why it has to be square, because it's going to be, this is going to represent the vertices and this is also going to represent the vertices. We can't have, a 4th column here because then we have to have a 4th row. But if this represents the 0th vertex and this also represents the 0th vertex, then what does the value here actually mean? Well, typically it's going to be a 0 or a 1. A 0 in this position, for example, means that there does not exist an edge going from 0 to 1. A 1 in this position means that there is an edge going from 1 to 0. A little bit more formally, if we have, let's say, our adjacency matrix, which is this, aka this represented in code, and we have some arbitrary index here. I earlier mentioned that we're using row and column, but that's usually for actual matrices. When it comes to adjacency matrix, we know that the index represents a vertex itself. So in our example, let's say we're talking about the first vertex, that's what V1 is, and the second one, we're talking about the 0th vertex. So this means an edge exists from the first vertex to the second. So in this case, this is a directed edge. If the value is 1, that means that we have an edge. If the value is 0, that means an edge does not exist from V1 to V2. But what if we wanted to go the other way? What if instead we want to know if there exists an edge from 0 to 1? Well, we just swap the order of these two. More formally, we would look if there is an edge from V2 to V1. The order that you index it represents the order that we're checking, where an edge exists, what direction the edge is going. If V1 is first, then we're checking V1 to V2. If V2 is first, then we're checking V2 to V1. So just to draw out how this would look if we drew it as like nodes and edges, let's just go through every single one. Well, first, let's actually draw each vertex. We have a 0, we have a 1, we have a 2, and we have a 3. Remember, the vertices are from, the dimensions. So let's just go through every single one. So from 1 to 0, we have an edge. That means from 1 to 0, we draw an edge going like that. Of course, we don't have an edge going from 0 to 1. How do I know that? Well, let's look at our grid. From 0 to 1, we don't have a 1 here, so there's no edge. Going here, we have an edge going from 1 to 1. What does that mean? There's a self loop, so there's an edge going in on itself. So notice how an adjacency matrix can basically represent the same information for an entire graph, right? We can have self loops. We can have, from each node, we can have edges going to every other node. So what's the maximum number of edges we could have with an adjacency matrix? Well, if this is V, the number of edges is going to be equal to V squared. So that's consistent with what we talked about earlier. Running through the last couple edges, we have going from 2 to 3. So that would look like this. And we could have going from 3 to 1, which is over here. So we have the 3 going to the 1 over here. So why is it rare to use an adjacency matrix? Well, take a look at how much space we used here. No matter how many edges we actually have, to represent a graph, we're using an entire matrix. That means the space complexity here is going to be V squared, where V is the number of nodes or vertices that we have in our graph. We could represent the exact same information. Like, look at this graph here. It's not a lot of information. We have 4 nodes, and how many edges do we have? We literally have 4 edges. So we could reduce the space complexity to V plus V, right? The number of nodes plus the number of edges, which in this case is also equal to the number of nodes. So, in terms of big O, that would be big O of V. We could represent it this way. So why would we use a matrix which takes up a bunch of extra space and doesn't provide a ton of information anyway? Well, that's what leads us to our next way of representing graphs, which is adjacency list. That is essentially what we have drawn over here. Let's talk about it in more detail. So now let's take a look at adjacency lists, and these are typically the most common way of representing graphs, especially when it comes to coding interviews. I mean, using a matrix can also be pretty common though, so I think these two are good approaches to get familiar with. So it's very similar to linked lists and trees that we talked about. So we'll have something like a graph node, let's say, or you could just call it a regular node or vertex or whatever you want to call it. But the important thing is that there's really 2 things when it comes to nodes, right? We know a node could have some type of value, whether it's an integer or a character or a string, or maybe the value itself is some object, like it represents a person, right? Or a city, for example, right? And you want to know how are these cities connected together or something like that. Or if it represents a person, maybe you want to know how are these people connected? Like maybe it could be a social network. Maybe person 1 follows person 0, but person 0 doesn't follow anybody because there's no edges going out from person 0. That's just one example. Now, what exactly would a self loop mean in that context? Well, it's hard to say. That's why maybe we don't allow self loops in that type of graph. Who knows? but graphs are obviously very important. Now, when it came to linked lists, we could have either had a next pointer or a previous pointer. When it came to binary search trees, we could have a left or a right pointer. But with generic graphs, we could have any number of pointers. So how do we represent it? Well, here you can see in Python, we use, let's call it neighbors, or you could say following if you're in the context of like a social network. But neighbors is a pretty generic thing to use. And instead of just having 1 or 2 or 3 or 5 or, predefining the number of pointers we could have, we use a list. Now, in Python, this isn't clear, but what type is this list, aka this array, going to be? It's going to be an array of neighbors, aka neighbor graph nodes. So how would we represent this graph when it comes to graph nodes? Well, graph node 0 would have a value of 1 and its neighbors would be empty because it doesn't, have any nodes going out of it. So neighbors in this case means what edges is node 0 pointing to. There aren't any edges. For node 1, we would have neighbors of this graph node. So a pointer to this graph node would be in the neighbors of node 1, and the graph node itself would actually be its own neighbor. Would graph node 3 be in its list of neighbors? No, because in this case, we're using neighbors to refer to which nodes is this node pointing at. It's not pointing at graph node 3. Graph node 3 is pointing at it. So if we were looking at graph node 3, it would of course have a value of 3. That's not so important. What would its neighbors be? Its only neighbor would be node 1. That's the only node that it's pointing at. So it would have a single neighbor. It would be a pointer to this graph node. Lastly, 2 would have a value of 2, let's say. Its neighbors would be just 3. So in the list of its neighbors, it would have a single pointer to graph node 3. This is obviously a bit more space efficient than the adjacency matrix that we looked at because we only contain pointers for nodes that actually exist. We're not declaring 2 pointers for every single graph node or 3 or 5. We're just declaring an array, and it could be empty or it could have some pointers. Now, what if we had undirected edges? Like maybe, the way we've drawn this is wrong. Let's suppose that this actually doesn't exist for simplicity, but let's say we had 3 edges that look like this, right? They don't have arrows on them, so they're undirected. Well, that would just mean that for the neighbors of 0, it would have 1 in its neighbors. For the neighbors of 1, it would have 0 in its neighbors, and it would also have 3 in its neighbors. For 3, it would have 1 in its neighbors, and it would have 2 in its neighbors, and for 2, it would have 3 in its neighbors. When we have undirected edges, we're basically assuming that there is, a pointer going both ways, something like this. So that's the basics of the different ways to represent graphs. Now let's look at some really common algorithms when it comes to matrices, and then later we'll talk about adjacency lists. So now let's cover an example problem that you might see for a matrix. And surprise, surprise, the algorithm we're going to use is DFS. I told you it's one of the most common algorithms, and that's because it's very, very frequently applied to graphs. So in this example, we have pretty much the same matrix we looked at earlier. We want to count the unique paths starting from the top left and going to the bottom right. In this case, of course, the path can only move along zeros, not on any ones. And also, for a single path, we can't visit the same cell more than once. Why is that important? Well, take a look at this. We can go along these zeros, and then we could go down here and then left here, and then we could pretty much be in an infinite loop over here. Among these 4, we could basically keep going in a circle and however many times we want to, and then we could move down and then get to our destination, the bottom right. So in that case, what would be the answer to this question? Well, it would basically be infinity, And that's kind of boring. So we don't want to, for any single path, like suppose we go here and then we go down and then we go to the left. Now we can't move to this cell because we've already visited it, and we can't move to this cell because we've already visited. So the only option we have here is moving to the left. We can't do that. It's blocked. So we can only go down. Now here, of course, we can visit a couple cells that we haven't visited before. We can't go to the right, it's blocked off, but at this point you probably get the idea. So when we want to count the paths, we want to go through every single possibility. So an algorithm like DFS is going to be helpful for us. This also might remind you of backtracking, which is what we talked earlier, and that's because it pretty much is. This is an example of backtracking. There's a big overlap when it comes to DFS and backtracking. They're both recursive and they're both very, very similar in nature. So this DFS is definitely going to be more complicated than when we looked at binary trees. So I'm going to just show you the code immediately, and we're going to see how in general the algorithm will run visually and then compare that to what the code would do. And by the way, yes, again, this is going to be a recursive algorithm with the recursive case and of course a couple base cases. In this case, we don't just have one base case, we actually have two. Now, the simplest way to think about this is not to immediately look at the code, but to think about it visually. It's all a matter of choices. We start at the top left. Like that's always where we're going to start. So in terms of the parameters that we're going to be given the grid, of course, that's our two-dimensional matrix here. We're going to be given what's our starting position. In this case, it's going to be 0, 0. So we can have kind of the dimensions written out. So we're starting at the top left. And what are our choices? Well, remember, we can move in all four directions. We can move up, we can move left, we can move down, and we can move right. And we know that's going to be kind of annoying because we can potentially move out of bounds. That's the first thing that we have to worry about. So that's what the first base case is going to be. First of all, here you can see I'm getting the dimensions of the grid. This is how you would do it in Python. So the length of the grid, which is going to be this, is going to give us the number of rows that we have. The length of one of these rows, you can see I'm just taking the first row because we know every single row is going to have the same length because this is a rectangle. I think it's safe to assume that most of the time. And the length of one of those rows is going to be the number of columns. In this case, we have a simple case because we have a square matrix, so it's 4 by 4, but that might not necessarily be the case. Now, in my case, I'm calculating this every time we call the function. That's pretty unnecessary to do. We could pass in those parameters to the function, but I prefer to do it this way because it gets kind of annoying when you have to pass in 6 parameters into a function. But it doesn't change the time complexity, so this isn't such a big deal. The important thing is we have the dimensions of the matrix. Now, one case is that our row, remember this is the row, goes out of bounds. It's too small, or our column goes out of bounds. So what we could check is our row less than 0, or is our column less than 0? Or you could simplify that into a single case because the minimum of these, if the minimum is less than 0, that's all we care about. We just care about if one of these is too small. So we can just take the minimum of the row and the column and check, is it less than 0? That means either this is too small or this is too small. It doesn't matter because we're out of bounds either way. What would we do if that was the case? Well, if we end up going out of bounds, that clearly means that we did not find a path, at least down this recursive, chain, this path, we did not find a path to the destination. So in that case, we would return true. This DFS is supposed to count the number of paths. You can see that there's a few more cases where we would return 0. I'll get to those in a minute, especially as we run through the example. But to briefly cover them now, another case, of course, for our row and column, instead of being too small, they could be too big. Our row could be equal to the number of rows. Why are we checking if it's equal to the number of rows instead of greater? Well, remember, the number of rows is going to be 4, not 3. We have 4 rows. The last index is 3, but the number of rows is 4. So if row ever goes out of bounds, if it ever equals 4, then we also return 0. Or if our column goes out of bounds, it reaches 4, then we also return 0, right? We did not find a path, we went out of bounds. Why can't we take the max of the row and the column and check if it's greater? Well, because remember, the number of rows and columns might not necessarily be equal. In this case, since they're equal, we could take the max of the row and the column, but maybe if we had 4 columns, we would not be able to do that. We know we go out of bounds this way or this way if we're less than 0, because that's always going to be the starting point, but the ending point could be different. That's another case where we would return 0. And another case would be, this is the slightly more simple one, is if we reach a blocked position. Like from here, right, starting at the top left, we go down, well, we reached a blocked position. We're not even supposed to be here. So we basically stop searching. We're not going to continue our recursive case because we're not allowed to even visit this position. So we're going to stop immediately, and we're also going to return 0. Basically, we're saying by visiting this position, there are no valid paths that reach the destination. So again, we return 0. Now, the other case is if we reach a position that we've already visited before. And what is this visit actually going to be? Well, it's going to be a hash set data structure. So that's what we're going to end up passing in. It's not super clear in Python because we don't have static typing, but this visit is going to be a hash set. And it's going to tell us if we visited a position before along a given path. So that would be the example where we go here, then we go down, then we go left, and then maybe we go back up to the same position. At this point, if we visited the same position twice, we would stop. We'd say, nope, if we visit this position twice, there are no valid paths that reach the destination. We're not allowed to do this. So we return 0. The other base case is, of course, we end up somehow reaching the bottom right. We reach the destination. How do we know we reached the destination? Well, it's defined as the last row and the last column. So if R is equal to the last row, which is row minus 1, and our column is equal to columns minus 1, then we return 1. That means we found a single path. This is that particular path, for instance, right? This is one path that could be counted as part of the solution. Now let's actually run through this example and see how the code would actually execute. So when we actually call this function, our DFS, we're going to pass in the grid, of course. We're going to pass in 0 as the starting row and 0 as the starting column, and we're going to pass in some hash set. And that hash set is going to be reused throughout this recursive function. What that means is we're not creating a new hash set every time we make a recursive call. We're passing in a reference to that exact same object. Every recursive call is going to have access to that exact same object. So starting at the top left, we're going to, run through our base cases. Have we gone out of bounds? No, we haven't gone out of bounds. Have we already visited this position? Nope. Is this position blocked? Nope. Let's assume, by the way, there's always going to be at least one valid path in this matrix. But if you're not sure of that in a real interview, it's worth asking that as a clarifying question to your interviewer. Next, let's check maybe we've already reached the destination. No, we haven't. We can't return. So at this point, what we're going to do is add this coordinate to our visit hash set. The reason I'm using a hash set in this case is because it's just easier in terms of code to just add a pair of values to check if we've done this before. And we know adding and removing from a hash set is going to be a constant time operation. But alternatively, you could use a two-dimensional grid. Like visually, what I'm going to do is basically just mark the positions that we've already visited with a blue circle. So if we wanted to know if any of these positions is visited, we could use a hash set, or we could use a two-dimensional grid of the same size as the grid to represent that information. If you're allowed to modify the grid, you could also, as you visit a position, mark it as a 1 to indicate that it's already been visited, because then logically we will basically assume that we can't visit that position. But it's not always safe to assume that you can modify the input grid, so we're going to ignore that for now. So now that we've added this to our visit hash set, it's time to do the recursive case. We're going to set our count equal to 0. We're basically saying that from this position, we want to count how many ways we can reach the result. And we're allowed to move in 4 directions. So we can move down, that's going to be row plus 1. We can move up, that's going to be row minus 1. We can move to the right, that's going to be column plus 1. And we can move to the left, that's going to be column minus 1. Now, when we go up, we're going to go out of bounds. Our row is going to be less than 0, so we're going to end up returning 0. Okay, what about when our column goes to the left? We're going to end up returning 0. What about when we go down? Well, in that case, we're going to visit a blocked position. So in that case, we're going to return 0 again because it's blocked. So the only valid position we can go to is to the right over here. And when we do that, we're not out of bounds. We haven't already visited this, and it's not blocked. It's also not the destination, so we can't return 1, but we are going to add it to our visit hash set. So far we've visited these two positions. Now that we've gotten an idea of how the base cases work, I'm going to start running through them a little bit quicker. So from this position now, this second position that we're at, we're going to have another count variable. We're counting how many ways from this position can we reach the destination. And when we find that result, we're going to return that to the previous position that we were at, which was the starting position, and then we're going to have our answer. Basically, these two are going to have the same count. Now from here, we're allowed to go in 4 directions. We can go up, can't do that. We can go to the left, that is valid, but it's already been visited. We know that because it's blue here, but we know in code we would add it to our visit hash set. So it's already been visited, we can't do that. So we can go down, well, we can't do that either. It's already blocked. So we can't visit this position. So we can only move to the right. And then from here, this is valid. Neither of the base cases are going to execute. Now, from here, we're also going to have a cost, which is initially going to be 0, but when we calculate it, we're going to end up returning that cost to the previous node, which is going to end up returning its cost to the previous position. But from here, we can go in 4 directions. We can go up, it's out of bounds. We can go to the left, it's a position we've already visited, but we have 2 valid positions now that we can go to. We can go to the right, or we can go down. Now, since this is a DFS, depth first search, it's recursive, we're not going to go along these 2 paths simultaneously. We're only going to do one at a time. We're going to go as deep as we can in one of them, and then we're going to go backwards. We're going to backtrack. That's why this is a backtracking algorithm. And then we're going to go back to where we were, and then we're going to go along the other path. So in terms of code, which one of these would execute first? Well, it looks like row plus 1, which is this one, would be first. So let's just go along that. So this is going to be added to the visit hash set. And then from here, neither of the base cases is going to execute. This is going to be added to visit. And now we have 4 choices. We can go up, can't do that. It's already been visited. Can't go left. It's blocked. We can go to the right here, and we can go down here. Which one of them is going to execute first? Well, as we saw before, down is going to execute first. But just to actually quickly run through the other case, what would happen if we went here? Well, then we don't have many choices. We can't go to the left. We can't go to the right. We can't go down. We can go up here, right? And then when we go up here, we'd be stuck. We can't go to the left. We can't go up. We can't go down. We can't go below because it's already been visited. So this path, essentially what I'm saying is would not lead us to a solution. So let's keep that in mind. But going down here, it's also not a base case. We have some choices, can't go up, can't go to the right, but we can go left and we can go down. What's going to happen, by the way, if we went left? Well, here we wouldn't have many choices. We could only go to the left one more time. And here we can only go down. And here we have 0 choices. We haven't reached the destination and we can't move anywhere else. We can't visit the same positions we've already visited. So we'd be trapped, and along this path, we would end up returning the base case 0. Okay, so the question remains, from here, can we even reach the result at all? Can't go to the right. Well, we can go down. So from here, the only valid choice, as you can see, is moving to the right recursively. And at this point, we would finally execute the base case where we have reached the destination. And then we would return 1. So from here, this cell, we would have a cost of 0. We would execute 4 DFSs in all 4 directions. 3 of them would return 0. This one would return 0, this one would return 0, and this one would return 0. But the one here, the one where the column is incremented by 1, would return 1. And at this point, we would end up returning 1 to the previous node. But before we return 1 to the previous node, you can see we're backtracking. First, we marked this position as visited, and now we're going to mark it as unvisited. You're going to see why we're doing that in just a second. So from here now, we're going to backtrack. We're going to mark this as unvisited and go to this node. From here, we know that there was only one path here that led us to the solution. So from here, the count would also be 1, and we would return 1 to the previous node. And before we do that, we'd mark this as unvisited. So then we're going to go back to this node. We know from here, only one of the paths reached the destination. So from here, we would return 1 to this node. Now this node, if you recall, had 2 choices. We could either go down, which we just talked about right now, or we could go to the right. Now from here, we're going to go to the right. We're going to execute the second valid case. But now, as you can see, all of these are marked as unvisited. Why is that allowed? I thought we could only visit the same position once. Well, that's only true along a single path. What I'm getting at here is we could from here have 2 paths. We could, do something like this that reaches the destination. But we could also have a path like this that reaches the destination. These are 2 different paths. So they are allowed to visit the same position, right? Both of the paths visit this position, as you can see, and this position, and this position, and even the result. I mean, of course, they have to both reach the result. We said only a single path can't visit the same position twice, but multiple paths can reach the same position. In fact, they have to if they want to both reach the result. So I hope that makes sense. It can be a point of confusion. But as you can see from here, we don't have many choices. We can go down, and then we can go to the left, and then we can go down. And then from here, we're going to end up trying this path. It's not going to reach the result. And we're also going to try this path where we go down and then to the right. And again, we are going to reach the result, but this is a slightly different path. This is a slightly longer path, but it's still valid. So what we would realize then is backtracking all the way back is from here, we can reach the result in one way. From here, we can also reach the result in one way. So what that means is from here, we can reach the result in 2 ways. And what about from here? Well, from here, we're going to end up returning the count back to this. So we're going to say that from here, we can also reach the result in 2 ways. And we're going to return that to the previous, which is here. And we're going to say we can reach the result from the starting position. We can reach the destination in 2 ways. And that's going to be the final value that we return. So when we call our DFS with these parameters and then print the result, 2 is going to be the value that we print. You can try it in any of the code languages that we provide. So now finally, when it comes to analyzing the time complexity of a solution like this, it can get pretty complicated. So I like to think about it in a simple way, but it's not super precise. I mean, the way I'm going to think about it is just by proving to you the big O of n boundary, but it's not going to be super precise. We know from the starting position, let's suppose that the worst case is where there's all zeros. We don't have any blocked paths. So in that case, the length of a path could be the size of the matrix, right? Any given path could be the size of the matrix. So thinking about it in terms of a decision tree, we have from any position, we have 4 choices. And for each of those positions, we have 4 more choices. And by 4 choices, I mean we can go left, right, up, or down. Now, of course, we know some of them are going to execute the base case where we either go out of bounds, or maybe we visit the same position twice, or we visit a blocked position. But like I said, this is an imprecise way, but it still gives us an idea of the upper bound. For every node, we're going to have 4 choices, and the height of this tree is going to be the size of the matrix, because we know the longest path, which is what this tree represents. This tree represents a given path. Like if you follow a path in this tree, it represents a path in the matrix. So the height of the tree is going to be the number of rows times the number of columns. Now, if you recall from our binary tree analysis, this is going to be basically the number of branches, which in this case is 4, raised to the power of the height of the tree, which is r times c. More commonly, people will, use the dimensions to mean n times m. So you could say that the time complexity of this is going to be 4 to the power of n times m. That's the big O time complexity. So this is not very efficient, but that's expected when it comes to brute force DFS backtracking. Now the memory complexity would essentially be the recursive call stack. That means when we start at this position, then we make a recursive call here, then a recursive call here, and do that for pretty much the entire size of the matrix. At most, there could be that many recursive calls outstanding at the same time. So we say that the memory complexity is going to be n times m. We could also say this is the memory complexity from our visit hash set, because that is also going to be the size of the grid. Or instead of having a hash set, you could just create a grid itself to keep track of visited positions. So that's the idea here. I know it's pretty complicated. It's not the type of thing you'll completely understand the first time you see it. It can take a while to wrap your head around a lot of the concepts that we talked about here. But DFS, especially on a matrix, comes up quite often. Check out the practice section for graphs if you want to find some practice problems that you can try out. So next, let's talk about the BFS algorithm run on a matrix. And as you can see, I'm going to be jumping into the code relatively quickly because we actually have even more code than when we were talking about DFS. But the good thing is, at least in my opinion, that this is more simple to understand visually than DFS. If you recall, BFS, at least when we ran it on a tree, was, something like this, where instead of, starting at the root and then going as deep as we can and then going as deep as we can on the other side, what we did is we went layer by layer. We went through the first layer, then we went through the second layer, and then we went through the third layer, etc., etc. And that's the same idea here. We're going to go through the first layer, and then the second layer, and then the third layer, and then the fourth layer, and then the fifth layer, etc., etc. Now, what type of question would this algorithm apply to? Well, by far the most common is the shortest path algorithm. Suppose we want to find the length of the shortest path from the top left to the bottom right, and then return that. The best way to do that, the most efficient way, is the BFS algorithm. We could also use DFS if we really wanted to, the algorithm that we just talked about. We could use DFS. We could basically check every single possible path that can reach the destination and then find the length of the shortest one of those. But that's a brute force approach. BFS is actually more efficient. The time complexity of this is actually just going to be the size of the grid. Let's say that's n times m, where, this is the number of rows, this is the number of columns. This is what the time complexity is going to be. Whereas DFS was much, much less efficient. It was 4 to the power of n times m. So let's see how we can run this algorithm in terms of code and why it's so efficient. So the setup is going to be taking the dimensions of the grid. In this case, we're just past a grid. Let's say we already know that the starting point is the top left and we're going to the bottom right. We're going to have a visit hash set just like with DFS. So there are some similarities. We're going to have a queue just like for BFS when we ran it on a tree. The queue is basically going to tell us the current level that we're at. So initially, the queue is just going to be initialized with the first node. That's our starting point, and we're also going to add it to the visit hash set. It's already visited, and now from here, we want to see this is basically all the nodes we can reach with a length of 0. So this is, our starting point essentially. Then we're essentially going to loop while the queue is non-empty, and we're going to take a snapshot of the length of the queue. Initially, it's just going to be just a single element, and we're going to pop all 1 elements, just like with a tree. But when we pop, we know we're not getting a node. We're actually adding the coordinates of the position, and when we pop, we're getting the coordinates of the position. Now, we might have found the result. What if we were at the destination? In that case, we would return the length of the path. Initially, like I said, our length is 0. But in this case, we know we haven't reached the result. So one way to code this up, and basically this is going to look complicated. It's a lot of boilerplate, but once you get used to it, it's pretty easy. It's just a pain to type out, in my opinion, because we have a lot of conditionals. We know we can move in 4 directions, just like we did in the DFS approach. And we know there's a bunch of edge cases. We could go out of bounds. We could reach a position that's blocked. We could reach a position we've already visited before. Those are a few edge cases, and we're handling them the exact same way we did with DFS, where if the minimum of the row and the column is less than 0, we're out of bounds. If the row is equal to the number of rows, we're out of bounds that way. If the column is equal to the number of columns, we're out of bounds that way. We might have already visited it before, or it could be the value 1. That means it's blocked. What we would do in that case is continue. That means we would just continue to the next iteration of the loop. We would just skip this coordinate. But you can see it's not as simple as just taking a row and a column. I'm writing it this way basically to eliminate duplicate code. We could have we could basically have this conditional 4 times for all 4 directions. Or we could put this in a helper function. Another way to do it, though, is to take all 4 of the neighbors. When we say neighbors, these are not actually the neighbors necessarily. These are basically the directions. So this would represent the right direction. This would represent the left direction. This would represent below, and this would represent above. So when we take these directions and add them to the row and the column, so that's what you can see we're doing for basically all of these. For row, we're adding dr. dr just stands for difference in row. We're basically saying how much did the row change? How much is the difference of the row? This is 0, and that means the column is changing, right? Basically what I'm saying is by taking these, which represent the difference in row and the difference in column, and adding them to the row and the column, we will basically have all 4 directions enumerated. So this is sort of more complicated than it looks. You can write it out the long way if you'd like, or you can even, put this kind of stuff in a helper function if you would like. But this is another common way that it's done. And this sort of minimizes the amount of code that we have to write. I could also here have declared another variable saying, the new row and the new column, so that we wouldn't have had to write row plus dr, C plus DC out, multiple times. You can see I had to write that out a few times here, but I wanted to make it explicit in this case to show you exactly what we're doing. But feel free to modify this to make it look more simple or match your coding style, however you would like. But now that we kind of covered what this is doing, this is just a bunch of boilerplate to go through all 4 directions using a loop. What are we actually going to do with those 4 directions? Well, of course, we know that the base case, we go out of bounds, reach the same position twice, or we reach a blocked position. That's when we do nothing, we continue. Otherwise, it means we reached a valid position. By the way, which one of these 4 is a valid position? Only the one to the right over here. So this is the only valid position. What are we going to do with this? We're now going to add it to our queue. We know that's the next layer. This is the only node we can reach with a path length of 1. So we add it to the queue, and we also add it to visit. We don't want to visit this multiple times now. Now, after we've gone through all the neighbors and we popped this position from our queue, now we have this in our queue, and we popped this from our queue, now we have this in our queue. So after that loop, we're also going to increment the length by 1 to indicate that this layer that we have now added to our queue can be reached. All these nodes can be reached with a path length of 1. So now let's continue. And at this point, I'm going to focus mostly on the visuals. We know we can go in 4 directions, down, up, can't go in either of those directions. We can't go left, it's already been visited, but we can go to the right, and that's the only position we can go to. That's the only thing we're going to end up adding to our queue and adding to visit. And of course, this is going to have been popped from the queue. And after that's done, our length is going to be incremented to 2. By the way, when we did pop this guy, we checked, is it the destination? It was not. So we did not return the length, which at the time when we popped this was 1. So if it was the destination, we would have returned 1, which is what we would have wanted to do. So now we get to a bit of a more interesting case. We only have 1 value again in our queue, but we have 2 valid directions we can go to, right and below. And both of those are going to be added to the queue and added to the visit hash set. We wouldn't be able to add this one, of course, because it's already been added to the visit hash set. And then we would increment our length by 1. So our length would now be 3. So our length would now be 3. I'm going to write the length below now since we're kind of running out of space up there. But basically, this is the layer of nodes we can reach with a path length of 3 starting from the top left. And through that process, we know we would have popped this from our queue. So this is now part of our queue. We're going to go to the next layer. So this is where it's going to get a bit interesting because the length of our queue is actually 2 now. So we're going to pop both of these from our queue. It doesn't really matter which one we pop first. Let's just say we popped this guy first. So we pop it from the queue and we get its neighbors. Can't go up, it's already been visited. Can't go left, it's blocked. We can go to the right and we can go below. So what we're going to do is add these to our queue and add them to the visit hash set. Now you're going to see why we add to the visit hash set as soon as we add to the queue, because that's very important. Because next we're going to pop this guy from our queue. So we pop this from the queue and we see, can we go up? Nope. Can we go to the left? Nope. Can't go to the right. And we can't even go below. This was open, but we added it to the visit hash set. So now we know it's already been added to the queue. So we're not going to add it to the queue again. This is very important. This is why the algorithm runs an n times m complexity, because we know for sure we're never going to add the same position to the queue twice. We're never going to visit the same position twice. And we still know that these are all of the cells we can reach with a path length of 4. So this is going layer by layer. That's very important. So now we have 2 positions in our queue. So we're going to execute this loop again twice. For 2 iterations, we're going to pop, let's say, this guy first. We can't go below, can't go to the left, can't go right, and can't go up. So we pop it, but we don't end up adding anything to our queue. It's just going to execute the continue statement. So at this point, our queue only has this guy. So we pop this from our queue, and then we add its neighbors. Can't go up, can't go right. We can go below, and we can go to the left. So these are now going to be added to our queue. What's the length to reach these? Well, previously it was 4, so let's add 1 and get 5. We can reach both of these with a length of 5. That's the shortest path to reach both of them. Now, we don't actually know what is the shortest path. We're not keeping track of that. It would probably be this or this, but that's not important. We just care about the length in this case. And at this point, we're almost done. We have 2 positions in our queue. Pop this guy. Can't go up, it's blocked. Can't go to the right, it's visited. Can't go below, it's blocked. We can go to the left and add this to our queue and to our visit hash set. And then we pop the last one in this layer. Can't go left, can't go below, can't go up. We can only go to the right. And at this point, we've gotten to the destination. But you can see this is where we look for the destination. After we pop from our queue is when we check, is this the destination? We don't check if it's the destination when we're adding to the queue. I mean, we could have done it this way. We would have to rewrite it a little bit because we're only incrementing the length after we've updated the entire queue. But let's just run this very quickly. So we finished this layer. So now our green layer here takes a length of 6 to reach. Now finishing up, let's say we pop this guy first. We'd pop it and we can't go up, can't go left, can't go right. We just add this guy to our queue and then we pop this one. So when we pop it, we check, is it the result that we're looking for? It is. And by the way, at this point, our length would still be 6. So we would return that and that would be the result. So I color coded it a bit to indicate to you the length of each of these. So to actually run that, you could see BFS would just be past the grid and then the function itself would take care of the rest. And then we could print the result. In this case, it would be 6. The path would look something like this. But that's the main idea. As you can see with this approach, we're never going to visit the same position twice. We're never going to add the same position to the queue twice. Worst case, we'd visit the entire grid. So in that case, the time complexity would be the dimensions of the grid, which is n times m. The space complexity would be the same because that's the max size that our visit hash set or our queue could end up being. So this would be the memory complexity and also the time complexity. So in my opinion, this is a bit more easy to understand in terms of like the visuals. Code-wise, there's a lot of boilerplate though, as you can see. So it can kind of be a pain to write out, but once you get used to it, it's just a matter of writing out all the, edge cases and getting them right. But it can definitely take a while to get good at it. I'd recommend taking a look at some of the problems in the practice section under the graph topic, because BFS is definitely a common algorithm that comes up a lot. Next, let's move on to adjacency lists. And the good thing, in my opinion, is that these are much more simple to run an algorithm on rather than on a matrix. Now, originally, we talked about the idea of having a graph node class or an object for an adjacency list where, we're storing some kind of value. It could be a string, a character, an integer, and then it's also going to have a list of neighbors. The neighbors are going to be pointers. They could be directed or undirected, but essentially they're going to be pointers pointing at other nodes. That's one way to do it. And if we were actually creating our own graph, we would do something like that. But when it comes to coding interviews, it's actually much more common to just use a hash map to represent an adjacency list. Because as you can see, there's two things we care about: the value, or the ID of each node, as long as that is unique. And for coding interviews, it's almost always unique. Each graph will have something that uniquely identifies it, whether it's an integer or a character or a string. In this case, let's say we have a character A. And so that's going to be the key of our hash map. So this is how I'm doing it in Python. But the important thing here is that this is the key, the character is the key, and the value for that key is going to be a list. And that list is going to represent the neighbors. So this is just an example adjacency list where we have two nodes, A and B. Now the lists here are empty, so that basically means there aren't any pointers. That's just a very simple example just to kind of show you that this same idea can be represented using a hash map. Now let's actually do a very common algorithm when it comes to coding interviews, which is usually you're not just given the adjacency list itself, you have to build it yourself. You are given enough information to build it though. So the most common thing is you're given a list of edges. In this case, these are directed edges, and we want to build an adjacency list with them. What does directed mean again? Well, for this edge, we're basically saying that there exists some edge going from A to B. So it's directed. So it's going from A to B. This is what it would look like in terms of the picture. Now, how do we go about actually building the adjacency list? Well, let's just first declare a variable. This is, let's say, an empty hash map. We're going through every single edge, which is a pair of nodes here. The values are, the identifiers for that node. So we're calling it, in this case, source destination. So source is going to be the first of the pair, and the destination is going to be the second of the pair. This is how you would do it in Python, but other languages will also be provided below. So one thing is that our hash map is empty, so these keys might not even be in the hash map itself. So if they're not, that's what we want to do. So we're first going to check, is source not in the adjacency list? Is this key not in the hash map? If it's not, let's add it to the hash map and give it a value of an empty array. So the neighbors are initially empty. We just added this node to the adjacency list. We're going to do the same thing with the destination. Even though we're not going to be adding anything to the array of the destination neighbors, because we want to at the very least make sure that every node that we saw in the list of edges is added to the adjacency list, even if it doesn't have any neighbors, because we want to at least have an empty list to confirm it doesn't have any neighbors. So here, what we would say is for the adjacency list of the source, for our first example, that would be A, we're going to append to its neighbors, which initially is an empty list, we're going to append B. So visually, we would say A points at B. It has a neighbor B. Going to the second edge, we would do the same thing. B, though, in this case, has already been added to the adjacency list. We did that previously with this line. But C is not, so we add C to the adjacency list. It doesn't have any neighbors, though, of course, just yet at least. But now we know B points at C, so we have an edge going from B to C. And then third edge, B to E, we're going to do the same thing. Put an edge over here, C to E. That means there's an edge going like this, and E to D. So there is an edge going like this. So this is what the graph would look like. We were given all the information we needed. We were given the edges, but from the edges, we could imply what the nodes are. And then we have a representation that looks like this. This is the same information that would be stored in our adjacency list, which, we're using a hash map to do that. And you can see why, because it gives us all we really need. Now let's move on to actually running some common algorithms like DFS and BFS on adjacency lists. And the good thing is these are a little bit easier than doing them on a matrix. So let's run pretty much the same algorithm we did on the matrix using DFS, depth first search. We want to count all the paths. And again, this is going to be a backtracking algorithm, but the code is a lot more simple, mostly because we don't have 1,000 edge cases to worry about. We don't have to worry about going out of bounds. That's what makes adjacency lists nice. So assuming we're given this input, that's our adjacency list, and assuming it was given in the form of a hash map in Python, we're going to run DFS, count the paths. Let's say the starting node is going to be A in our DFS, and the target node is going to be E. So we want to count the paths from A to E. The adjacency list is passed in, and we also have a hash set, which is going to keep track of visited nodes along a single path, just like we did with a matrix. So that hash set is passed in. We're going to call this function and then print whatever it returns. So starting at A, we check, has this node already been visited? If it has, there's 0 paths from here to the result. It's not the case though. Well, is this node already the target? If it is, then that means we found a path to the target. We can return 1. It's not E, so it's not the target. Then we declare a variable to count how many paths from A to E. We add the node to the visit hash set and we go through its list of neighbors. The good thing here is it's so easy to iterate through the list of neighbors because we have it in our adjacency list. We don't have to go, manually in 4 different directions. That's really annoying to write out. So we call DFS on each of the neighbor nodes. Now, maybe A doesn't even have any neighbors. That would be an empty list, an empty array, and then this for loop would never even execute. But in this case, A does have 1 neighbor. So we were at A, now we're going to be at B. I'm using these arrows to kind of indicate which node that we've already visited and which node we're currently at. So we're at B right now. So recursively, we're at B. Is this node already been visited? Nope. Is this node the target? Nope. So now we're counting how many paths from B to E. So that will be 0 initially. We'll add B to the visit hash set and go through the neighbors of B. It actually has 2 neighbors, C and E. Let's say we call DFS on C first. Notice how it's DFS, not BFS. That means we're going as deep as we can in one direction. So we get to C. This is not visited already, and it's not the target. So we count paths from C to the target, and we add C to visit hash set, and we go through its list of neighbors. It only has a single neighbor. So then we call DFS on E. Now we are at E. It's not been visited already, but it is the target node. So we return 1 in this case. That means we found this path that leads to E. So we return 1. This is the base case. So we return 1, we backtrack, and then we end up back at C. From C, we called DFS on E, it returned 1, we add 1 to our count, and then this loop is going to stop because we only had 1 neighbor from C. So then we're going to backtrack now. From visit, we're going to remove C. So you can think of that as, removing this pointer. And then we're going to return the count, which is 1, and that 1 is going to be returned back to B. And then from B's perspective, we're going to take that result, 1, add it to its count. So its count is now 1. But for B, it actually has a second neighbor. It has the neighbor E. So we're going to call DFS now on E from B. So pointer here again, same base case is going to execute. Now we found another path that looks like this. So we return 1 from E. We add that 1 to our count for B, which is 2. So we know there's 2 paths from B to E. And then that's its last neighbor. So then we're going to remove B from the visit. So you can think of that as removing this pointer. And that's kind of the backtracking part. And then 2 is going to be returned back up to A. So 2 is over here. And then A only had a single neighbor, so its loop is going to stop and it's going to end up returning 2. So there were 2 paths from A to E. Now we didn't even end up visiting D. That's because we didn't need to. Whenever we get to the target, we're going to immediately stop. So you can see that this is much more simple than running it on a matrix. But the core ideas are definitely the same. We have some base cases. We want to, enumerate every single possible path. And if we end up visiting a node, then we want to stop. Now, in this case, we never visited the same node twice along a single path. But for example, suppose that from C, there was actually a pointer back to B. In that case, let's say we do a DFS, we get to A, then we get to B, then we get to C. And then from C, we have two choices. We can go to E or we can go back to B. But if we did that, we went back to B, we'd see, well, we've already visited this once along this path, so we can't just visit it again. So at that point, we would end up returning 0 from there. We'd say that there's 0 paths going to the target where we start at B, come to C, and then go back to B. There's 0 valid paths doing it like that. So it can get complicated to analyze the time complexity of this type of brute force backtracking DFS approach. So I'll try to keep it simple. We know that at any given path, we know that we're going to go through every single possible path in the entire graph. I mean, we have to count the paths. So that could be the worst case. The length of a path is going to be no larger than the number of vertices that we have, because we can only visit each vertice once along a given path. So that is going to kind of represent the height of our decision tree. Now for each vertex, how many choices could we have? In the worst case, it would be, every vertex is connected to every other vertex. So that would mean V choices. But we're going to say, let's just use some value n, where n is the average number of edges that each node has. This is a slightly more common way of talking about it. But the important thing is just kind of understanding the ideas that I'm talking about here, understanding the ideas of choices and how long could a path be and stuff like that. So the height, again, of this decision tree, when I say decision tree, I mean, all the decisions that we could make when we're counting the paths on this graph. The height is going to be V. The number of choices we could make is going to be N, where N is, let's say, the average number of edges that each vertex has. So in that case, the time complexity, analyzing this the same way that we did a binary tree, is going to be something like N to the power of V. So big O of N to the power of V. Now, it's pretty rare to actually have to analyze the time complexity this type of way, but the important thing to recognize here is that this DFS, this backtracking, is not going to be very efficient. Just like most backtracking algorithms, this is exponential. We know it's exponential because the power here is going to be a variable. If we had n squared, that's not the end of the world because the power is a constant value. Even n cubed wouldn't be that bad. But here, as the size of our graph grows, which is V, this time complexity is going to grow extremely quickly. So this is very, very inefficient. BFS is much more efficient, as we will see. So let's take a look at the same example problem. Let's try to find the shortest path from a node to a target. So in this case, the starting is going to be A again, and the target is going to be E. Those are the parameters we're passing in, and we're passing in the adjacency list that we built, for this representation. Now the BFS is going to work similar to the matrix. We're going to initialize a few variables. The length is initially going to be 0. We're going to have a hash set, and we're going to add the starting node as visited to that hash set, and we're going to have a queue, and we're going to add that starting node to the queue. So that's the first level in our BFS. So while our queue is not empty, we have a single node in our queue right now. We're going to iterate through the length of that queue at that given moment. So we're going to take a snapshot of the length. It's 1. So we're going to run this loop 1 time, and we're going to pop 1 node. So we pop that node. This is our current. We're going to check, is it equal to the target? If it is, we can return the length, which is initially 0. So we're saying, the length from starting here to arriving here is 0. That would make sense, but this is not the target. So we go through its list of neighbors the same way we did earlier, but we check, is this neighbor not already visited? If that's the case, we can add it to visit, and we can add it to the queue. But if it is already visited, then we don't do either of those things. In this case, it has 1 neighbor, B, and yes, we're going to add this to the queue and add it to visit. So then this loop will stop, and this loop will also stop because we went through every node in the queue at that point, and then we can increment our length. So we know it took a length 1 to arrive at this level. Next, we check, are we still executing the while loop? Well, our queue is not empty, so we are. we're going to take a snapshot of the length of the queue. It's 1. It's just one node. So we're going to run this loop once. We're going to pop this node. It's not the target, so we're not going to return. We're going to go through its list of neighbors. It has 2 neighbors, and each of them have not already been visited. So we're going to add both of them to the visit hash set and add them to the queue. And then we're going to increment our length by 1. So it took a path length of 2 to get to this layer or this level of the graph. And now we're going to run the while loop again. We're going to start going through both of these nodes. We're going to take a snapshot of this queue. It's going to be of length 2 because there's 2 of these here. We're going to pop them. Let's say we pop C first. We would pop it. We would check it's the target. Nope. We would go through its list of neighbors. It has a single neighbor, which is E. We would check, has it already been added to visit? Yes, it has. So we're not going to add it again. Then we're going to end up popping the next one, which this is the only one remaining. We pop this. Is it equal to the result? Yes, it is. So we return the length. It's 2. That means that the shortest path was length 2. And we know that because we went layer by layer. These are all the nodes we could reach with a path length of 0. These are all the nodes we could reach with a path length of 1. These are all the nodes we could reach with a path length of 2. And this is the first time we encountered the result node. So the shortest path to that node must be 2, and that's what we return. Now here, the time complexity is going to be the same as earlier. It's going to be the size of the graph. But earlier we talked about for a matrix, the size of the graph was n times m. And technically what we didn't account for when we were doing that were the edges. This is the number of nodes in the matrix graph, but the number of edges for each node was 4. So technically the time complexity for running BFS on a matrix is 4 times n times m, but we know we don't care about constants. So this is the time complexity we get here. But in this case, let's say the number of nodes is actually v for vertices, right? So that's the size of the graph. But how many edges could each node have? Well, technically v, right? Because remember, we learned earlier that e is going to be less than or equal to v squared because each vertex could have v edges. So if we're talking about edges for each node multiplied by the total number of nodes, it could be v times v, which is equal to v squared. But we don't write it this way because we know for sure here that's not necessarily the case. This is not a full graph where every single node has the maximum number of edges. So to be more accurate, we could say the size of this graph is actually v, which is the number of vertices, because we potentially will have to visit every single one of these. In the worst case with our BFS, we'll have to add each of the vertices to our visit hash set, but we might also have to travel along every single edge, which may not necessarily be equal to v. It could be greater or it could be less. So to be more accurate, we say that the time complexity for this BFS is equal to v plus e, where e is the number of edges in the graph. The space complexity, though, is a bit more simple. We know in the worst case, we could add every single node to the visit hash set and every single node to the queue. So the memory complexity is going to be big O of v, where that's the number of vertices, of course. Now, before we finish up with graphs, I want to mention that we definitely learned a lot here, and that's because graphs are a very, very big topic in general, but also for coding interviews. They're a topic that comes up very frequently. But one thing we didn't talk about is what if these edges actually have some kind of weight attached to them? For example, the length of, this edge is not just 1. We've kind of been assuming each of these edges has the same length. We treat them the same. But what if, the same way how cities are connected by roads that could be of different length, what if the length of this was 2, this was 3, this was also 3, and maybe this one is 10? What would be the shortest path in that case? It would have been this over here, not what we had. We said the opposite. We said this is the shortest path. So our algorithm here would get that wrong. There is a much more complicated algorithm that could account for edges that have some weight or value attached to them. And if you want to learn more about it, I recommend checking out the Advanced Algorithms course. There's actually tons of graph algorithms that we didn't talk about. but they can get very, very complicated. There's a lot of academic research that's actually gone on in graphs. These are really complicated structures. But I think understanding DFS and BFS gives you a really, really strong foundation. After all, the shortest path algorithm that could solve this problem is actually based on BFS anyway. It's just a modified version. If you'd like to practice some graph problems, I recommend checking out the practice section and going to the graphs topic. Okay, so now let's finally move on to dynamic programming. Are you nervous? Because you should be. Just kidding. Dynamic programming can be really scary for a lot of people, but I'm going to try my best to try to make it as simple as possible. And the first problem we're actually going to be looking at is one we already talked about when we were talking about recursion, and that is the Fibonacci sequence. And this is an instance of a one-dimensional dynamic programming problem. Let me show you what I mean. But first, let's recall what the Fibonacci sequence is. Basically, the 0th Fibonacci number is defined as being 0. The first Fibonacci number is defined as being 1. An arbitrary Fibonacci number, the nth in this case, is defined as being, the n-1 Fibonacci number plus the n-2. For example, the second Fibonacci number is equal to the first Fibonacci number plus the 0th Fibonacci number. Therefore, the second Fibonacci number would be 1 plus 0, which is just equal to 1. And then we could continue calculating the third and the fourth Fibonacci number and continue going just like that. Now, if we wanted to calculate an arbitrary Fibonacci number, let's suppose the fifth Fibonacci number, we would do it using a loop, kind of how I just talked about right now. We would calculate the second, and then we'd calculate the third, the fourth, until we got to the fifth. It'd be pretty straightforward. We could do it in O of n time using a loop like that. What you might not realize is this is actually an instance of a dynamic programming problem. But to really understand the fundamentals of dynamic programming, I'm going to spend a lot of time analyzing it and showing you how we can take the recursive solution that we talked about earlier and convert it into a dynamic programming problem, because that's what you'll normally be doing when you start getting to more difficult dynamic programming problems. So when we solved this problem recursively before, we started with the decision tree. We wanted to calculate the fifth Fibonacci number, and we know to do that, we have to get the fifth minus 1 Fibonacci number, aka the fourth Fibonacci number, and add it with the n-2 Fibonacci number, aka 5 minus 2, aka 3. And basically, we keep drawing out this decision tree until we get to the base cases, which are these two here. So let's continue doing that. For 4, we know we have to get the third and the second Fibonacci number. So for 3, we have to get the second and the first Fibonacci number. And then here, we're going to do the same thing. Notice we're doing the same thing that we did over here. We're going to get the second, the first Fibonacci number. For 2, we're going to get finally to a few base cases, 1 and the 0th Fibonacci number. And for 2 here, we're doing the exact same thing. So this is some of the repeated work that you might be noticing. We're going to get the first Fibonacci number and then the 0th Fibonacci number, and then 1 is already a base case, so we're not going to do anything. We know the first Fibonacci number is by definition equal to 1. Now the only one of these we have to expand upon is this one over here. So 2, again, repeating the exact same thing we already did a couple places. We have to say this is going to be the first Fibonacci number plus the 0th Fibonacci number. Now the code for this approach would look something like this. So we have our recursive function. We know that if the Fibonacci number we're trying to calculate, let's say it's n, is less than or equal to 1, we're going to return n itself. So basically if n is equal to 1, we return 1. If n is equal to 0, we return 0. If that's not the case, we call our brute force recursive call in both directions. N minus 1 is going to be the left branch, n minus 2 is going to be the right branch. And then of course we would get to the base cases, and then those would return up and those would return up, and they would go all the way back up until we got to the root. The downside of this approach though is the height of this decision tree is going to be, the Fibonacci number that we're trying to calculate. In this case, it's 5, so the height of the tree is going to be approximately equal to 5. The number of branches is going to be 2, so In terms of big O of n, we would say that the size of this tree is going to be roughly equal to n. I mean, we can see that some of the levels aren't completely filled, but this is a rough upper bound. N in this case is what the Fibonacci number that we're trying to calculate is. But we see we're doing a lot of repeated work here. When we calculated the second Fibonacci number over here, we had to draw out this subtree, this recursive subtree, and then we wanted to calculate the second Fibonacci number again, and we had to draw out the entire subtree. And then, we even had to do that a third time over here. But what's even worse than that is when we wanted to calculate the third Fibonacci number, we had to draw out an even bigger subtree over here. But we didn't only do it once, we had to do it twice. We had to draw out the same subtree over here. So what I'm getting at is there's a lot of repeated work that's going on, and there's a technique that we can use to eliminate this repeated work. It's sort of based on dynamic programming. So this technique of optimization is called memoization. We can basically take a brute force recursive solution. If we see we're creating a decision tree to solve the same subproblem, in this case, calculating the second Fibonacci number, we can cache that. Basically, after we calculate it once, we can store that somewhere so that next time when we're trying to solve the exact same subproblem, we don't redo all of the work. So in this case, we wouldn't even create these subtrees. We would automatically know what the second Fibonacci number is because we calculated it once. So in terms of code, you can see it looks very, very similar to the recursive solution. That's why when you're first learning how to do dynamic programming problems, what people do is they'll solve the recursive problem and then try to add memoization, try to add caching to it. And I still, to be honest, use this technique when I'm solving a difficult dynamic programming problem that I can't figure out. You can see when I call the brute force, I'm passing in 10, but when I call the memoization, I'm passing in 5. Please ignore that. You can consider this as a 5. We're calculating the fifth Fibonacci number using the brute force way. And now with memoization, we're calculating it the memoization way. You can see we're passing in a parameter, which is the cache. Most commonly, I like to use a hash map to represent the cache, but you can also use a array, but I think it's easier using a hash map. So in this case, I'm actually going to draw our cache as a array because that's essentially what it is. We're mapping a integer. So in this case, a Fibonacci number. So for example, in this case, 2, and we're mapping it to the Fibonacci number, basically the second Fibonacci number. So I'm going to draw it as an array, but we know we're actually using a hash map in this case. So initially we pass in an empty hash map into memoization. So, think of this as the empty hash map. We pass in 5. We're trying to calculate the fifth Fibonacci number. Have we reached the base case? Is this a 0 or a 1? Nope. Is 5 already in our cache? Well, our cache is empty. By the way, this is an O of 1 operation to check if a value is in the cache. That's why we're using a hash map. But we could also use an array and it would be the same time complexity. In this case, 5 is not in our cache, so we call, memoization, or you could call it whatever you want, but we're recursively going to check what the n-1 Fibonacci number is. In terms of the decision tree, we're going to start at 5. Now we're going to check what the fourth Fibonacci number is. We're going to check the same base cases. It's not a base case. It's not already in the cache. Our cache is empty. So then we're going to call memoization n-1. We're going to call the recursive function on 3. And 3 is also not going to execute any base cases. Then we're going to call memoization on 2. This is where things are going to get interesting. So now we're at 2. This isn't, again, quite a base case. It's not in the cache. So now we're going to call memoization on 1 over here, which is a base case. We know 1 is going to end up returning 1 because the first Fibonacci number is 1. Then from 2, we calculate the 0th Fibonacci number. We know that's also a base case, and that's going to end up returning 0. So here we're going to have 1 plus 0. Add those together, it's 1. So we found what the second Fibonacci number is. It's equal to 1. So what are we going to do? We can immediately return it, but we're actually going to cache it before we return it, because what we're saying is we just calculated the second Fibonacci number. If we ever need to calculate it again, which we know we're going to here, we want to be able to calculate it immediately without having to make any recursive calls. So we cache that. So in our cache, for the key value 2, we're going to say the Fibonacci number is 1. Then we're going to get back up to 3. We calculated the second Fibonacci number. Now we have to calculate the 3 minus 1, which is 1, which is a base case. So here we're going to calculate the first Fibonacci number. It's going to end up returning 1. So then we're going to add these two together, which is 1 plus 1. The second Fibonacci number is 1. The first Fibonacci number is 1. Add those together, we get 2. Therefore, the third Fibonacci number is 2. So we're going to throw that in our cache. So for the key value 3, the Fibonacci number is 2. So now we know if we ever have to calculate the third Fibonacci number again, we don't want to have to repeat all this work, so we won't have to. And now again, things are going to get a little interesting. Now we're at 4. We calculated the third Fibonacci number. It's time to calculate the second Fibonacci number. We could go through that whole recursive tree, but when we try to calculate the second Fibonacci number now, we're going to check, well, it's not less than or equal to 1, but it is in our cache. 2, the second Fibonacci number, is in our cache. What is it? The second Fibonacci number is 1. So that's what we're going to return. We're not going to do the recursive case. This is a base case. So we're going to end up returning 1. So when we're trying to calculate the fourth Fibonacci number, we get 2, which is the third Fibonacci number, plus 1. So the fourth Fibonacci number is 3, and we can throw that in our cache and then return that up to the parent, which is 5. So now we're trying to calculate the fifth Fibonacci number. We already calculated the fourth. Now it's time to calculate the third Fibonacci number. So we're going to recursively call that, and we're going to see it's not less than or equal to 1. But again, we check our cache and we found it. We found 3 in our cache. The third Fibonacci number is 2. So basically, we don't even have to execute this entire tree. We only have to check 3, and then we immediately find the value, which is 2. So we calculate the fifth Fibonacci number, which is 3 plus 2, and that ends up being 5. So we throw that in our cache. The fifth Fibonacci number is 5, and then we return it. So you can see by caching, this is all the work that we eliminated. So this is actually the size of our decision tree when we implement caching. This is what it looks like. You can see that this essentially is linear. To calculate the fifth Fibonacci number, we calculate the fourth. To calculate the fourth, we calculate the third. To calculate the third, we calculate the second. And to do that, we calculate the first. It's linear. I mean, technically, you can see that each of these nodes actually has a right child, sort of. So you could say that actually the size is not just n, it's 2 times n, but we know that that's also still linear. It reduces to big O of n. So that's the overall time complexity when we implement caching, which is also called memoization, which is actually also called sometimes top-down dynamic programming. This kind of diagram, memoization and caching, is sometimes referred to as top-down dynamic programming because we're starting at the top of the tree and then going down. There's actually another form of dynamic programming, which is generally a bit more difficult actually, because you can't just take the recursive solution and then add caching to it, and it's called the bottom-up approach of dynamic programming. And as the name implies, for this tree, we're going to start at the bottom of it and then work our way upward. So we're still not going to redo all of this work that we, scribbled out, but we're going to start at the bottom of this tree and then work our way upward. And I'm going to show you that right now. So this approach where we don't use recursion at all is sometimes called the true dynamic programming approach. Like some people don't even consider memoization dynamic programming. Some people only consider this to be dynamic programming, but this is also called the bottom-up dynamic programming approach. So we would just pass in whatever Fibonacci number we're trying to compute. Let's say in this case, n equals 5. Here I wrote n equals 10. But to keep it simple, we're going to just calculate the fifth Fibonacci number. So we know we're trying to calculate the fifth Fibonacci number, and recursively we saw that to do that, we have to get the fourth. To do that, we have to get the third, and to do that, we have to get the second. To do that, we have to get the first, and to do that, we have to get the 0th. But why start here, which was the top, and then go top down when we can go bottom up? Start at the base case immediately, and then work our way upwards, because when we have the base case, we can calculate, well, this is another base case, but when we have both of the base cases, we can calculate this guy, and then we can calculate this guy, and then we can calculate this guy until we get to the result that we actually want. So in terms of code, it would be pretty simple, actually. This is the simplest code, I think, of the three solutions because it's essentially a loop. Now, it can look a little bit complicated, and that's because I've really optimized this to the point that we don't even need an array, but I'm going to draw it this way just to get the main understanding across. First of all, if we have a Fibonacci number that's less than 2, we're going to return whatever n is. So the 0th Fibonacci number we know is going to be 0. The first Fibonacci number we know is going to be 1. But assuming we have n equals 5, we're going to create, this subarray. I'm calling it DP, and we'll have this as our little subarray here. And now visually, forgetting the code for just a second, visually we would start here. We would want to get the second Fibonacci number. Now, how do we do it? Just take the two previous Fibonacci numbers, add them together. 0 plus 1 is equal to 1. Now we want to get the third Fibonacci number. Add these two guys together. 1 plus 1 is 2. To get the fourth Fibonacci number, add the two previous together. 1 plus 2 is 3. To get the fifth Fibonacci number, add these two together, and we get 2 plus 3 equals 5. We did the result. What was the time complexity? Big O of n. We just had to iterate, n times, roughly speaking. What's the memory complexity? Also big O of n. We're maintaining an array that we have over here. But my question to you is this array even necessary? Every time we got to a value, when we were trying to calculate this guy over here, we only needed the two previous values. And then when we moved, when we calculated that, and then we moved here, we didn't even need those values. We needed the two previous values here. We didn't need this guy anymore. So my question is, do we actually have to maintain the entire array? Or maybe we can get away with only saving the two previous values at a time. And that's exactly what we're gonna do. So forgetting this portion of the array here, we only need an array of size 2. And initially the values are gonna be 0 and 1, just like we've drawn over here. But then we're gonna get to I equals 2. We're trying to calculate the second Fibonacci number. We're gonna save this guy in a temporary variable. I'm just gonna write it here. We're gonna save 1 here. And then we're gonna calculate in this position what the second Fibonacci number would be. It's going to be these two guys added together. 0 plus 1 is 1. So what we would do is overwrite this. We know in this case it's, it was previously 1 and it's staying 1, but I'm just doing this to get the point across. And then in the 0th position, we would put whatever originally was over here in this spot. The good thing we saved it here, but in terms of code, we would save it in a temporary variable. So here we would now put 1. So this is telling us we calculated now the second Fibonacci number and put it over here, and then we put the first Fibonacci number over here because we know we're going to need the first and the second Fibonacci number. Now when we take our I, increment it by 1, and try to calculate the third Fibonacci number. And you can probably at this point see where I'm going here, but I'll quickly run through it just to get the point across. So we're going to overwrite the value here now by taking these two original values, 1 plus 1, adding them together, and then putting it over here. So now we have a 2 here. And we would have put the original value, which was 1, and then put it over here. It's already 1, but we're doing it anyway. And at this point, this would be the second Fibonacci number, and this would be the third Fibonacci number. And now here we would take 1 plus 2, add them together, replace this position with 3, and take the previous Fibonacci number, which was 2, and replace this guy with 2. And then these two would be the third and fourth Fibonacci number. And at this point, we've sort of ran out of space, but you probably get the idea. We would now take these two, 2 plus 3, add them together. We would get 5. That's the fifth Fibonacci number. We would end up storing it in this spot. And then we would end up, once our loop stops, which it would now, we would end up returning the value that's stored over here, which is 5. So that's the fifth Fibonacci number. And of course, since we're looping n times, the time complexity is going to be big O of n, but we saved space. We didn't have to allocate the entire array. The space in this case is just an array of size 2, which is constant memory. So our memory is not scaling as we increase our input n. So this is the most efficient way to solve this problem. And I hope this gives you an idea of the thought process that goes behind dynamic programming. Dynamic programming is essentially a technique that takes a big problem and then simplifies it What makes this a dynamic programming problem is that we have originally a big problem. We're trying to calculate the 5th Fibonacci number. But to do that, we have to solve a sub-problem, which is calculate the 4th Fibonacci number. To do that, we have to solve a sub-problem, which is the 3rd, and another sub-problem until we get to the base cases. So that's what dynamic programming is basically all about. Taking a big problem and then breaking it down into sub-problems, which Fibonacci number is a very good example of because it's mathematically a sub-problem, and then solving that sub-problem. Most dynamic programming problems can actually be represented with equations like this. So this is the one-dimensional case. Why this is considered one-dimensional is because we have a one-dimensional array, which is our solution space, right? We have to get the 0th, 1st, 2nd, 3rd, 4th, 5th Fibonacci number. It's one-dimensional. So that must imply that there are two-dimensional dynamic programming problems, which is correct, and that's what we're going to talk about next. So next, let's move on to two-dimensional dynamic programming. And let's solve a pretty familiar problem at this point, counting paths. So we're going to be given a two-dimensional grid, and we're starting at the top left. We want to go to the bottom right, and we want to count the number of paths that can lead us there. Now, in this case, though, there aren't any blockers. Like before we had zeros and ones were blockers, but this time we don't have that. And we have another thing that's going to simplify things for us. We can only move down or move to the right. So that's going to make things pretty easy for us. So for example, one path would look like this. Another path would look like that. Since we can only move down or to the right, every path is actually going to be the exact same length, because as we move down, we're getting closer to the bottom right. As we move to the right, we're getting closer to the bottom right. And, eventually the paths are going to converge and they're both going to be the same length. Every single path to the result is going to be the same length. Now, based on what we learned in the graph section, we can do this recursively with depth first search. And so that's the brute force way to do this, but it's not going to be very efficient. So suppose we're given the number of rows and the number of columns. In this case, notice we actually don't care about the grid itself. It's not a parameter. What we actually care about are the dimensions of the grid. In this case, it's a square grid, so it's 4 by 4. So 4 rows and 4 columns, and the input is going to be the starting position. We know it's going to be 0, 0 to start with. So when I'm actually calling brute force, I'm passing in 0, 0 as the starting coordinates, and the dimensions are 4 by 4. So we have some base cases. First of all, what if we go out of bounds? How are we going to go out of bounds in this case? Because our row is never going to be too small because we're starting here, but we can only move down. So if we go out of bounds, it's because we went too far out, not because we went too far up. So when we reach this case, it'll be because our row is equal to 4, which is the number of rows we have. So if r is equal to 4, then we went out of bounds. Same thing with the column. We can only move to the right. We can't move to the left. So that simplifies things for us. So when we go too far to the right, so if c equals the number of columns, we can return 0. That basically means we went out of bounds. There's no valid path that goes out of bounds that reaches the result. The other base case, of course, would be if, we did reach the goal. So that would be if r is equal to rows minus 1 and column is equal to columns minus 1. In that case, we would return 1. That means, okay, this is a path. Otherwise, suppose we're actually starting from here. It's not a base case. So what we would do is call brute force 2 times, because we can either go down, that's this first case where we say row plus 1, or we can move to the right where we say column plus 1. So brute force, this is going to basically be a decision tree with 2 branches, because for every position, no matter where we're at pretty much, we can either go down or to the right. We can't go in 4 directions. We can only go, in 2 directions. So this decision tree has 2 branches. What's the height of the decision tree going to be? Well, like I said, every path is going to have the same length. So any path in our decision tree is going to have the same height, roughly. And the height is basically going to be the number of rows plus the number of columns, because that's practically what the length of every single path to the destination is going to be. So we can say that the time complexity is 2 to the power of n plus m, where let's say these are the dimensions of the grid. So I've written that up here as well. So that's the time complexity. So obviously it's not very efficient, but we can make it much more efficient. Basically, the time complexity can be reduced to the size of the grid because we're going to notice some repeated work. First, I'm going to quickly walk through a little bit of the brute force, and then we're going to see how we can use caching to improve the time complexity. So first we start here, we go down and we go to the right. So now we want to know how many ways can we reach the destination from here and from here. Well, from here, we're again going to go to the right, or we're going to go down, or we're going to go to the right. From here, we're going to do the same thing, go down or to the right. And then, from here, suppose we're going to go down and to the right, and then from here we're going to go down, which is a base case, that's going to return 0, and we're going to go to the right over here. From here we're going to go down, can't do that, we're going to go to the right as well. From here, same thing, but finally we get to the destination. This is going to return 1 for us. So when we're calculating how many ways from here can we reach the destination, we're going to have a value of 1 now. What about from here? Well, here was 0 because we went out of bounds, but from here was 1. So we're going to take those two results, add them together, and we get a 1 over here. Same thing for this guy. There was a 0 here and a 1 here. So add them together, we get a 1. Now, finally, when we get back up over here, we have the value below, but now we're trying to calculate the value that's over here. Well, from here, we can have two choices. Go to the right or go down. We have the value down here, but what's the value over here? We don't know. We have to go down and we have to go to the right. Well, what about from over here? Again, we can go down and to the right. Well, right is out of bounds. That's going to return 0. Down is reaching the destination. That's going to return 1. So add those together. We get a 1 over here. Now we can calculate what goes over here. 1 plus 1. So add those together. We get a 2 over here. What about in this position? There's a 1 over here and there's a 2 over here. Add those together, we get a 3 in this position. Then we can calculate what goes over here. 1 plus 3, add those together, we get a 4 in this position. So now you're starting to get the idea. So as we try to calculate, starting from here, how many ways can we reach the destination, we pretty much have to we have to solve the sub-problem for every other position, because to solve this problem over here, we have to solve these two problems. But to solve these two problems, then we have to solve these next 3 problems. And to solve those, we have to solve these, and etc., etc. We have to keep going until we get to the base case, which is the result, and then work our way back to what we were originally trying to do. When you do this recursively and then add caching to it, which I'm going to go over right now, this is called the top-down dynamic programming approach. But as you might have noticed, we can eventually also work our way starting from the bottom and then work our way up, which is going to be the true dynamic programming approach, which is called the bottom-up approach. But for now, let's focus on taking this brute force and adding caching to it. So let's undo a little bit of this work and go back to some of the basics that we were talking about over here. For every single position, no matter what it is, we can get how many ways from here can we reach the result just by taking the value below it and the value to the right and adding those two sub-problems together and then assigning it over here. But notice something. If we want to solve this sub-problem, we have to solve this sub-problem and this sub-problem. But if we want to solve this subproblem, we have to solve this subproblem and this subproblem. Well, we have to solve this subproblem twice. That's where the repeated work is coming in. And it's going to get worse and worse. From here, we have to solve this and this. From here, we have to solve this and this. From here, we have to solve this and this. This is being done twice, as you can see. This is being done twice, as you can see. So there's a lot of repeated work going on, and I can draw out the entire thing. I encourage you to do that if you want to have a better understanding of it. But the idea is there's going to be a bunch of cells that have repeated work. And it's going to be exponential because you can see that there are 2 different ways we can land in this spot. That means there's going to be 2 different ways we can go move to the right over here. There's two different ways we can land in this spot. So there's going to be two arrows actually going down here, two arrows going to the right. So it's going to get more and more and more. And if we had a really big grid, it would be very, very inefficient. So caching is going to help us a lot here. So in terms of code, the good thing is about caching, there's very few changes that you actually have to make here. So essentially the first base case is going to stay the same, and the second base case is going to stay the same, but in between that, we're going to add the case where if our cache, which in this case is a two-dimensional array, which is going to be the exact same size as our input grid. Well, technically we don't have a grid, but the cache is going to be of the dimensions of that, input. And you could also use a hash map if you wanted to. Generally, I prefer to use a hash map, but in this case, we're using a two-dimensional grid, and our memoization solution has an extra parameter for that two-dimensional grid cache that our brute force did not have. And when I'm passing in a grid here, this is kind of complicated. If you're not familiar with Python, this is essentially creating a two-dimensional grid with all zeros. That's a 4x4 essentially. If you are familiar with Python, you still might not understand this because this is, kind of a weird syntax. Essentially, we have an array of size 1 with a 0 inside of it. We multiply it by 4, which gives us an array of size 4 with 4 zeros inside of it. And then we create an outer array, taking that array and creating 4 copies of it. That's where this comes from. And that gives us basically a 4x4 grid with all zeros inside of it. It's a lot easier to do this in most other languages, thankfully. But when we have that cache, if we don't go out of bounds, so take this, for example, we went down and to the right, and then from there we went down and to the right, and then from here we went down and to the right. But in reality, one of these is going to execute first. Let's say this one executes first, and then we calculate how many ways from this position we can reach the result. And once we have that, we're going to add it to our cache. So you can think of this grid as being our cache. We're going to put the value here. So as we saw before, all the values in the bottom row are going to be 1. That makes sense because from here, we can't move down. We can only move to the right. So from here, there's one path that can lead us to the result. And from here, there's one path that can lead us to the result. From here, there's one path that can lead us to the result. The next row we already filled out earlier looked like this. So now let's briefly go over filling out the rest of it. So from here, we want to calculate the value. We go down and to the right. We don't have the value here. Let's go down and to the right. We don't have the value here. Let's go down and to the right. There's nothing on the right, but below there's a 1. So here we can put a 1 as the result. Now we can calculate the value that goes here. 2 plus 1, that's going to be 3. Now we can calculate the value that goes here. 3 plus 3 is 6. And we can calculate the value that goes here. 4 plus 6 is 10. So now when this guy wants to go down and to the right to calculate the value that goes here, we already have the value that goes here. We cached it. By building this grid, we added it to our cache. We're not going to run DFS. We're not going to run, our recursive call from this position again and do all that repeated work. We don't have to do that anymore. So from here, when we go down, we're going to check, is that value out of bounds? Nope. Is that value in our cache? Yes. So we can return that value in our cache, which is 6, but we still have to calculate the value that goes over here. By the way, the order of this is somewhat important. Now, these two could be swapped. You don't have to put them in this order, but it is important that we put this before this because we have to check if we went out of bounds before we try to index this two-dimensional array. Because if we index it with, an R or a C that's out of bounds, then we're going to get an exception thrown or an error or something like that. So this is usually the first check that you want to make. You want to make sure we're not out of bounds. That's really important. But otherwise, if none of the base cases execute, we're basically running the same thing we did with our brute force. We're running the recursive call, going in both directions, either R plus 1 or C plus 1, passing in the same, hard-coded values, rows, columns, whatever, and passing in that cache, which is a reference to the object. We're not creating a new cache every time we call the recursive function. We're only creating a single cache initially and then reusing that throughout the recursive calls. And then when we add the result of those two together, so in this case, we're going to recursively call memoization over here. We're going to go down and to the right. And from here, we're going to go down and to the right. this is going to be a 0. There's a 1 over here. Add those together. We get a 1 here. What value goes here? 3 plus 1. So we get a 4 over here. Now we can finally calculate what goes over here. It's 6 plus 4. So there's 10 ways from here that we can get to the destination. There's 10 ways from here that we can get to the destination. Add those two together. That means there's 20 different ways from the starting point that we can get to the destination. And these are all unique paths. So this is something how it would play out if we did it recursively with memoization. But as you kind of saw, why should we even start at the top and work our way down and then recursively, solve the subproblems and then go back up? Why not just immediately start at the bottom and then fill in these values and then get all the way to the top and ultimately have that result anyway? Well, the time complexity will still be the same because we still have to pretty much fill out this entire grid. As you saw right now, the time complexity is the size of the grid. We're not doing any repeated work, but in this case, we also have to declare a bunch of space. We have to create a two-dimensional grid, which is going to be the same size. But the benefit of dynamic programming is sometimes we don't have to declare all that extra space. As we saw with the Fibonacci sequence, we were able to save space by using the bottom-up approach. The same is true with this problem. Let me show you what I mean. So this is what the code for the true dynamic programming, aka bottom-up approach, would look like. It's usually pretty short for dynamic programming problems. The bottom-up approach usually has a lot less code than the recursive approach, but it's usually difficult to come up with unless you have a good understanding of the recursive approaches. And there are many dynamic programming problems that follow this same pattern of having a two-dimensional grid and, solving subproblems that are below and to the right, and then eventually arriving at the solution. So in this problem, what we're going to do is start bottom up. We're going to start at the base case and then calculate these values and then go here and then calculate these values and then keep going like that. Now, it's intentional, the order that we're solving these subproblems, and we kind of have to do it this way, starting at the last row, going to the left, starting at the next row, going to the left, because, well, this is the base case, and for us to know this value, we have to get the bottom value. Good thing here is for the last row, there's nothing below. We can just kind of assume that there's a bunch of zeros here if we really want to. And that's sometimes a technique that's used in more complicated two-dimensional dynamic programming problems. In this case, we'll look below, that'll be 0, and we'll look to the right, and what we expect from here is that there's a 1 there. Now, it doesn't really make sense that from here, how many paths are there that can lead to this position? Well, is there 1 path or is there 0 paths? Technically, to me, it makes sense that there would be 0 paths, but as the base case, we put a 1 here because that's just what allows our math to work out. If we put a 0 here, then the value we're going to get here is going to be 0, and then here, and then here, and then all of these are going to end up being 0. We know that's not correct, so we put a 1 here. And then when we want to calculate this value, we go below and to the right, we take this, add it, and then we get a 1 here. And so we have to compute it like this. And then when we want to get to the next row, we already have all of these populated. So for us to calculate this position, we look below and to the right, there's nothing there. And we already have the value populated here. So we'd get a 1 here. And then we can populate this value only after we've gotten these two. We can add them together and get a 2 here. So it's going mostly in the same order that our recursive algorithm did and the memoization one did. It's just we're immediately starting at the bottom and working our way up. We're not even making the recursive calls starting from the top. So in terms of code, it would basically be the exact same thing. What we're going to do here is declare a previous row, which is going to be all zeros. What that basically is, we're implicitly creating a row over here that's just telling us that there's all zeros over here. And then we're iterating through this 2D grid, starting here, starting in the last row and then going up and up and up. And in our nested loop, we're starting at the last column and then working our way to the left. Well, technically, we're not starting at the last column. We're starting at column minus 2, the number of columns, which in this case would be 4. That's what we're passing in here, 4 minus 2. So we're starting at the second to last column. Why am I doing that? Well, because we know that the base case is going to be 1 anyway. So we actually fill in that base case. We create a current row. So this is going to be our current row, and we're going to fill in a 1 at the last position. And we actually know that for every row, the last value is going to be 1 because we know from any of these going down, there's only one way to reach the destination. We can't go to the right for any of these anyway. But notice how we're actually not creating a 2D grid because it's not necessary. Notice how to fill in this entire row, all we need is the previous row, aka the row below it, and that's enough. We don't need anything from the row above or the row above that. We just need the row below it. And to get the values in this row, we only need the values below that row. So at any given point, we're only going to have 2 rows in memory, the previous row and the current row. So the space complexity is going to be 2 times the number of columns. Let's say m is the number of columns. So this is the space complexity. This can be reduced, of course, to big O of m, because we don't care about constants. So that's the space complexity of this approach. Clearly, the time complexity, we are having to still iterate through the entire grid. So the time complexity is still going to be n times m. And if you're a little bit confused by the syntax that we're doing here, this is Python. Of course, you could do this in any language. But this is basically starting at rows -1, and this is starting at columns -2, this column. And this is basically saying we're going to keep going until we've gotten to the 0th row, and we're going to stop as we get to the -1 row. So we're not going to execute when we get to the -1 row, and we're not going to execute when we get to the -1 column position. That's why we have -1 here as well. And the last -1 basically means we're decrementing each time. So we're going to take the column, decrement it each time. In most languages, I think it's a little bit more obvious what the for loops are doing, and we have the code for those below if you want to check them out. So at this point, you probably get the idea, and I bet you could fill in this grid yourself if you really wanted to, but I'll do it really quickly. So when we want to calculate the value here, which is current row, we're going to take the current row, column plus 1. So that's our way of looking to the right. We take the current row, and get the column plus 1. To get the value below, we take the previous row in the same column. So we take those, add them together, and then assign that value here. It's going to be 1. We're going to do the same thing here and here. They're all going to be 1. Now, before we start looking at this row, we're going to take our current row, which was this, and assign it to previous row. So this is now going to be considered our previous row. This is no longer going to be in memory. And now here, we're going to create a new current row of the same dimensions. It's going to initially be all zeros, but we're not going to care about that. And the last value here is going to be a 1. And then we're going to start calculating these. This one is going to be 1 plus 1, 2. This one is going to be 3. This one is going to be 4. And then we're going to do the exact same thing over here. This is going to be out of memory. This is going to be the new previous row. And this is going to be the new current row. There's going to be a 1 here. This is going to get a 3. This is going to get a 6. This is going to get a 10. And again, this is going to be removed from memory. This is going to be the new previous row, and this is going to be the new current row. There's going to be a 1 here. This is going to be 4. This is going to be 10. This is going to be 20. And then finally, we're going to delete this from memory as well. This is going to be our previous row. We're going to return the 0th value in that previous row. That's exactly what we wanted. We're going to return the 20. So this is, believe it or not, a relatively simple 2-dimensional dynamic programming problems. They can get a lot harder, but if you can get really good with the concepts that we talked about here, understanding the idea of decisions that we're making, not doing any repeated work, and basically filling in the values of a grid, you can go very, very far with more difficult dynamic programming problems. If you want to practice some, check out the practice section and look at the problems in the 2-dimensional dynamic programming topic. So now finally, the last topic that we're going to cover is bit manipulation. And the reason that we're covering it last is because I think it's not really a super important topic, especially for coding interviews, but it's definitely something that comes up. So I think it's very important to, at the very least, understand some of the basic things that you can do with bit manipulation. And even beyond coding interviews, I think it's good to have a fundamental understanding of the basics. So there's a few logical operations that you can do with bits. Now, first of all, what is a bit? Well, we talked about it close to the beginning of the course. Bits are just zeros and ones. Computers basically use zeros and ones exclusively under the hood, but most of that ends up being abstracted for us. But let's start with a few fundamental operations. One is the AND operation. So with zeros and ones, we can do a logic AND, aka a bitwise AND. So for 2 given bits, suppose 0 and 0. Now we usually use this character, the ampersand character, to indicate a bitwise and that's actually the case for most languages. So I'll summarize the main operations in terms of code. Now this is Python, but actually these operations are pretty much the exact same in most languages. So the logic AND operator is going to use this character. So 0 ANDed with 0 is the value 0. So basically what the logic AND means is that both bits have to be 1 for the result to be 1. But if that's not the case, the result is going to be 0 regardless. So if the first bit is 0 and the second bit is 1, then the result is still going to be 0. If the first bit is 1 and the second bit is 0, again, the result is going to be 0. But only in the last case where both bits are 1 is the result going to be 1. So that's where the name comes from, and both have to be 1, and then the result will be 1. Or is sort of the opposite. Only a single one has to be 1, and then the result will be 1. But if neither are 1, then the result will be 0. So this is the character for logic OR. And so continuing, 0 or 1 will be 1, because only one of these has to be 1. And then if the first one is 1 and the second one is 0, the result will again be 1, because only one needs to be 1. And if both of them are 1, the result will be 1. The third case is called exclusive OR, and this actually does come up occasionally in coding interviews. It's basically the result will be 1 only if one of the bits is 1, not if both of them are. So it's similar to OR, except it's exclusive OR. Only exclusively one of these can be 1, and then the result will be 1, not if both of them are 1. So the character for that is the up caret, kind of. So 0 exclusive OR with 0 is going to be 0. Exactly one of these should be 1 for the result to be 1. It's not, so we don't get a 1. But if we have the second one is 1, then we get 1 in the result. If the first one is 1, then we also get a 1 in the result. But if both of them are 1, we get a 0 in the result. So you can kind of take a look at these three and compare them. They're mostly straightforward, but if you haven't seen this before, if you've never seen these are called truth tables. Basically, these are some logical operations that we could do. This is not something you'll necessarily have to draw out in like a coding interview, but it's good to kind of understand the logical basics of what's going on here. Now, of course, there's the negation operator, which is the tilde in most languages. It'll just take any bit and take the negation of it. So, if we take the negation of 1, it's going to be 0. If we take the negation of 0, it's going to be 1. It's pretty straightforward. These are really the only two cases. The last thing is bit shifting. So if we have some binary integer, usually in programming languages, we're talking about 32-bit integers, but I'm not going to draw all that out because, it would take up a bunch of space and it's not super important to get the idea across. Let's say we had an integer that, was 0, 0, 1. So basically, this is the integer 1 in binary representation. Of course, we could draw out all 32 digits, but we're not gonna in this case. Now, if we take this and bit shift it to the left by 1, that's what we're doing down here. We're taking n, which is 1, and shifting it to the left by 1, and then assigning that to n. So what this would do is it would just take all these bits and then shift them to the left by 1. So by doing this operation, we would get a result of this. What if we did this operation again on this integer now? Well, then we would get a result like this. What if we did it one more time now? Well, assuming in this case we just have an integer with 3 bits and we have no bits, to the left of it. Well, if we bit shift this one more time to the left, where does the 1 go? Because previously we were saying every bit was shifted to the left. Well, in this case, we have a 1 here. It's going to get shifted to the left, and then it's essentially going to be dropped off. It's going to be deleted. It's going to be replaced with a 0. It's not going to circle back here. It's just going to completely be deleted, and then we would have this as the result. This 0 would be moved to the left, and when this 0 is moved to the left, it's going to be always replaced with a 0. That's what we kind of saw throughout this example. When we shifted this by 1, it was replaced with a 0. When we shifted this, again, replaced with a 0. Now, one thing that's very important when we have a binary value, let's suppose we have 1, 0, 1, 1, this is the ones place, right? This tells us how many ones we have. That's how numbers are represented in binary. The next digit is going to tell us how many twos we have. So this is the twos place, and then the next digit is going to be the fours place, and the next digit is going to be the eights place, and it's going to keep going like that. Now this is somewhat comparable to if we were, suppose had base 10, if we were thinking about integers in terms of base 10, which is what we do most of the time. We're all used to thinking of numbers where the max value a digit can be is 9, and then if we get the value 10, we of course add a new digit for that, right? We count 1, 2, 3, we go all the way up to 9, and then when we get to 10, we add a new digit for that. That's called base 10. This is called base 2 because by the time we start at 0, then we get 1. By the time we get to 2, we add another digit for that. So this in binary is not the number 10, this is the number 2. That's why this is the ones place, this is the twos place, this is the fours place, eights place, etc., right? Each time we move to the left, we're getting a new power of 2. So essentially, this is 2 to the power of 0, this is 2 to the power of 1, this is 2 to the power of 2, 2 to the power of 3, which is 8, and it keeps going like that. That's how binary numbers work. Whereas with base 10, you have a number like this. This is the ones place, aka 10 to the power of 0, that evaluates to be 1. This is the tens place, right? This is not 3. This tells us we have 30 because it goes in the next spot. So this is 30, right? We're pretty familiar with that. That's basic math, but we call this the tens place, aka 10 to the power of 1. This is the hundreds place. This isn't 4, this is 400, right? So this is 10 to the power of 2. 10 to the power of 2, by the way, is 100. So it keeps going like that. This is the thousands place, etc., etc. That's why we call this base 10. So I wanted to kind of review that with you in case you weren't already familiar. And by the way, what happens if we take this and shift it to the left by 1 and we got something like this? 5 times 5, 4, 3, 2, and then we add a 0 in this spot, similar to how we were doing it with binary. Well, shifting to the left and adding a 0 when it comes to base 10 is essentially taking this and multiplying it by 10. If you're familiar with math, you know multiplying by 10 essentially adds a 0. Well, in terms of binary, when we're shifting to the left by 1, we're actually multiplying by 2. That's very important. That's a pretty basic and important idea to remember. As you shift to the left, you're multiplying by 2. This in binary is the integer 1. This in binary is the integer 2 because we have, something in the twos place. This in binary is the integer 4, and it basically keeps going like that. So that's bit shifting to the left. We can also bit shift to the right. So suppose we had a value like this. By the way, this represents the value 4. In binary, suppose we shift to the right by 1, we would get something that looks like this. Suppose we shift to the right by 1 again, we would get something that looks like this. Notice how as we shift, we took this 1, moved it to the next position, and then we replaced what was on the left with a 0. That's similar to what we did when we were shifting to the right. So now we're going to shift to the right one more time. We're going to get basically 0. And similar to how when we shifted to the left by 1, we were multiplying by 2. When we shift to the right by 1, we're dividing by 2. This is 4, this is 2, this is 1, and this is 0. So we're dividing by 2 when we shift to the right, but if we have an odd number, we're going to round down. So with all that being said, let's jump into an example problem where we're given some integer and we have to count the number of bits. So suppose we were given an integer like 23, which by the way, in terms of binary would look something like this. In most languages, it would be represented with a 32-bit integer. So we would actually have 32 bits. In this case, we would just have a bunch. So in this case, we have 5 bits. So we would have probably 27 zeros that come before it, which would make this a 32-bit integer. But let's just draw out the 5 bits for simplicity's sake. And suppose we want to, given this integer, count the number of bits. Now, n in this case is going to be 23 base 10, but we know under the hood that's represented by some binary value that will look like this. So we want to count the bits of its binary representation. How can we do that? Well, we're basically going to use the same ideas that we talked about over here. We're given that as a parameter. We're counting the number of bits. Initially, that's going to be 0. While n is greater than 0, so suppose we're given an integer like 23 and we want to count the number of 1 bits in its binary representation. Well, in terms of binary, it would look something like this: 1 0 1 1 1. Now, most of the time you'll be using a 32-bit integer to kind of store this. Python actually has unlimited bits for values, but let's suppose we had 32 bits. Basically, since this is 5 bits, we would have 27 more bits, which are all leading zeros. So I'm not going to draw all of those out. We're just going to focus on these. And we want to count the number of 1 bits in its binary representation. So n in this case is the parameter. It's going to be 23. But we know every base 10 integer has some binary representation. In this case, this is what it looks like. We want to count how many 1 bits it has. In this case, it has 4. But how can we count them algorithmically? Well, it's not too complicated. We just need some of these operations that we already talked about. So in our function, we're given the parameter. We're going to declare count, which is going to, be the count of 1 bits. We're going to count while our value n is greater than 0. We're assuming we don't have to worry about negative numbers in this case. And we know that the value 0 itself, even in binary, will just be 32 zeros. So there's not going to be any 1 bits for that anyway. So now we're basically going to count 1 by 1. We're going to check the ones place. Is there a 1 bit here or is it 0? How do we know? Well, we can use the logic AND operator, the bitwise AND. By taking n, which is right now 23, and bitwise ANDing it with 1, we're going to get an operation that looks something like this. This is what 1 looks like in binary. Of course, it would have a bunch of more zeros, but we don't care about those zeros. So when we bitwise ANDed single digits, we had this truth table over here, and this will help us out. When we bitwise AND multiple bits, it's basically taking each of these and taking the bitwise AND of them. So we know that for these two, it's going to be 1. And for this, it's going to be 0. For this, it's going to be 0. For this, it's also going to be 0. And for this, it's also going to be 0. Because both of the bits have to be 1 for us to get a 1 in the result. Now, let me tell you something. When we take any number and bitwise AND it with 1, the result that we get is always going to be either 0 or 1. The reason is because this is 1 in binary. It has only zeros here. So we know everything in the result is going to be 0, except possibly this digit. And it's all going to depend on what this digit happens to be. If this digit is a 1, we're going to get a 1 in the output. If this digit is a 0, we're going to get a 0 in the output. We're using the value 1 because it's special. It has all zeros except for this bit. So this will tell us if we have a 1 in the ones place or not. So in this case, we are going to get a 1. So this is going to evaluate to true. So then we're going to increment our count by 2. And then what we're going to do is take our n and shift it to the right, which we know is the same as dividing by 2. So when we take this and shift it to the right, we get something that looks like this. Right, we're basically chopping off this bit. We don't care about it anymore. Then we're taking the rest of these, shifting it by 1, and then we're replacing the leftmost digit with a 0. Now we're just going to repeat the same thing until this value becomes 0. So we're going to take the digit 1, the value 1, bitwise AND these together. In this case, we're going to get a 1 in the output because this is a 1. And then we're going to increment our count by 1 again. So far our count is 2. We've counted 2 1 bits. And we're going to basically do the same thing. So now this is going to be shifted to the right by 1. We're going to get something like this as the value. We're going to check is this a 1 or not by taking the bitwise AND. It is a 1. So now our count is going to be 3. and then we're going to shift this to the right by 1. We're going to get something that looks like this. Now we're going to bitwise and this. So we're going to check, is this a 1 or not? We're going to get a 0. So this is not going to evaluate to true. So we're not going to increment the count by 1. Our count is still 3. And then, of course, lastly, we're going to take this, shift it to the right by 1. We're going to finally get this. We're going to check, is this a 1 bit or not? It is. So we're going to increment our count. Our count is now going to be 4. And then we're going to shift this to the right by 1 again. And at this point, it's going to be 5 zeros. So our conditional is not going to execute anymore. So our loop is going to stop, and we're going to return the count that we calculated, which is 4. So we had 4 1 bits in this particular integer, which is 23. So 23 has 4 1 bits. So we didn't go super in depth in this because I don't think it's super worth going into. I think understanding the basics is probably enough. And there are some practice problems in the practice section if you want to practice more bit manipulation type problems. Usually they just require a bunch of tricks, which is why I think they don't really come up super often in coding interviews, because they don't really make for good coding interview questions. Either you know the trick or you don't. So they're not the best coding interview questions in my opinion. But these basics that we talked about definitely can come up even outside of coding interviews. So it's good that you have now learned them.